Right, so let us start with the first concept, that is your electronic configuration of D block elements. So first I'll complete with the D block elements, then come back to your F block elements. So whenever we're learning electronic configuration concept, as I said, first I'll explain you the concept, then I'll start doing all the questions which are related to them. So for D block elements, or when we speak about the transition elements, and the general configuration for the transition elements is, so let us write that first thing. General configuration is, how do you write general configuration? We write using the principal quantum number, isn't it? Ns, right? So Ns n minus 1 d. Okay, let us write both. Ns starts from 0 to 2. I'm writing 0 also. I'll show you why it is 0. And your n minus 1 d starts from 1. It ends till, it's going to fill till 10 electrons in the d shell. So now n minus 1, what are these two? Here n minus 1 is called penultimate shell. Penultimate shell, right? And your n minus 1, n minus 0 to 1 is outermost shell, right? Done. Outermost shell. Now what happens is, whenever one electron is adding into any element of the D block elements, the electron will add into the inner penultimate shell, n minus 1 d shell. Because the electron is entering into the n minus 1 d shell, that is inner shell, that means if this is your nucleus and you have this, right? Now I said this is your n minus 1 shell and this is your ns shell. Now whenever electron is entering, it's going to enter into this D shell only. Because it is entering into the D shell, we call it as a D block element. So the electron fills into the D shell, that is the inner or the penultimate shell. That's why we call it as D block elements.
Unacademy introduces the Gogol batch for droppers. That's for JEE Main and Advanced 2021. This batch is starting on 20th November. We have eminent educators like Vikas Gupta, MS Chauhan, Nitin Jain, Mr. Neel Kamal Sethia, Narendra Avasti, Pankaj Joshi and Vimal KR Jashwal. So these top educators are going to train you all. We also have micro class 11th for JEE Main and Advanced 2022. This batch also is starting from November 20th with eminent educators as mentioned. The top educators of the whole country are going to teach you all. So Unacademy proudly announces this batch which is starting from 20th November. Link is given in the description, students. Please go through the link.
Okay, that's simple. Now let us see with an example. Now I said, why did I take n0 to 2? That I have to understand. See, I have marked some anomalies in the configuration. Let us see. Now whenever I speak 0 to 2, let us see what elements have. Now suppose I'm going to pick up a nickel. Right? Nickel, what is the configuration? Right? So nickel, you have configuration. And now I said, this is your D block element, D block, D and D block. So why did I pick up 4 places? Basically the D block is divided into 3D series, 4D series, 5D series and 6D series. Okay, that means the incoming electron here enters into the inner D, that is 3D, hence it is called 3D series. Here it's entering into, just see, it's entering into inner 4D, so it is called 4D series. Here the electron is entering into inner 5D, so I've called it as 5D series. Here into 6D, so I call it as 6D. There's no change in s orbital, just see, s already, it's the outermost shell, the valence shell. Now, so in 3D series, let me see why did I call this as 0 to 1? So now in 3D series, let me pick up nickel as an important thing. So nickel configuration is what? 3D8, 4s2. 3D8, 4s2. Now let us come down exactly to this. Palladium. Palladium configuration, when you see, you have to write first D and then S. S is valence electron, please remember. So you have to write 4D10. So 4D10 and here S, if I see, it is 5s0. Right. Let us come down to platinum. When I pick up platinum, okay, yeah, platinum configuration, if I see, it is 5D9, 6s1. So 5D9, 6s1. So where is N starting? Just see, where is your NS starting? NS is starting from 0. 0 and ending at 2. That's why I've written 2. So this, to show that thing, I picked up an example starting from 0 and ending till 2. And D, as usual, it is D1 to 10. Okay, hope you understood this concept. Remember, in D orbital or D block elements, the electron enters into inner. This is outer shell and this is inner shell. Don't get confused. Inner shell, that's why it is called D block. Now let us start with the questions. With this concept, I think you can easily do all the questions. Let us see the first common question. Now they said zinc, cadmium, mercury are not considered as transition elements. Why? I said zinc. Okay, let us write the configuration. Let us write the answer. For zinc, when we speak about zinc, what is the valency of this, or what is the configuration for this? The configuration for zinc is 3D10, 3D series and 4s2. Done. Next they said cadmium. When I write cadmium, cadmium is here. Again it is 4D10 and 5s2. 4D10, 5s2. Now let us come back and see. They've asked me for mercury. Mercury is coming under 5D series. So 5D10, 6s2. 5D10, 6s2. So what are you finding here? The electron or the D shell is completely filled. Yes, you don't have any DD transitions also. There is no excitation of electrons between the EG set and the T2G set. So no electron change. Okay, I'll explain what is the T2G and EG set also. So most important thing is whenever you say some element is transition elements, important thing, the electron has to enter into the D shell. There should be a transition in the D shell, then only I can call it as D block. Are you finding any electron or nothing? No transition, isn't it? No exchange or no shift of electrons to higher state. So because of the stable configuration, D10 configuration, we don't consider zinc, cadmium and mercury as transition elements. So how should you write the answer? Write this answer and finish it off. Due to stable D10 configuration, DD transitions are not observed. Okay. Let us come back and see the next set of questions based on the electronic configuration. Now I have shifted to a question where I'm going to relate ionization, enthalpy and electronic configuration. So what did we learn? We have in D block elements where the general configuration is Ns and N-1d, right? Right. So where is the electron entering? Every time the electron is entering into the D shell, that's why it is called the D block element. Now they've asked me to relate your ionization enthalpy with electronic configuration. So what is ionization enthalpy? The amount of energy required to remove an electron from the outermost shell. Simple. That means you are going to remove an electron from the Ns subshell and they are asking us to give the reason. Now they said give reason why IE1 for zinc and copper. Why is zinc having more IE1 than copper? Okay, let us see with the configuration. Now they have asked me to compare between zinc and copper. Zinc and copper. Let us write the configuration. So zinc, the configuration belonging to 3D series, 3D10 and 4s2. So 3D10 and 4s2. When I come back to copper, copper is here, the configuration the configuration here is 3D10 4s1. So here it is 3D10 4s1. Now which is fully filled? Yes, yeah, when I compare both, here this is fully filled. First most important thing is it is fully filled. When it is fully filled, isn't it stable? Yes, it is highly stable. When it is highly stable, what will happen to the ionization enthalpy? Obviously, I require a lot of energy to remove the electron from that stable configuration. So, automatically, IE1 is higher for zinc. So, this is the main reason which you have to write. So, once it is fully filled, very difficult for me and I have to apply a lot of energy to pull that electron. Hence, Zn has higher ionization enthalpy than copper. Okay, reasoning is nice. Now, let me come back and give the same in the other way. Now, we are talking about IE2. When do we call something as IE2? When I have already taken out one electron from the valence shell, I call it as IE2. Now, let us take out one electron from copper and one electron from zinc. Again, I'll write the configuration. Now, Zn configuration is 3D10 4s2. Copper configuration is 3d10 4s1. Now they said second ionization enthalpy. Second ionization enthalpy means it should be Zn. If I have to say Zn plus 2, yes. Now, okay, one electron I have to take because only one ionization enthalpy from here till here, isn't it? Zn plus 1 and Cu plus 1. Because only one, after removing one, then you will remove the second one, isn't it? So, one electron. So, when I am removing one electron, from where should I remove? Should I remove from here or here or here? I have to remove from here. So, this becomes 4s1. Now, for copper, one electron I have to remove. This becomes 4s0. Now see, compare the stability between two. This is fully filled. Yes. Now this is completely stable compared to this because there is one half filled electron there. So now you write your reason. This is fully filled, stable configuration. Hence, IE2 is higher. That's it. Simple. How did I reason? I just wrote answer to the question given to me. These three things will completely explain the answer. Don't try to write big stories in the paper. You will not be able to complete the 70 marks paper. Done. So simple. Both the things finished. Now let me explain. Explain why transition elements have most irregularities. Okay. Explain why transition elements have many irregularities in configuration. That is your question. In configuration, why is it so? Now let us see. I have marked so many irregularities. Here irregularity, this one again, this. Why is that irregularity? Okay, let us see the answer. Now, when I have to write the answer for this, first try to write the general configuration. Because they have not asked specifically this particular series, isn't it? So write generally. The general configuration for this is N is 0 to 2, N minus 1, D 1 to 10. Now, what's happening? Why is it showing the difference? Because the energy difference between Ns and Nd is very less. That's why the electron which is entering, it can either enter into Nd or it can enter into Ns also. Means it will enter first into this, then it will come into S also. Means the possibility of entering the electron into Ns and N minus 1 D is easy. Because why is it? Because the difference of energy level, the electron can easily excite to that state. So the difference of energy level is very less in the D block elements. So they show variable electronic configuration. So let us write energy difference between Ns and N minus 1 D, right, is very less. So, the electron can enter into both. Hence, they show variable electronic configuration. Hope you understood. Let us meet again next question. Right, let us come back and do one more question where we are relating ionization enthalpy with electronic configuration. Now, it's almost a similar question. I felt this is also important for you all, so I picked up this question. Why is ionization 1 enthalpy of manganese and chromium? Now, there is a comparison between these two. Okay, in that ionization 1 enthalpy, Mn has greater ionization enthalpy than chromium, it seems, and IE2 for chromium is greater than manganese. So I have to prove that. Okay, let us see. So first, let us write for IE1. Now, so when I speak about IE1, first basically I am going to take out that electron and first write the configuration. So Mn, what is Mn? It is 3d5 and it is 4s2. Okay. Now let us write for chromium. Chromium again is 3d5 and 4s1. So this said the first this one. Why is this more higher? IE1 is higher because this configuration, when I compare this configuration, this is half filled, right? This is half filled. Here also this is half filled, but there is one unpaired electron here. This is paired, so which is more stable compared to both. This is fully or completely stable, and hence IE1 would be higher. because when it is completely stable, it is very difficult for me to pull out that electron. So when I have to speak about IE2 means you're going to take out, now this is done, you have to, now we are going to take out one electron from where, from here, because this is the outermost electron. So this becomes Mn plus 1 and this becomes Cr plus 1. Then when it becomes Mn plus 1 Cr plus 1, this is 3d5 4s1. Now this becomes 3d5 4s0. So now which is more stable compared to this? Here you have an unpaired electron, so easy for me to take out the electron. But here this is half filled and highly stable. So here you're going to write half filled, highly stable, hence IE2 is greater. That's it. You're going to write that reason after taking that electron. Right. So simple. Let us start with this. Why does Mn2, okay, show maximum paramagnetic character among the bivalent ions of the first transition series? So where are we? We are going to study. Now they are asking a question about Mn. Now they said they've already given me the oxidation state, that is Mn plus 2. So let us take that, write that Mn plus 2 and give the reason. Now in Mn plus 2, so Mn, when I write, the configuration is 3d5 and 4s2. So 3d5 and 4s2. What did they ask me? It's showing Mn plus 2, they said. So from where should I remove the electron? This is Mn and Mn plus 2. This becomes 3d5 4s0. So no? Yes. Now when I see the configuration, it is basically 1, 2, 3, 4, 5. Fill all the 5 electrons. 1, 2, 3, 4, 5. So now come back to the question. Why does Mn show maximum paramagnetic behavior? Now what is paramagnetic behavior? When they have unpaired electrons, then we call paramagnetic behavior. Where even if you have one paired electron, we call it as diamagnetic behavior. So when I see, all are unpaired electrons. So this is paramagnetic in nature. Right, let me compare with others. Now when you see this whole series, right, Mn only has, after losing the electrons, it is only by a bivalent atom which has paramagnetic. See, you removing 2 here, this becomes completely paramagnetic. See the others, this is paired, everywhere it is paired. But if I see, manganese only is paramagnetic because of half-filled or D5 configuration. Yes. Right, let us come back and see. Now I'm going to relate, earlier I related ionization enthalpy with electronic configuration. Now I'll be relating the color property with electronic configuration. Let's see how can we learn this. So what did they say? Give reasons. Giving reasons indicate which one of the following would be colored. I have to tell whether the particular ion is colored or not. How do you say something how do you say something is colored or not? Only important thing is there should be an unpaired electron present in that particular element. Then only I can say it is colored, right? So why unpaired electron? When there is an unpaired electron, that electron, when it absorbs certain amount of photons, it will go to the excited state, right? During excited state, it's going to absorb that particular frequency of the color and finally drop down to the ground state. So now most important concept, when a question is asked based on color property, try to write the configuration first, and after writing the configuration, whichever has unpaired electron, that one will be colored, you can say. Simple. So they've given us 3 examples. So let us write, nothing to write, just explain, just write the configuration and write which is colored or not. Now you have Cu plus 1. Plus means just plus 1, scandium plus 3, nickel plus 2. So let us write the configuration and take out the electron. So first for copper plus 1, copper is here. Now it is 3d10. 3d, first write the configuration, 3d10 4s1. They've given me scandium. Scandium is 3d1 4s2. They've given me nickel. So nickel is here, 3d8 4s2. So 3d8, right? 3d8 4s2. Now what should I do? I have to remove electrons. How many should I remove? I have to remove 1. So this becomes 0. I have to remove 3. So this whole thing goes out and this becomes 0. Now I have to remove 2. This whole thing becomes 0. Now after this, try to write the this in configuration for 3d10. Now this is your 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Fully filled. I said unpaired electrons, then only colored. So fully filled, this is colorless. This is colorless, right? Let us write this as colorless. 3d0, right? Now if I write 3d0, is there any thing or any electron to get excited to the state? No, right? So colorless. Now I have to write for this 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8. How many unpaired electrons do we have? 2. Yes, if it has unpaired electron, it's going to show DD transition. After showing DD transition, it will show color. I'll explain what is DD transition in this question. So because of this unpaired electron, this is colored. So observe this question and please write the answer. Yes, let us see why our next question. Why are Zn plus 2 salts white while Ni plus 2 salts are blue? Okay, now they've given us color. I have to explain. What do they say? Zn plus 2 salts white. First we'll see why it is white in color. So when I say Zn plus 2, so what is Zn configuration? Zn configuration is 3d10 4s2. 3d10 4s2. Now take out 2 electrons. This becomes 0. Now this is fully filled. Completely filled, isn't it? This is completely filled in this way. So when this is completely filled, it doesn't show any color. So it is white in color. Simple. Now I have to write for nickel. Nickel is plus 2. What is nickel configuration? Nickel configuration is 3d8 4s2. So write down 3d8 4s2. Now take out 2 electrons from this. This becomes 0. So no, do we have unpaired electrons? Yes, we have unpaired electrons. 1, 2, 3, 4, 5, 6, 7, 8. We have 2 unpaired electrons. Now I'll show what is DD transition from this. Now because of this unpaired electrons, it is blue in color. Right? Now when I speak about D, yes, this whole set is called degenerate set, right? Which has the same energy. Now the first one, it's called dxy, dyz, dzx. Next one, dx square y square, dz square. Now this dxy, yz, zx, this set, this whole set is called a T2G set. Triplet degenerate set. Triplet means 3 degenerate set, and this whole set is called doublet degenerate set. These 2 doublet, these 3 triplet. Okay, fine. So let me erase this and use the board. So what did they say? What did I say? Now I proved nickel is colored in nature. So nickel has plus 2 state. Yes, in this plus 2 state, it has, I said 1, 2, 3. This way, and first 3 are. Now when an electron or when a photon of energy is supplied to this is going to divide or break up into 2 energy levels. One, you have the lower energy level as T2G. This is T2G. T2G with electrons, filled electrons, and the higher one would be EG set with half filled electrons. Right? Now the transition of this particular from the lower to the higher, we call it as DD transition. Now further, when it is supplied, 1 more electron. So this transition, D to D transition, is called, because of this, it's going to show color property. Let us come back and solve this question. Let us, because I'm trying to do different variations in that question. Once I'm trying to compare ionization enthalpy with electronic configuration, color property with electronic configuration, paramagnetic or diamagnetic behavior, that is magnetic behavior with configuration. So let us see how can we relate so that all the questions are complete under this category. Now they've given us which of the following two. Okay, so they've given a different type of question here. They've not mentioned the element, but they've given the atomic number. Among these two, I have to say which is paramagnetic in nature. So as I also said, if it is unpaired electron, then it is paramagnetic nature. If it is paired, it is diamagnetic in nature. Correct? Now I have to write the configuration and show which is paramagnetic. So let us write the answer. Now you have 5 and 4. This is 5 or 4, whatever element they've given. Okay, I don't know whether it is 5, 4 or vanadium. I don't know, but it is this is given. But why did I say 5? Because the element configuration is V. Most of the students may get confused. But this is vanadium, atomic number 23, 21, 22, 23. So V stands for vanadium. Okay, not 5. So vanadium 4 and vanadium 5. So when I write or see the configuration of vanadium, it is 3d3 4s2. So 3d3 4s2. Here again 3d3 4s2. Now what did they say? They said 4. It has lost 4 electrons. The oxidation state is 4. So this becomes 0. This becomes, already 2 have gone. So this becomes 1. Now in this 5, so this becomes 0. This also becomes 0. It has to lose 5 electrons. So now here how many do we have? You have 1 unpaired electron. 1, 2, 3, 4, 5. Yes. 1 unpaired electron. Here it's nothing. No unpaired electrons only. The earlier one, whatever is there, it's completely stable. Yes. So which is paramagnetic now? Yeah. Compared to 2, because of this unpaired electron. Unpaired electron V4 is paramagnetic and this is diamagnetic. Because they've asked me only paramagnetic, I'm writing that answer. Simple. Now let us come back and see this question. So I need this part of the board. I'll erase this part of the board and try to do this question here. Now this is a different way of questioning us. What is this? Of the ions Ag plus. So let us write the ions first. They said Ag plus 1, CO plus 2, Ti plus 4. Now how can I remember the this in configuration? Okay, basically in your CBSE paper, in your actual CBSE paper, CBSE is going to give you the atomic numbers. So seeing the atomic numbers you can write, I believe, use the above principle and try to write the configuration. Now they said which one of the following will be colored in aqueous solution. So what concept should you remember? For an element or for an ion to be colored, it has to show DD transition. For showing the DD transition, it should have unpaired electrons. So whichever is unpaired will be colored. Whichever has unpaired electron will be colored. Point number 1. So let us write that. Whichever has unpaired electron, that particular ion is colored. Simple. Next, if each one of the above ionic species, right, is in turn placed in magnetic field. Okay, they have taken this ionic species and placed in magnetic field. How will they respond and why? Now we very well know when I place in the magnetic field, if it has an unpaired electron only, it's going to get attracted to the magnetic field. So whichever is paramagnetic will respond or get attracted. Whichever is diamagnetic will repel. That's the concept. So let us write the first concept and let us write the second concept. So the second concept is paramagnetic. Same thing, same concept, will attract. Third concept is diamagnetic, will repel. Done. Fine. Here also shall we write paramagnetic? Better. Then you will understand. Para means unpaired. Paramagnetic. So let us see now. They've asked me to write for 3. Now silver. Your silver is here. Silver configuration is 4d10 and 5s1. 4d10 and your 5s1. Done. Next. So next, cobalt. Okay, cobalt they asked me to write. Cobalt is here. 3d7, 4s2. So 3d7 you can write here also, not a problem. But when you're taking out the electrons, it's important. Now Ti. right? Where is our Ti, titanium, vanadium? Here, 3d2, 4s2. So 3d2, 4s2. Now I have to take out one electron. From where will I take out? I'll take out one electron here. This becomes 0. I have to take out 2 electrons. I have to take out 2 electrons from here. This is 0. I have to take out 4 electrons. So when I take out 4 electrons, this is 0. This is 0. Now see which is unpaired. Now this is completely filled. So completely filled. So it is not colored. Here when I write 1, 2, 3, 4, 5, 6, 7, 3 unpaired electrons. 3. Okay, so this will be colored. And this is paramagnetic. Now let us see this. This is completely filled, isn't it? If I take out this, leftover is completely filled. So this is completely filled. So colorless. This is also colorless. Now let us see. So first question did we answer? Out of the following ions Ag, Co and Tl, which is colored? I said so Co plus 2 is colored. That's it. The first question is done. Hope you understood. Once again, they asked me to compare between all the 3. 1, 2, 3. I took all the 3 configuration. I tried to remove one electron from the outermost shell. And then I wrote the configuration. When I saw this is completely filled, diamagnetic. When I saw this is unpaired electrons, so paramagnetic, hence colored. When I took out 4 electrons, it is again diamagnetic, so it is colorless. So I've come to that conclusion. Now I have to see what will happen when they placed in the above. Now we very well know what concept did I say. If it is paramagnetic, it will get attracted. If it is diamagnetic, it will get repelled. Now among all the 3, let me erase this again. I have to use the board for this. Now among all the 3, this concept is first is, hope it is clear. I have to explain the second one. Among all the 3, what is this? 4 is 2, 4 is 0. Okay. Now among all the 3 which has some unpaired electrons, n is equal to 4. So because of this paramagnetic, n is equal to 3, sorry, when it is placed in the magnetic field, immediately they get attracted because of this paramagnetic nature. So same story again. CO plus 2 is, or CO plus 2 and gets attracted in magnetic field. Why? Because of its paramagnetic nature. Why? Because of its paramagnetic nature. This is how you're going to write both the answers. Right, let us come back and see one more question which is related to your electronic configuration. Now I'm going to compare or check the oxidation states using electronic configuration. So what did they give me? They've given me they've given this question: what may be the stable oxidation state of the transition element with the following D configuration? Okay, in the ground state of the atoms. This is basically your NCERT question only. This is there in NCERT question. So I felt if I teach this, it's easy for you to learn the question. So now they've given me among all these, this should be the penultimate shell, and how many oxidation state, to what extent can it show the oxidation state, I have to calculate. As soon as such question is given to you, take that particular data given to you, 3d5, 3d8, 3d4. Okay. Now we very well know in d orbitals we have both ns and n-1d. Already d is given, try to write to s orbital. S is maximum 0 to 2. So just write 4s2, 4s2, 4s2 and 4s2. Now see how many electrons if it gives, it retains stable configuration. You have to have a little clue here. Simple. Now for the first one, here 3 plus 2, if it loses 5 electrons, that is plus 5, the leftover is stable inert gas configuration. So possible state or the stable configuration is plus 5. Done. Let us come back here. You have two possibilities. Here it can lose plus 2 and this becomes half filled and stable. So plus 2. It can also lose 7, plus 7. It can also lose, suppose if I take, okay, now can I see 6 here? Okay, now how many are there? 7. So can I make, let us see if I can write 6 or not. So 3D, now I'm going to take out 2 from here. I'm going to take out, I'm going to drag in, what do you say, this is 2, isn't it? And now how many do I need? I need 4. So I'm going to take out 4. So 1, 2, 3, 4, 5. So when I have to write 6 configurations, suppose, I'll take out 1 electron from here, 1 here, 1 here, 1 here. This 5 possibility, because already 2 I have written. The next possibility I have taken both. And now 1 possibility is I am leaving 1 and the left over 4. So total 4 plus 2, 6. 6 also can be shown. 2, 7, 6. Hope you understood this concept. 2 stable half filled. 7 the leftover is stable. 6 because that's next possibility. 1 electron left. Yes, done. Let me see for this. Here possibility, if I have to see the stable configuration, I can take 2 electrons. Okay, can I take one more electron from here? Suppose if I have to take out, now if I write 2 plus 2, done. If I can write plus 5 or not, let me check. If I have to write plus 5, 2 from here and 3 from here. Yes, now let us write 3D 5. 1, 2, 3, 4, 5, 6, 7, 8. Now what did I say? I'm going to remove 3. 1, 2, 3. It has become stable, isn't it? 3D 5. So the possibility for this is 5. Stable configuration. 2 from here, 3 from here. After removing those 3, it has become half filled. Now let us see for this. 2 done. 4 also I can remove easily because the leftover is stable configuration. So the oxidation state can be 6. This is how you're going to answer the question. Right, now let us do this question. Now here what am I going to do? I'm going to relate, till now I've done all the combinations. Now I've come back to see the stability of the particular ions. Based on the electronic configuration, we're going to see whether it is stable or not. They've given us examples, Mn plus 3, Cr plus 3, vanadium plus 3, Ti plus 3. I have to see based on the number of unpaired electrons. Let us write the configuration for that. For Mn plus 3, Cr plus 3, V plus 3 and Ti plus 3, titanium plus 3. Let us write first for manganese. Now manganese is here 3d5 4s2. So let us write 3d5 4s2. I have not still taken out the electrons. Chromium, when I write, it is again 3d5 4s1. Okay, I have to explain the anomaly also for chromium and copper. Okay, next comes here vanadium. Vanadium is 3d3 4s2. 3d3 4s2. Your titanium 3d2 4s2. 3d2 4s2. Now I have to take out 3 electrons. So this becomes 0 and this becomes 4. Always start from, take out electrons from S because that is the outermost or the valence electron. Now chromium is 3, 0. Now this becomes 4. Vanadium is 3. This becomes 0. This becomes 2. Titanium 3. This becomes 0. This becomes 1. Now write the configuration. 1, 2, 3, 4, 5. 1, 2, 3, 4. Here 3d4. Did we write something wrong? 3d5 4s1. So okay, no, 3d5 4s1. No, this is plus 3, isn't it? This is 4s1. So if it is 4s1, this should be 0 and this is 3d3, isn't it? So we did a mistake here. Okay, 3d3. Now vanadium 2, titanium, right. Now all have unpaired electrons, but which is more stable I have to see? Yes, now see, when I have to see all the things, as I said earlier, this first 3 are called T2G set and the leftover 2 are called EG set. Now if I have to see among all the 4, chromium is the only element which has stable T2G set. Means half filled is more stable than full filled, right? So it has stable T2G set. So here, no, not filled. Here only 1. Here 3 and again unpaired. So based on this configuration, I am trying to explain the half-filled configuration or the half-filled T2G set makes chromium plus 3 most stable in aqueous solution. So write the answer like this. Cr plus 3 has most stable configuration due to T2G or due to half-filled T2G set. That's your answer. Right, so welcome back students. Let us come back and do the next property of your D block elements after electronic configuration, that is your atomic radii. So we will do both the atomic radii and ionic radii also. So here a particular graph, we are going to relate the atomic radii with 3D series, 4D and 5D series. So I picked up 3D here, 4D here and 5D series here. That. Now what happens whenever we are seeing, basically in transition elements, there's a lot of variation in the atomic and ionic radii. So we are seeing that trend, isn't it? So graphically, your NCERT book has given you this data. So I picked up that graph from your NCERT book and trying to explain the different trends in atomic radii. So whenever I go through this graph of atomic radii, just see the 3D series. When I start, we very well know the 3D series starts from scandium and it ends at zinc. 4D starts from yttrium to cadmium and 5D starts at lanthanum and ends at mercury, correct? Now whenever we are seeing the size, as I move from left to right in a period, just observe 164 picometer, 147, 135, 129, 137. So the size is decreasing, isn't it? The size is completely decreasing here. Now this whole gradually from here, okay, we'll do this anomaly also. Now this has become stable till here and now this also, and finally it has increased to 137 picometer. So what did I do? I picked up 3 cases for that. So we'll study under these 3 cases. First important thing is why is the atomic radii decreasing as we move from left to right in the period? Simple. So that is your first question. So what is the first question? When we move from left to right in a period, that means this is your left, this is your right. I'm going towards this side. Atomic radii decreasing. Why? What is the question? So how should I answer this question? Now when I see this particular filling of electrons, now suppose this is your nucleus, right? Now this is your, these are your shells. Now this is your 3D shell, that is your N-1D. This is your 3D shell, penultimate shell, and this is your 4s electron. So now what happens when I move from left to right in the period? Every time the electron, see where is the electron getting added? Here 3D, again 3D, again 3D, 3D, 3D. It's going on adding to the same shell. Every time the electron adds to this, every time the electron adds to this shell only, 3D shell. So when it is trying to add electrons to the 3D shell, so what is happening to the nucleus? Automatically your protons also will be added. So the proton and your electron both start increasing here. So first important thing you have to remember, first concept, yes, as I move from left to right in the period, atomic number increases, number of protons and number of electrons increases. When this is increasing, what is observed now? The nuclear charge on this, that very important. So the nuclear charge, okay, I'll write N dot E, nuclear charge increases. Because very closer to the, this is 4 compared to 4s, 3D is closer, so it's trying to drag the electrons towards it, because protons and neutrons, protons and electrons, they get attracted to each other, so nuclear charge increases. When the nuclear charge increases, what happens to the size? Atomic radii decreases. Simple. This is dragging from this side and both are, this is trying to pull that electron, so that the size or the atomic radii becomes very small. Simple. Now and this atomic radii decreases. Now what is one more factor you have to speak? Because the 3D electron, now what happens, your 3D or that electron which is getting added here, the screening effect of 3D electron is very less. Why? Because of its size, isn't it? The diffuse size of 3D is very, it is compact, isn't it? So that concept, that is your screening effect, or this 3D because of diffuse size will not protect this forest. Directly the electron, the proton in the nucleus tries to drag the whole forest electron towards it. Why? Because the screening effect of D is less. Simple. I have written 2 points. First, as I move from left to right, atomic number increases. Understood. When atomic number increases, protons as well as electrons both increase. Okay, let us erase all this so that you don't get confused. Now, this is your 3D, I said, right? This is your proton and this is your electron. This also is your electron. So, number of protons and number of electrons increases. The number of proton, number of electron increases. This try to drag this electron and drag this electron also. So nuclear charge increases. When nuclear charge increases, atomic radius decreases. Simple. Why is this all happening? Because the screening effect of D electron is very, very less. Because of its size, when I see the shape of the D orbital, the size is diffused. So D electron is less. You complete that answer. Done. Now I'm done with this part of the graph. Now I'll come back to this part of the graph. Now I said, why is the atomic radii of iron is here, cobalt and nickel? Yes, similar. Why is it similar? See here, it is 126 picometer, 125 picometer, 125 picometer, and almost 128 picometer, very close. Why is it? What is happening? Now let us answer the middle series. Now I'll write it as midway. Midway means this part of the curve. So here what happens is, I said both the effects. Now screening effect and nuclear charge, I'm going to speak in terms of this. When I go to the middle of the series, your electron, again it's going on adding and adding and adding. Yes. Now the number of electrons or the D electrons becomes, they go on increasing, isn't it? Yes. Now at that particular point in the middle of the series, number of electrons in D shell increases, correct? It increases. That's what is told. Now, at this particular point, when the number of electrons as well as the nuclear charge, because both keep acting on that particular electron. So, at the middle of the series, though the number of electrons are increasing, the nuclear charge also acts, the electron also acts. So, a situation comes where the nuclear charge as well as the screening effect, or nuclear charge and the number of D electrons both start counterbalancing each other. Because the atomic number is increasing, number of electron increases, right? So at the middle of the series, 2 important concepts. One is nuclear charge as well as screening effect of D, they counterbalance. Both balance each other. So they become equal almost, counterbalance. Nuclear charge and screening effect counterbalance. So because of this, the size remains the same. Though the electrons are adding, both compensate each other and they become equal. So I clearly answered this question. Number of electron increases in D shell as atomic number increases. And the most important thing is this middle series. Done. Now again I'm going to speak in terms of nuclear charge and Se. Now as I come above, when I am reaching zinc, why does atomic radii increase at the end of the series? Now zinc, it is 137 picometer. So why is it increasing? So again I'll speak in that terms only. When I come back to zinc, for example, in zinc, what is the atomic configuration? It is 3D10 4s2, isn't it? So zinc 3D10 4s2. Now what is happening here? What is dominating? When I see the electron ball going on adding and adding and adding to the same shell. So the number of electrons starts increasing so much that you're adding 3D1, 3D2, 3D3, 3D5, 3D6, 7, 8, 9, 10. You're going on adding to the same 3D shell. Very important here when it comes to zinc, electron repulsion starts. Because you're adding to the same shell every time, isn't it? 3D only, you're going on adding to 3D, isn't it? So now electron repulsion starts, which becomes greater than your nuclear charge. So nuclear charge also is trying to pull the electron, but electron repulsion will dominate now. Here what happened? Nuclear charge was dominating. Here what happened? Both were balanced. Here what happened? Electron repulsion start increasing. So because of this electron repulsion, that thing, and I said nuclear charge is decreasing automatically. When that repulsion is there, the size automatically increases, isn't it? Right? So that is why electron repulsion greater than nuclear charge. So the concept ended. Size increases. Yes, because of repulsions. Automatically, when something is repelling, it will open up, isn't it? It will just, the distance between them increases. So, this is your concept. I am trying to explain only 3 important things using this graph. Again, we will do with this series and this series also. Most important thing you have to remember in the exam is first series, this one. Nuclear charge is dominating screening effect. In the midway, in the second series, second part of this, nuclear charge counterbalance screening effect. In the last series or the last part, electron repulsion dominates nuclear charge or nuclear charge NC. That's it. Right. So let us come back and do the atomic radii trend in the 4D and 5D series. So what did we learn in 3D series? First, scandium had the highest. Then gradually, when I went into the midway of that particular series, it was almost equal. Then gradually, when we went into the end of the series, that is for your zinc, the atomic radii increased. So I have already clearly given you the reason for that. Watch that video clearly, and then let us come back and do the next part. Now, when you have seen that graph, we also have observed, now for 3D, as I said, for 3D it was like this. Now immediately 4D, as we go down, as we know, as we go down the group, the atomic number increases, so number of shells increases, so atomic radii also has to increase. So this is your 3D, this is your 4D. Now when I have to say 5D has to be more, isn't it? For 5D series, it has to be higher than this. But what was observed is the 5D series was also almost equal to your 4D series. So we are going to learn that reason now. So how is this question given? Why are atomic radii of second and third transition series similar? Why? Okay, they are talking about second transition series means 4D series, and 5D series, why are they almost equal? They want us to reason. Let us see. Now we very well know when I have to move, right, in a period, if I have speak in a period just like this, in this way, what are you observing? 184 picometer, 176, 171. So because of the increased nuclear charge from left to right, the atomic radii decreases. That is what you are observing. Fine. But now when I go into a group, that is from top to bottom, let us see, 184 picometer, 212, 240. Okay, this is increasing. Done. Let us come back to the next. In titanium 176, zirconium 206 and hafnium 208. Now what are you observing? The atomic radii of titanium. Okay, first we'll start with titanium. The radii of titanium, right? When I say it is less than the radius of zirconium, but radius of zirconium is almost equal to radius of hafnium. This is what we have to answer. What is the reason? Now, when I have to write the reason, I'll clearly, or I have to start with the configuration. So, what is the atomic number of zirconium? 40. So, let us write for zirconium, it is 40. So, what are you finding? What is the configuration? It is, if I have to write the outer configuration, it is 4s2, okay, 4d2, right? Okay, 4d2 and 5s2, outer configuration. And next, hafnium is 72, right? If I have to write the configuration, this is 4D, so this will be 5D2, this is 5S, so this is 6S2. But apart from that, you also have a 14. Now this is where your reason lies. Be very careful in answering. Once you write this configuration, your concept or explanation of the concept starts from here. Now, because of this F orbital, we very well know F has, what are the characteristics of S? F has double dumbbell shape. So the structure of F, so let us write, it is double dumbbell shaped. right? When it is double dumbbell shaped, how is this looking? The electrons are completely diffused, isn't it? They're very farly placed. One electron here, this is your suppose nucleus. One electron here, one electron here, one electron here, one electron here. They're highly diffused in nature. So the important thing, they are highly diffused. Okay, because of this highly diffused, or because of this nature, what will happen? Will they shield these two electrons from the nucleus? No, isn't it? Because already because of the shape, they can't diffuse, they can't screen the or shield these two electrons. So what will happen to their effect? They have pore shielding effect. Shielding effect. Now, because of this pore shielding effect, what will happen to the atomic radii or nuclear charge? The nucleus which is here, it tries to pull this d electron and s electron very closer because of this pore shielding. So automatically the atomic radii decreases. Atomic radii decreases. So which pore shielding? Pore shielding of 4f electrons. Now, this concept of pore shielding of 4f electron is called a lanthanoid contraction. So, this is your main concept, lanthanoid contraction. Lanthanoid contraction. So, because of this lanthanoid contraction, zirconium and hafnium. See, zirconium and hafnium, this radii or the decrease in the atomic radii is clearly observed. So when examiner asks you this question, you can write in one word. First important thing, write this concept and immediately write lanthanoid contraction. You have to explain the lanthanoid contraction. The question is given for 2 marks, right? Then start explaining, write the configuration and show this is 4f, right? Then immediately say that is double dumbbell or diffuse shape. Diffuse shape means it is unevenly spread. When it is unevenly spread, the nucleus here tries to drag this one and also drags the outermost s electron. Then automatically the atomic radii reduces, which is called lanthanoid contraction. So one more reason what I can write is, fine, let us write, this is first reason. Now let us write the second reason. In your second reason, the same thing. I have to justify why are these two equal. Now, I spoke the first concept based on nuclear attraction. Now, second one also I'll speak in terms of nuclear attraction. Okay, nuclear attraction and pore shielding. Second reason also, I'll be writing in terms of this only. Just see, when I speak about titanium, atomic number is 22. When I speak about zirconium, atomic number is 40. When I speak about hafnium, atomic number is 72. Now, from here till here, how many units of charge, or positive charge has increased, or the nuclear charge has increased? This one, 18, isn't it? Now, from 40 to 72, 32 units. Now, what happened as we go down, the number of positive charge, the units of positive charge is increasing. Where is that unit of positive charge present? That is in the nucleus, isn't it? That means the nuclear force is not, isn't it increasing? It is increasing. So, you can write from zirconium to hafnium, increase in nuclear charge is by 32 units. So simple. Compare the atomic radii, compare the atomic number or number of protons added to that. So we have seen the atomic radii trends, that is we have studied in 3D concept, 3D series. We also learned for 4D and 5D based on lanthanoid contraction. So those are the keywords which you have to remember. Please read the trends carefully. Now let us come back and do the ionic radii trends. When I have to see the ionic radii, just observe carefully here. This is your formation of M+2 ion and this is your formation of M+3 ion, right? So scandium, as we know, that cannot form, and so I've started with this. So when I'm taken the ionic radii of M+3 cation, the picometer, as I move from left to right, just observe the ionic radii when I move from left to right is decreasing. So let us see this. When I move from left to right, M+2 cation, 90, 88, this also is decreasing. Yes, just see. Decreasing, increasing. Now this is fully filled, completely filled, so that doesn't participate, not a problem. But here, as you see this, now in a period from left to right, as we've seen, ionic radii decreases. What is the reason? As we know, as the size decreases, the nuclear force of, or as we move from left to right, the electron adds to the same in the penultimate shell. That is a penultimate shell n-1d, right? When you're trying to take out one electron while forming the charge, you're trying to take out one electron, what will happen to the nuclear charge on that electron? So whenever, as and when you're trying to take out one electron, now this is your nucleus, this is your n-1d, and this is your 4s, right? Now every time you're trying to add one electron here, yes, done. So when you're trying to take out one electron, suppose you're trying to take one electron, then you'll separate from here, okay, one gone, s electron, then that will be m plus. Then again second electron, this is also lost. For the third electron, you'll start removing from here, isn't it? Now this becomes m plus 3. When you're trying to remove one electron, the effective nuclear charge on this particular thing becomes more, because this electron is lost. The leftover electrons, they experience a lot of nuclear attraction. Yes, that is the reason your ionic radii decreases from left to right. So what reason will I write? Increased nuclear charge. This increased nuclear charge will reduce the ionic radii. So as I said, once again, first when you're trying to remove an electron, you'll remove one from here. Second electron, you'll remove from 4s. Third, when it comes, you have to come back to 3d and remove, isn't it? So when you're trying to remove, number of electron decreases and nuclear charge on them increases. So that is the reason this decreases from left to right. Right. So let us come back after your atomic radii and ionic radii. We'll come back to the next trend of your D block element, that is your melting point and boiling point. So we'll also learn what is here atomization, concept of atomization also in this now. So as we have seen in atomic radii and ionic radii, we have a lot of variations in the graph. 3D series also there's variations or trends. We've also learned about 4D and 5D concept of Lanthanoid contraction. Now in melting point also, when I observe the graph, there's a lot of variation in the graph of graph shown by transition elements. So let us see the questions based on this. So one important concept, whenever they're asking you about melting point or boiling point, whether it is high or low, what key point should I remember to answer those questions? First we'll discuss that and come back to these questions. Now that particular concept I'll explain in this term. Suppose if they ask you in transition metal elements, melting point first increases and shows a dip, and then in the middle, and then decreases. First it is increasing, then it is decreasing, then again it is decreasing. What is the reason? First most important thing, your answer should start like this. So in transition elements, what is the general configuration? And you have the configuration of Ns 0 to 2, n-1, d 1 to 10. So now what happens, as I said, the energy difference between Ns and Nd, that is n-1d, the energy difference is very less. So both of these, they try to undergo interatomic attraction and finally form a strong metallic bonding. First most important thing. What did I say now? Let us write first. I said energy difference is very less. Okay, when it is very less, what will happen? They'll undergo strong interatomic attractions. Okay, strong interatomic attractions, then finally what does it lead into? It leads into stronger metallic bond. Okay, all these are metals, isn't it? Metallic bond. This is also fine. Now what happens when the metallic bond is stronger? Automatically I have to supply excess amount of energy or melting point to melt that particular thing, right? I have to use an amount of energy more than required because the bond formed is very strong. So hence the MP increases. This is the reason. Now next important concept which you have to remember when you answer such questions, right? So this is one concept. The second concept would be, if the number of electrons or the number of unpaired electrons are more, the melting point would be high. Remember this concept. What did I say? Number of unpaired electrons. The number of unpaired electrons are more, so MP will be more. Yes, let me give another statement. So where will I write this? Okay, I think I can erase this part of the board. Okay. So the next key point which I have to remember, this is my first key point, the second key point, third key point. Third key point in melting point is if the number of bond pairs, that means if it is completely filled, if it is stable, okay, or number of, well, otherwise we'll write if it has stable configuration, then melting point decreases. Why? You don't find the d electron participating in the reaction, isn't it? So it is completely bond 3d10 configuration or d5 configuration, you'll have low melting point. So remember that. Unpaired electrons more, high melting point. No unpaired electrons, that is, it is completely stable, low melting point. So let us come back with that. So remember this concept and this concept. Now they've asked me in this form. What is the form? Why does iron have higher melting point than copper? So come back to iron. Now when I take, now this is your iron, this is here. They've asked you copper. Copper is here. This is your copper. Let us write the configuration. Fe configuration is 3d6 4s2. Now copper configuration, it is 3d10 4s1. Yes, done. Now I said number of electrons or more, higher is the melting point. So compare these two. This is how many? D is d6, isn't it? So 1, 2, 3. 1, 2, 3, 4, 5, 6. How many unpaired electrons do you have? N is 4. Here in copper, all are filled, isn't it? Stable configuration. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. N is equal to 0 here. So the same concept I'm applying here. Number of unpaired electrons or more, melting point would be more. So this is the reason melting point of iron is more than copper. Simple. So write this number of, okay, we will not write like that. We'll write iron has N is equal to 4 unpaired electrons. So MP is higher. Simple concept. Done. Let us come back to next question. Why do zinc, cadmium, mercury have low melting point? So where do zinc, cadmium, mercury lie? They lie at the extreme end, isn't it? After copper you have zinc, after gold you have mercury, after cadmium, after silver you have cadmium. So they are asking us, why do they have low melting point? Simple concept. When do I say it is low? Without configuration also you can write. You can just write zinc, cadmium and mercury have completely filled shells, completely filled, stable configuration. When it is stable configuration, see this concept. Melting point decreases. That's it. So you have to remember this and remember this. Now let us answer this question and see. Maybe this is also similar but a bit different way of answering. And they've given me one more set. Earlier what did they give us? They've given us this comparison. Then they've given us your iron and copper comparison. Now we are concentrating more on these peaks. These peaks I did. Now I'm concentrating on these peaks. Just see. But they ask us why chromium. Okay, chromium is here. Molybdenum, right? Tungsten, right? And why are these, right? So these three elements, why do they have the maximum peaks in the melting point trends, they asked us. So why do they have highest? What did I say? Basically, whenever they're asking about the melting point, you have to concentrate only on the number of unpaired electrons. More the number of unpaired electrons, higher is the melting point. Point number 1. Less the number of unpaired electrons or stable configuration, lower would be the melting point. And let us write. Now for chromium, when I have written, okay, chromium, it belongs to 3D series, your molybdenum belongs to 4D and tungsten belongs to 5D, right? So when I speak in 3D series, just observe 3D5, 4s1, 4D5, 4s1, 5D4, 6s2. And this one RE is 5D5, 6s2. So what are you observing? Why do they have highest peak in the melting point? Now, see the number of unpaired electrons, half filled. But here you have one unpaired electron. Here also half filled, one unpaired electron. Here 4 unpaired electrons, isn't it? Now see here 4, 3D, 1, 2, 3, 4, 4 unpaired electrons here. Now when you observe here, half filled, and this is 6s2 filled completely. Now when I have to see chromium, because of the presence of unpaired electron, it is highest. And on the top of that, this is half filled, okay. But this and presence of unpaired makes the melting point of chromium higher. More than that, if I see, this is higher. More than that, tungsten, these compared to these two, this is having more number of unpaired electrons, so this is a bit more higher than that. So let us come back and see. We're going to write chromium number of unpaired electron, this, yeah, and if I have to see 3d 5, okay, here only I can write, isn't it? Yeah, number of unpaired electrons of 5 and 1 6. Okay, this is stable, but I'm counting as half filled. And molybdenum, if I say 4d5 4s1, if I have to say tungsten 5d4 6s2, if I have to see Re, it is 5d5 6s2. So everywhere you have number of unpaired electrons, so you can generalize and write as number of unpaired electron increases, MP increases. That's it. Now, they've given me one more question in terms of density. They said chromium, yeah, where is chromium? Chromium is here. Where the other one, iron. Okay, now they're comparing between these two. Chromium and iron, they've given us the density. Chromium has 7.19 and iron has 7.8. So, which has higher melting point? You don't know anything about the configuration, nothing else. You want to speak in terms of density. So, we very well know density is equal to mass by volume. Now, for chromium, the this one as atomic number, double of that. So, the mass would be when I compare chromium mass and iron mass, which will have more mass, iron will have higher mass. When the mass is more, obviously the density will be more. Yes, so first concept based on density, the mass of iron, your mass of Fe is greater than mass of copper, sorry, mass of chromium. When the mass of chromium, mass of iron is more than chromium, what will happen to that melting point or this one? Let's see. Yeah, the chromium and iron, when I see, obviously the density will be higher. Okay, I spoke in terms of density. This is one concept. The next concept where I'm going to speak in terms of configurations also. In chromium, it is 3d5. In chromium, it is 3d5 4s1. When I speak about iron, you have 3d6 4s1 4s2. Yes, now if I have to compare between this and this, how many unpaired electrons do we have here? You have 1 2 3 4 5 and 6. Now see how many unpaired electrons? 1 2 3 4. N is equal to 4. 4 unpaired electrons. Yes or no? Yes. Now when I have to see this is completely half filled. It is stable. Okay. Yes. Now this is completely half filled, but it is highly stable. Yeah. Now there is one valence electron existing here. So I will write N is equal to 1. When I have to compare both of these, yes, when I have to compare both of this, chromium has half filled and stable configuration, right? So both the concepts are acting on this. So it has higher MP compared to Fe. But here what is happening? You have only unpaired electron, but the stability factor also counts here. There's no stability factor counting here. So chromium is in the peak compared to iron. Right, so let us do one more question on the melting point and boiling point concept. So what did I say? If when is the melting point, boiling point high? Whenever there is number of unpaired electrons more or the number of valence electrons more. So they're asking if this question is asked. No example given. Generally they've asked you. MP and BP of transition elements are generally high due to. Okay. First, write it in 3 ways. Okay, 3 just arrows or bullets. First important thing. Involvement of N-1d and Ns electrons. First thing. Because of this involvement, what is formed? Interatomic interactions. Now, this interatomic interactions, because of this, what has formed? Metallic bonding. Because of this metallic bonding, what happened? MP and BP increases. These are the reasons. Simple. So let us come back and see this question. The maximum and minimum MP of first and the second pre-series elements are observed with. Okay, I felt this MCQ is a bit tricky and very nice, interesting thing. I found it in one of the competitive books, so I felt this will be useful for you as a practice this question. Let's see. I have to find in these sets. This set is given to me. This set is given to me. This is one set. This is one set. They said the maximum and minimum. Remember this. First should be maximum, then should be minimum, or the first and the second transition series. Now, are these two first and second transition series? Yes. These two first and second transition series? Yes. This one? No. Mercury comes under 3D series, isn't it? So, I should not consider during the answer irrelevant because this is that. Next, MO and CD? Yes. Now, my answer is not that. I very well know the melting point would be maximum when it has half-filled electrons or valence electrons. This is my concept, isn't it? Half filled. Now compare, this is stable, okay, fine. But if I compare this one and this one, which has half filled electrons, this, when this I ruled out. Now compare between this and this. Half filled, but unpaired electrons. Perfect. Unpaired electrons. This can participate in metal-metal interactions or interatomic attractions. So this is my answer. Answer is this. Why? You can write due to presence of unpaired electrons. That's it. Same concept I'm explaining every time. Unpaired electrons will make the melting point, boiling point, atomization higher. Right. So after your melting point and boiling point, the trends which we have seen, let us come back and do this concept, that is enthalpy of atomization. So what actually is enthalpy of atomization? So let's take one example and then do this question. Now suppose I have chlorine, right? Yes, here the physical state, chlorine gas. Now this is going to, suppose if I take half mole of this, I'm going to get chlorine at 1 mole. And the amount of enthalpy or the enthalpy change here, okay, let me first write, is equal to plus 122 kilojoules per mole. Okay. Now what is enthalpy of atomization? Just see. The enthalpy of atomization is the amount of heat. Just see, it is the amount or the enthalpy change. This is your change when 1 mole of the gaseous atom is obtained from its elements which are in their own physical state, means according to that particular thing, which are in their physical state at standard conditions. Once again, enthalpy of atomization is the heat change, the enthalpy change when 1 mole of the gaseous atom is obtained from its elements, yes, in their physical state at standard conditions of temperature and pressure. Done. Now, why are we taking this? We have studied already melting point. I said, what did I say? Higher the number of valence electrons, that is the number of unpaired electrons, stronger is the metallic bond formed. If the metallic bond is stronger, the melting point also would be stronger, higher. In the same way, more the number of valence electrons, stronger would be the metallic bond, then higher would be the enthalpies of atomization, because I have to break the bond, then only form the individual atoms. So they said transition elements, when I see the series, 3D series, 4D and 5D, there's a lot of variations in that particular thing. So whenever I'm seeing this graph, what are you observing here? These are the low, the least scandium, all these scandium element here. Here when I come back here, you have zinc completely filled. In between you have the peaks of chromium. Yes, we have seen in the last graph. You have also seen iron here. So what are we finding in them? They have number of valence electrons or unpaired electrons, correct? Iron also. So reason I can start writing like this. First important thing, number of valence electrons. I'm talking about these peaks. These peaks, right? Number of valence electron is more. Stronger is metallic bond. Okay. When the metallic bond is stronger, higher would be, I have to apply a lot of enthalpy atomization. I have to break it into atoms, individual atoms. Higher would be delta H naught A. Standard enthalpy of atomization. Higher would be standard enthalpy of atomization. So what is that reason now? In transition elements, the middle series, the midway series all have unpaired electrons, correct? So this unpaired electrons is making them or showing the trends in their enthalpies of atomization. So you can write the middle series of elements have more unpaired electrons, hence have higher delta H naught A. That is your answer. Right. So let us come back and do the next question based on enthalpies of atomization. So now what is the concept you have to remember? Number of unpaired electrons or the number of valence electrons are more would be the metallic bonding. If the metallic bonding is stronger, I have to use more of the melting temperature or more of the enthalpy of atomization temperature, right? Or the heat change. Now the same concept I'm going to apply in these two equations and see whether it works out or not. They've given me why do the metals of second and the third transition series. Now this is your 3D series, 4D and 5D series. Now as we've seen in the graph, there's a lot of variation compared to 3D. So why is the reason they asked? What should you write if they ask you for 1 mark? Only important concept is just finish off your answer writing in this way. The whole concept is explained here. In 3D, or if I have to say in 4D, that is your second series, and 5D series, what is increasing? Metal bonding is increasing, isn't it? Metal bonding is increasing. When the metal bonding is increasing, automatically delta H naught A also increases, isn't it? That's it. Just you can write hence delta H naught A increases. Simple. Your answer is done. This concept linked. Let us come back and see. In the series, scandium 21 and zinc 30, enthalpy EOA I have not written completely. Enthalpy of atomization is lowest for zinc. Okay, they've given the value for zinc, that is 126 kilojoules. That means 126 kilojoules per mole is used to convert or form 1 mole of zinc gaseous atom from its particular element. Why they're asking? Again, I'm coming back to the same concept. When I speak about scandium, let us write the answer. I speak about scandium 21. For zinc, it is your 30. So where is scandium lying? Scandium is lying here and your zinc is lying here. The atomic number is 21 here, zinc is 30 here. When I have to see the this in configuration, scandium belongs to 3D series, zinc also belongs to 3D series. Scandium configuration is 3D 1,4s2. Zinc configuration is 3D 10, 4s2. Now compared to both, which has unpaired electron? Yes, this is only in scandium it has 1 unpaired electron. In zinc, completely filled. Now same concept, come back. Number of unpaired electron or number of unpaired electron or valence electron increases. Delta HA or standard enthalpy also increases. But in case of zinc, what happened? Zinc is low, they said. Zinc has stable configuration. It has stable configuration. Automatically, it is not going to participate or not going to form interatomic attraction or that metallic bond. Yes. So, when it has stable configuration, metal bonding not observed. Metal bonding not observed. When metal bonding is not observed, I very well know EOA is least. Simple. This is my reasoning. This is how you have to reason in the exam. Please observe carefully. Any doubts, please let me know. Yes, students. So welcome back to one more session of your D block chapter. So I already started the D block chapter explaining you the different trends based on the electronic configuration. After we have learned electronic configuration, we have come to a concept called how to learn the different trends in atomic and ionic radii. Okay, please go through the videos carefully and keep noting it on daily basis. After atomic and ionic radii, we've also dealt the concept of enthalpy of atomization, which I've explained in terms of how much, what is the amount of energy required or amount of delta H naught A formed when 1 mole of gaseous atom is obtained from its respective elements. Now I'll be dealing with ionization enthalpy and related questions with this, right? So whenever we speak about ionization enthalpy, we've already studied in grade 11th. What is ionization enthalpy? Basically, the amount of energy required to remove an electron from the valence shell. We've been studying the same since I think 9th class, isn't it? So I am going to supply certain amount of energy. So with that energy, whichever the electron which is present in the outermost shell, we are going to pull that out. Once this is done, then we're going into the inner shell. Now for us, the concept is, how are we going to explain the ionization enthalpy values in your 3D series, 4D and 5D? There are many questions asked based on 3D, 4D and 5D series. First we'll complete off 3D series and come back to your 4D and 5D series. So whenever we speak about 3D series, so I have a tabular column which is given in your NCERT. I've just noted down here, and let us start. Now, how is this question asked in the exam? Suppose they'll not ask you what is ionization enthalpy, nothing of that sort. Suppose if they ask you a question like this. Now basically this is your NCERT question. Let us see how to answer this question. So how would you account for the irregular variation of ionization enthalpy in the first series? Okay. Now as I said, now if this is an atom, the outermost electron, I have to supply certain energy and pull out that electron. Next into the n-1 shell. The same concept. When I go with the 3D series, we very well know D block elements are when we study 3D series, 4D, 5D and 6D. Now these are trends for your 3D series where you have ionization enthalpy 1, first ionization enthalpy, second and third. Let us see the anomalies, the trends in this particular thing. Now I said, how do you account? Means I have to explain in simple words. Now you have to, first important thing you have to write is ionization enthalpy. What does it depend on? Ionization enthalpy depends on nuclear charge. Okay. Right, this is the most important concept. So nuclear charge, higher the nuclear charge, more is the ionization enthalpy. I have to apply extra energy to pull out that electron. Yes, isn't it? Now, how is this changing when I'm moving from left to right in the period? Now, this is your 3D series, as I said. Now, see how is the ionization enthalpy? Is it increasing or decreasing? Less, increasing, increasing, it is increasing. So, when I move from left to right in the period, left to right in a period, what is happening to ionization enthalpy? IE values are increasing. Why is it increasing? As we know, as I move from left to right, the atomic size decreases. Simple logic. So why does it decrease? Why does it increase? As atomic size decreases. Why is atomic size decreasing? Because we very well know, I already told in the first video, this electron enters into the same penultimate shell, n-1 d shell only. Yes, it keeps on d1, d2, d3, d4 like that. It goes on, adds till it ends with 3d10. Correct? So what should I write? Since electrons get or electrons add to the same penultimate shell. Okay, this is your basic information, penultimate shell. Now after writing that, they want to explain us the whole trend, isn't it? Now this information gives them the basic thing. This is done. Now after writing that, now start with the table. Now we have to see, when I have marked the anomaly with red, so it's easy for me. In chromium, when I have to see chromium first ionization enthalpy and chromium second ionization enthalpy, observe carefully. Chromium basically first ionization enthalpy is already high. So what happens? What is the reason? So once you finish off this basic thing, erase that. Okay, I'm erasing this part and let us start with chromium. Now when I take a chromium, the configuration of chromium is 3d5 4s1. So this is 3d5 4s1. Now the first ionization enthalpy is 653 kilojoules per mole. Okay, so first IE1 is 653 kilojoules per mole. Now when I have to take out, one electron from this. Yes or no? You are going to take this electron out from here. This is the outermost shell. Done. So once this is done, first ionization enthalpy, this becomes 0. Now I'm going to what should I do now? This becomes a Cr plus 1. Now after taking out, I have to apply again energy IE2, that is how much? 1592 kilojoules per mole, double. Why? Why is it so much? Because I have to remove electron from the half-filled d orbital. That is very important. This half-filled is highly stable. Half-filled, it is highly stable. So that is the reason IE2 of chromium is very higher than IE1 of chromium. So please understand the concept. IE1 is higher. Okay, then double, it has become double because when I apply the second energy, I have to remove electron from the 3d5 configuration, which is half-filled, and it is highly stable. That is the first anomaly. Now I'm going to explain the concept here with zinc. Right, now let us erase this chromium and write for zinc. Now zinc, the same concept. What am I writing for zinc? The atomic number 30 and it is 3d10, 4s2. Now I have to take out one electron. Now I have to apply first ionization enthalpy. How much is it? It is 906 kilojoules per mole. Now I have to take out one electron. Suppose if I am taking first one electron, Zn plus 1. So this becomes 4s1. Yes, then again you have to take out one more electron, Zn plus 2. This becomes 0. Second. Now again come back, I have to make, now I suppose if I have to take out one more electron from here. Just see, it is 3829 kilojoules per mole I require. Why? Because 3d10 value is, I have to apply IE2 because okay, how much is this? 1734 kilojoules per mole. Now how much? I have to remove extra electron from where? I have to remove it from an fully stable or completely filled configuration, completely filled configuration, that is D configuration. So when it is highly stable, automatically the ionization enthalpy will become maximum. So I started explaining from left to right. I explained in terms of chromium because that is showing this one, it has half filled. I explained in terms of zinc because it is fully filled. So you can generalize the answer and write in this way, right? Now, let us erase this and come back to this question. I did this, I gave the basic information. Now let me do this question. What does this question say? Why is ionization enthalpy smooth and sharp is not smooth and as sharp in S and P block elements? Okay, now what are they doing? Here they've given me generally. Now they're comparing with the S block elements and P block elements. Now what happens when we study D block? The first important concept is this ionization enthalpy, as I said, it depends upon nuclear charge. Nuclear charge indirectly depends upon atomic radii. Correct? Now, when I have to see along the group, along the period and along the group, yes, important, I have to compare between S block, P block and D block. Now, what is happening in D block elements? Here your effect of lanthanoid contraction is acting, isn't it? You're not finding that lanthanoid contraction in S and P block. So, because of this lanthanoid contraction, first important thing, this lanthanoid contraction is causing or it is making, or because of this lanthanoid contraction, what do we say? The size is going to decrease, the atomic radii decreases. When the atomic radii decreases, I have to apply extra energy or the ionization enthalpy will vary, isn't it? Ups and downs, yes. So first important thing, lanthanoid contraction, because of this atomic radii decreases. When atomic radii decreases, nuclear charge increases. When nuclear charge increases, ionization enthalpy increases. So this is one concept of D which is varying from S and P. The next important. Now what if we see, we have seen this is in a group, right? We have seen it in the group. When I speak about this one in a period. Now as I said, the configuration, D5 configuration and D10 stable configuration, isn't it? Are you finding that in your S block and P block? No. So this D5 and D10 configuration, because we can also write effect of stability, that is D5 and D10 configuration. Effect of stability, that is D5 and D10 configuration, both also affect ionization enthalpy which is higher. So I can generalize D block giving these two concepts along a period and along a group. Right, so let us do one more question. I think all the questions will be similar only, but only thing for me doing so many questions is by the end of I complete the topic, the concept would be clear. It's easy for you to apply the concept in the exam, right? So let us see this question. Why are second ionization enthalpies of chromium and copper higher? So both these questions are similar, but only thing is the elements are different, right? Now they say the second ionization enthalpy for chromium and copper. Okay, chromium second ionization enthalpy, yes, 1592 higher when I compare to all these things, and copper it is 1958 higher when I compare to these two. That is one anomaly, isn't it? So they're asking us why is this higher. So second ionization enthalpy they said. So what is this chromium? Now chromium, the configuration for chromium is 3d5 4s1. Okay, now for your copper, the configuration is again 3d10 4s1. Now what happened? They asked me for second ionization. So when I am applying the first ionization enthalpy, so I am going to remove this electron. This becomes 0. This also becomes 0. Now this is your first IE1 and IE1. Now when I have to apply the second ionization enthalpy, observe I have to apply or I have to remove this electron. Now second ionization enthalpy when I am to remove, this is half filled, and this half filled and this full filled configuration is most highly stable. When it is highly stable, automatically the ionization enthalpy values will become more, isn't it? So that is the concept. So just simple, how should you write this answer? Your second ionization enthalpy IE2, that is for your chromium you will get 3d5 configuration, for copper you will get 3d10 configuration. So more highly stable, hence IE values are greater. This is the same concept here also. Now they've asked me third ionization enthalpy for manganese or zinc. Okay, so for manganese third ionization enthalpy, when I compare all these are in 2000 value kilojoules, this is only 3000. Okay, now again 2000, now okay 3000 increasing. Now they're asking you why is the third ionization enthalpy of manganese and zinc higher. Now for manganese, if I have to take, configuration is 3d5 4s2. For then I said zinc again it is 3d10 4s2, 3d5 4s2, 3d10 4s2. Now what happened? Third they said for first 5 ionization enthalpy this goes, second ionization enthalpy this goes. So when you are applying the third ionization enthalpy, what are you left with? Your third ionization enthalpy has to remove electron again from the same 3d5 and 3d10. So what happens here in case of your manganese? Okay, which ionization enthalpy? Ionization enthalpy 3, third, that is your delta Hi3. So for manganese it has become 3d5, and in case of zinc 3d10. You have to apply energy on this. The same concept here, highly stable, so IE is maximum. Simple, isn't it? Just write the configuration, see whether it is first, second or third, and you can write that value or write that reasoning answer. Right, let us see one more set of ionization enthalpy questions. So I already started the ionization enthalpy, then I told you how what are the trends seen in ionization enthalpy in transition elements for 3D series. We have taken an example of chromium, first ionization, second ionization, I compared with zinc, that's done. Then gradually I also told you generally how to write, what are the factors for affecting ionization enthalpy in transition elements. Now we are also going to discuss, suppose if this question is asked for 1 mark, generally writing, I have to write 2 keywords. What do they ask you? Why do transition elements possess high ionization enthalpy? They have not specifically given anything. So simple thing, you have to just concentrate on 2 important keywords. One is smaller atomic radii. Okay, this is what I've told you earlier, in a group because of lanthanoid contraction and in a period because of effective nuclear charge, correct? Yes. Now, smaller atomic radii is one concept which is making the ionization enthalpy very high. Second important concept because of this, Z effective. What is Z effective? Effective nuclear charge. So, Z effective is also high. So because of these two factors, your ionization enthalpy becomes very, very high in transition elements compared to your S block and P block. That is your basic thing. Now suppose if they are asking you this question. What did they ask you? Earlier we have compared between chromium and zinc. Now we are comparing between a set of chromium and vanadium, this combination, and I am comparing with zinc. Now what is the question? See, let us see. Now gradually what am I going to do? I am going to involve one element and try to explain, give you reasoning. They have asked me, why are the ionization values of ionization enthalpy lower for chromium and vanadium and higher for zinc? Okay, now no, nothing to remember with ionization values. Your concept, whole concept moves around your atomic, electronic configuration only. So write in terms of electronic configuration. Now what happened in chromium and vanadium? So when I take your chromium and when I take vanadium, so both, what is the configuration of chromium? It is 3d5 4s1. Yes, one less is your vanadium. So what happens when you are trying to ionize or when you are applying certain amount of energy here? Yes, what happens when I apply the first this is ionization energy? I try to take out 1s electron. Further, okay, when I am trying to apply one more second ionization enthalpy, that is more stable, half-filled configuration, very difficult, right? So now what happens? First, for chromium and vanadium, when you are trying to take out this 1 electron, 4s electron, so you are going to, what are you going to do? You are going to do ionization of s electron. How many s electrons you have? Only one. Done. Now here when it comes to Zn, because the charge of Zn would be Zn plus 2, how many are you ionizing? You have to ionize 2 s electrons. Yes or no? So here ionization of how many electrons? Of 2 s electrons. Now what is the concept? We very well know ionization of s electron. What is the main concept of s electron? S electron has higher penetration power than P, P greater than D, D greater than F. So what is the concept? When the penetration capacity, okay, when the penetration capacity is high, means you will hope you know the penetration capacity. Yes, when this penetration capacity is high, the nuclear charge or the effective nuclear charge will be also maximum. So Z effective is maximum. When the Z effective is maximum, should I apply less energy or more energy to take out that particular thing? Yes, important. Ionization enthalpy also will be maximum. So simple. Here in ionization of chromium and vanadium, only one. In zinc, I have to ionize 2 s electrons to get that Zn plus 2 state. So there the concept of this penetration acts. Now I already studied in grade 11. S orbital penetration is very high, closer to the nucleus. When it is closer to the nucleus, Z effective, that is nuclear charge also is maximum. When this is maximum, I have to apply almost 1734 kilojoule per mole to take out that electron from S. So that's why zinc has higher value. So this is your answer. You're going to write in this way. Yes, I hope it's easy. Let us come back into. They've asked me, why is first ionization of 5D series higher than those of 3D and 4D? Okay. Now they've compared the elements in 3D. Now they've gone to a question called comparing between 3D, 4D and 5D. All the three they're going to compare. They said, why is ionization enthalpy of 5D higher than 3D and 4D? So as we've seen in the configuration, when I speak about 3D configuration, now 3D series. So 3D series, the configuration is 3D1 4s2. Okay, let us write. So let us write this answer. I have to write in terms. In 3D series, you have your 3D1 and 4s2, the first element. In 4D series, it becomes 4D1 4s2, 5s2. Correct. When I have to go to 5D series, not lanthanum, but it is for cerium. When I go for cerium, you along with this, now 4D1 becomes 5D1, 5s2 becomes 6s2. Apart from this, you also have an electron entering into 4f subshell. This is most important. Here, what's happening? This 4F or F subshell, first important thing, F has which shape? It is double dumbbell shape, right? And F has diffused. When for the shell, the electrons are diffused. They are very farly spaced. When they are farly spaced, suppose if I have one electron here, one electron here, one electron here. Now this is your positive. Okay, one electron here. All are diffused in F. So because of this diffused nature, what will happen to the shielding effect? Yes, it is poor shielding. It is very it doesn't protect the outer electrons. So because of this poor shielding, whatever nucleus is here, it tries to drag this electron, it tries to drag this electron also, right? So because of this poor shielding, atomic radii decreases. When atomic radii decreases, what will happen to the Z effective? Z effective nuclear charge increases. When nuclear charge increases, ionization enthalpy also increases. Simple. How did I relate? I have related from the configuration, taking F into consideration, because this is 3D, D, S, but only variation is F. So in 5D series, because of the because the electron enters into the F orbital, you have to say, because of the shape of F, which is diffused, and poor shielding, higher nuclear charge, automatically I have to apply a lot of energy to take out this electron, as nucleus keeps on dragging these electrons towards them. Right, so let us see this question now. We almost completing the ionization enthalpy. The various variations and anomalies have clear. I spoke about this concept. I spoke about this one. This is increasing. So all these questions are covered based on ionization enthalpy. Let us finish off the topic with these two questions. Yes, let us read. Why does copper and zinc? Why does copper and zinc do not extend oxidation state beyond 2? Simple, right? So copper, where is the copper here? And zinc is here. Why don't they extend beyond 2? Because of their stable configuration. And because of the stable configuration, what is happening? Ionization enthalpy is very high, isn't it? For stable configuration, you can write it in one word, simple answer, because of stable configuration and high ionization enthalpies. That's it. This is the concept which the examiner expects you to write. Now, done. And let us come back and do this question. This is a bit tricky, but it's easy. While filling up electrons in atomic orbitals, okay, the 4s orbital is filled before 3D, but the reverse happens during ionization of an atom. Explain why. Okay, they're asking us, whenever you're filling an electron, you first try to fill S and then go and fill your D. But when you're trying to remove an electron, you'll first start with S and then D. What is the reason they're asking us? Simple. So whenever you have to fill an electron, what rule do we follow? We try to follow N plus L rule, isn't it? Yes. Now what is this rule? What happens? We see that whichever is the minimum value after adding both, the principal quantum number and the azimuthal quantum number, after adding both, whichever value is minimum, I'm going to fill that first, right? So let us see for 4s. Now 4s. Okay, 3D also, right? They've given D also, D also. Done. This is your principal quantum number, N, correct? So N plus L rule. So N is 4. L value for S is 0. So this is 4. Now for N principal quantum number, N value is 3. For D, L is equal to 2, isn't it? So 5. So which is minimum value in these two? This is the minimum value. So whichever is minimum value, I'm going to fill that first and then go to D. So that is the reason for the first one. Now for the second one, when I have to take out, or I'm using ionization enthalpy, I have to remove an electron. So what happens when I compare this one, N minus 1 D and your NS? Isn't it? Right? Now, which is easier? When I have to remove electron, this is the outermost shell and this is your inner shell. Now, I can easily remove electron from this using less energy, but removing electron from the penultimate shell will become difficult. Why? Because the electron attraction or the nuclear attraction keeps on dragging the electron. This is your penultimate shell. That is your inner shell, penultimate. So the nucleus tries to drag the electrons from here. The nuclear attraction will be more. So what should you write as the second reason? When removing an electron, it is easy to remove s electron compared to, okay, I'll write it here, compared to D, because it is in the penultimate shell closer to the nucleus. So these, because of these two reasons, first is this reason, second is this reason, that is why we follow this concept. So we've already completed the ionization enthalpy concept. We've already done, let us see what have we done in D block. We have studied trends in atomic and ionic radii, yes. We have done we have done ionization enthalpy, yes. We have also learned what is the concept of enthalpy of atomization, done. We've also studied how are the questions related based on electronic configuration, where are related with the color property or stabilization concept and aqueous solutions, and have shown you whether it's going to show paramagnetic or diamagnetic behavior. Now let us come back and learn oxidation states. Now oxidation state questions are basically very easy questions, but let's see how can we answer such question if it is given in the exam. Now when I speak about your transition elements, oxidation state, so on what basis is oxidation state depends on? Oxidation state depends on a few concepts. Let us see. I'm going to relate those concepts in all these questions. So your oxidation state of transition elements, or rather any element, it depends on first important thing, electronic configuration. I'm going to take the electronic configuration, calculate how many oxidation states is it showing, how many electrons can it donate, right? So the first concept is it depends on electronic configuration. The next concept is this oxidation state, or the this property of showing losing so many electrons, it also depends upon sorry, if I say the stereochemistry of that molecule, very important, stereochemistry. I'll be using this concept also, stereochemistry of this molecule. Right? Did I write the spelling? No. Stereochemistry. Yes, this is correct. Now, this also depends upon nature of bonding. Okay, I'm going to use this concept also. Nature of bonding also I'm going to use and do the questions. After this, the oxidation state concept also depends upon lattice energy. Okay. Lattice energy concept also I'll be doing. This also depends upon your solvation energy, yes. And I can also say, if I have to specifically speak about the lattice enthalpy, okay, I will do one question on lattice enthalpy, very interesting, yes. Solvation energy also, yeah. Fine. So all these concepts will affect or will show an impact on the element oxidation state. So let us see how can I solve these questions. So which electron, let us see the first question, which electron are available for bonding in transition elements? I said I'll be using all these concepts. So first question is based on your electronic configuration. So which electrons are involved in D or transition elements? Basically the electrons of n-1d as well as ns electrons are utilized. So both are used in your bonding. So electrons, that is n-d 1 to 10 and 0 to 2. I've already shown why did I take 0. So both these are involving, done. So I've used this concept of electronic configuration. Now let us see, this is a very important famous question, I don't know. Okay, fine. So what is the highest element in transition series which shows highest oxidation state, lowest oxidation state and maximum oxidation state? All the three questions clubbed together. So highest oxidation state in transition elements is shown by an element called ruthenium. Ruthenium is it is coming under your 4D series. So first is ruthenium. Ruthenium 4D series I said. So 4D. Okay, and 4D, after 4D it is 5s. Now next element which is showing highest oxidation state is osmium. Osmium, it comes under 5D series and 6s. So when I have to fill the electrons, this is 4D7, 5s1. So 7 plus 1, 8. Osmium is 5d6, 6s2. Okay. So how many can it donate? It can donate the maximum oxidation state of both. Just see, 7 plus 1, 8. Here 6 plus 2, 8. So the maximum oxidation state of 8. 8 shown by ruthenium and osmium. Done. I have to see now lowest oxidation state. So the lowest oxidation state when I speak, this is basically shown by transition metal complexes. So this is your coordination chemistry chapter where we'll be speaking about coordinate covalent complexes. So the lowest oxidation state is shown by nickel. How? In nickel, when it is trying to form a complex with carbonyl, this is called a nickel tetracarbonyl. So nickel tetracarbonyl, in this particular thing, this is a complex, coordinate complex. Here, the carbonyl group is a neutral ligand. Okay, we have weak ligands, strong ligands. Okay, right. Again, in that you have a neutral ligand also, the ambidentate ligands also. So I'll be dealing with this chapter once I'm done with this. So this CO is a neutral ligand. Most important. When it is a neutral ligand, the charge on ligand is 0. How do I calculate? I am going to take this metal as X plus 4 into 0 is equal to 0. So X is equal to 0. So nickel is the element which will show 0 oxidation state when it is in the form of a complex. So the lowest oxidation state is shown by nickel in nickel tetracarbonate. Done. And next, maximum oxidation state. So maximum oxidation state, when I see this manganese is showing maximum oxidation state, that is plus 7. So I can write manganese plus 7. So 7 plus 7 is the maximum oxidation state. Simple question, isn't it? So just note the concept. Right. So students, we've started with the oxidation state. Let us see this question, which is quite common in your D block element. That is your 3D series. You picked up in 3D series. So specifically, your 3D series tabular column is given in your textbook. 4D and 5D is not given. But most of the questions will be asked from 3D series only. Right. So let us read see this question. How to answer, how to put it in bullets also. Right. So what did they ask us? Explain the following stability of +2 oxidation state. Okay. Now whenever I see the oxidation state of D block elements, right, that is a 3D series, they are showing variable oxidation states. So what is the reason first? Because of the presence of N-1 D electrons, correct? First, we very well know the variable oxidation states. Right, now we have N-1 D 1 to, okay, let us write 1 to 10, and your N is 0 to 2. So because of this presence of D, first it removes electrons from here. After that, it has also the possibility of possibility of removing electrons from D. That's the reason it's going to show variable oxidation state. See how are the variable oxidation state. If I have to start from scandium +3, it's going 2, 3, 4. When I come down, vanadium till 5, chromium till 6, manganese till 7 maximum. Then iron, again this, cobalt 4 in this. Now what is observed? They are asking us to speak only in terms of +2 oxidation state, right? So when I have to go with the first series, now let me speak about this till here, because this is the break point. Now till 7, again it started decreasing, isn't it? Now let me take as the first series here, and let me go with the second series. Not second series, not 4D series, the second set, first set and second set. So when I have to speak in terms of first set, that is from your scandium to your manganese, and second set, let me speak or write in terms of Fe to zinc, so iron to zinc. So what are you observing from the first set? That you're able to observe higher oxidation state. Just see, what did I mark? I've marked all these are stable oxidation states. Very stable oxidation state. So what am I trying to explain? In the first set of series compared to +2, the higher oxidation states are more observed, right? So let us write that. In first set, scandium to manganese, higher oxidation states are observed. Your higher oxidation statements for all these, they are stable enough. Yes, done. Now when I am proceeding down to the lower the second set, what are you observing? In Fe, +2 is stable, cobalt +2 is stable, nickel +2 is stable, copper +2 is stable, zinc +2 is stable. So in lower end of the series, +2 oxidation state is more stable. Right? So now why? What is the reason? They're asking us. So reason is, suppose if I take this iron, now if this is 3d6, 4 is 2, isn't it? Suppose if I take out 2 electrons, what is it left with? 3d6. Fine. Now that 3d6 electron, how is it? It is unpaired. I accept that. But if I'm trying to take out 1 electron from here further, then it becomes Fe +3. this d electron then becomes 3d5, that is stable, yes or no? Yeah, so that stability or that d5 electronic configuration can be attained by overcoming the nuclear attraction from here. Means the nucleus is trying to drag the electrons, d electrons, yes. So this inner dn-1 is very strongly pulled by the nucleus. So what does it prefer first? It tries to prefer +2, then comes back to +3. Yes, not, it can't go till +7, right? Now let us come back and see for CO. When I see for CO here, again +2, yes. So this becomes 3d7. It becomes difficult for me. I have to apply extra energy, ionization enthalpy, to pull this electron because it is closer to the nucleus. Let us come back to nickel. Here it is +2. And done, removed. How many are left? Again, it has d8 electron that is dragged by the nucleus. So it first prefers +2 and then goes to +3, then goes to +4. But preferred first is +2. When I have to go to copper, 1s1 here. If I have to see your copper, S1 electron gone, then it attains 3d10, stable configuration. Yes. Now, if I have to compare that in aqueous solution compared to Cu plus and Cu plus 2, Cu plus 2 is more stable because of the disproportionation reaction which it shows, which I explained in one of the question. So Cu plus 2 is more preferred because of this disproportionation reaction. It gets oxidized and reduced in the same reaction. Now when I come to zinc, it's going to remove 2 electrons and attain stable D10 configuration. So what am I trying to explain all these? I am trying to explain when in D block element, when I go from left to right, basically it is left to right, isn't it? The +2 oxidation state becomes prominent. Why? Because of the inner d electron which are pulled by the nucleus. Z effective is more high in the higher this particular elements, and that's why it tries to prefer +2 state only. So more stable due to an inner d electrons. What do you say? They they experience, right? They experience higher nuclear charge. What is this? This is Z effective. So that is the reason here higher oxidation state and this is lower oxidation state. Right. Now one more important thing you have to remember. +2 and +3 oxidation state, whichever are showing, are always ionic compounds. They form ionic compounds. When it is higher oxidation state, that is your 5, 6 and 7, all these. So higher oxidation states are always, they're going to always form covalent compounds. Remember this concept, please. Right? This is very important when we do certain compound. Just keep this in mind as of now. When I apply this into certain compounds, you will understand the concept. So let us see this type of question. Now, such question is very common in your board paper because they try to club 2 or 3 concepts together. Like we are studying basically ionization enthalpy separately, your oxidation reduction potential separately, color property separately, magnetic property separately. But here, because your weightage of the chapter is 5 marks, they're going to club all the 3 topics together, maybe sometimes 5 topics together, and give you questions like this. Very quite common question. Let us see this question. They've asked us among Ti +4, vanadium +4, Mn +3 and Cr +3, which is, I have to relate these for 3 concepts. One is stability. Okay, let us divide this page into 3. They are asking me to tell me which is more stable. Okay, stability. Then they're asking me to find out which is the best oxidizing agent. They're asking me to find out which is colorless in this. Okay, how will I judge? First important concept which you have to remember in your mind, whenever a concept of stability is asked, remember a particular element after losing the ions, okay, we are basically cations, we lost so many electrons, isn't it? So basically after, not ions, basically after losing the electrons, right? Okay, electron, it's going to form an ion. After losing an electron, if it attains a stable configuration, okay, D5 configuration or D10 configuration, or inert configuration, okay, right? Then we call it a stable ion. Once again, suppose if this particular ion is given to me, first let us see, after removing electrons, right, after loss of electrons, if it is trying to attain a stable configuration, then you call it a stable ion or a stable cation. Let us test for all and see which is more stable. Now I have to take out first Ti plus 4, then you have V plus 4, then you have Mn plus 3, then you have Cr plus 3. For this, atomic number will be given to you. With that, you can write the configuration. Careful while writing. Follow the above principle. Be very careful while writing electronic configuration. If you don't know how to write, your whole answer goes wrong. Now Ti4. Now they asked me Ti. Now first let us write the configuration of titanium 3d2 4s2. So this is 3d2 4s2. Now I have to remove 4 electrons, correct? So when I remove 4 electrons, what will happen to this? This becomes 4s0, this becomes 3d0. What are we left with? We are left with only argon configuration. This is 3d0, 4s0. Now this has attained stability. Okay, let us come back and see vanadium. Vanadium is 3d3, 4s2, right? The configuration 3d3, 4s2. It has to remove 4 electrons. So 2 from here, this becomes 0, and 2 from here, so this becomes 1. So how is this looking? Argon and 1 unpaired electron. Let us start with manganese. Manganese is 3d5, 4s2. You write down 3d5, 4s2. How many should it remove? They've given me Mn plus 3. So remove 3 electrons. 2 from here, it becomes 0. 1 from here, this becomes 4. So how many do you have? Argon configuration and 3d4. Yes, that is what you've done. Let us start with chromium. Chromium, they've asked me to write 3d, configuration is 3d5, 4s1. So write the configuration 3d5, 4s1. How many should I remove? I have to remove 3, isn't it? 1 from here and 2 from here. So this becomes 3d3. So now this is your argon and 3d3. Now important. Now I have a confusion between this one, because it has attained argon configuration. I have a confusion between this because this is already unstable. It is having 1 unpaired electron. This is also unstable because it has unpaired electrons. So now I have to concentrate both on titanium and chromium. Now what happens in titanium and chromium? Most important thing in chromium is this particular 3d3 is like this, isn't it? 1, 2, 3, 4, 5. 1, 2, 3. This concept or this particular electrons have occupied which set? T2G set. And the EG set is empty. Now the attainment of T2G set by Cr plus 3. Okay. Now this is reached the stable form. And when we study in your CFS, crystal field stabilization, crystal field splitting, we are going to split when this particular thing is exposed to photon. These T2G set, now which is stable, yeah, will divide or it break up into T2G set and higher EG set. DD transition we said, isn't it? So that DD transition concept I already explained. Because of the DD transition element and the formation of T2G set, Cr plus 3 is considered more stable because this is complete. If I say half filled, T2G is half filled, and further it is stabilized by excitation of electrons. So when I have to compare between this and this, which is more stable? This is more stable. Chromium is more stable due to formation of T2G set. So that is how you have to analyze. So given compound in the first one, which is the answer, Cr plus 3 due to formation of T2G stable set. This is ruled out unpaired. This is ruled out unpaired. This is also fine, but argon inert gas configuration. But what is the existence of that particular ion? Because of this T2G, as I said, give that particular T2G set the photon, it will get excited. So I'm perfect with this concept. Now I have to start with oxidizing agent. Okay. So what is an oxidizing agent? Suppose if I have an metal in its plus 3 oxidation state. Now when I am writing something like this plus 2, what does it mean? This metal has gained 1 electron and formed plus 2. From plus 3 it has gained 1 electron. So something which gains electrons is an oxidizing agent. So this metal is acting as an oxidizing agent. What is oxidizing agent? Something which gains electrons. So now they're asking, among all these, which is the better oxidizing agent, they're asked me. Now I have to cross check. Now when I have to write Ti4 plus 4. Suppose this Ti plus 4, let me write and write Ti plus 3 also, because I am trying to show gaining. Vi plus 4 by Vi plus 3, Mn plus 3 by Mn plus 2, Cr plus 3 by Cr plus 2. Let us see the configuration. Now when, okay, this one I think you can erase, oxidizing gain. Okay, when this, I'll write here, I need place, gain of electrons. Now, when I take Ti plus 4 and plus 3, just observe your Ti, when it is plus 4, okay, this is plus 4. Now it has gained one electron. From plus 4 it has gained. So this becomes what? It becomes, from 4 it has gained one electron. That electron reaches the this one D, and this becomes D1 configuration. Now B. Vanadium, it is plus 4. So when it is plus 4, what will happen? This becomes 0. This also becomes 0. Correct? Now when this, okay, let us write. This becomes 0. This also becomes, it is 5, isn't it? So this becomes 1. Now what is this configuration? It is, no, earlier it was 3d3 and 4s2. What did I say? It is, it's going to take out 4 electrons. 2 from here and 2 from here. So this becomes this T4. Now I said, no, V4, sorry, V4. Now I said it's going to gain one electron. So where will it gain? It will become D2 configuration. Let us come back to manganese. Manganese, it is plus 3 to plus 2. So what is plus 3? First write plus 3. When it is plus 3, it is 0 and this is 4. Okay. Now I have to convert gain one electron plus 2. Where will it gain? It will gain electron here and this becomes D5. Chromium plus 2 plus 3 plus 2. Now where is chromium? Chromium. Chromium plus 3. So chromium plus 3 is, S will become 0. 5 will become 3. Now I have to gain one electron to this. So D becomes D4. This is D4 configuration. Okay. Now tell me, among all these, which is the better oxidizing agent? Whichever reaches stability is the better oxidizing agent after loss of electrons. So among all these, Mn plus 3 to plus 2 has reached a stable configuration D5. Hence, it is the best oxidizing agent. Okay. So simple. Wherever it reaches stable oxidation state, that is your best oxidizing agent. So Mn plus 3. Done. Let us come back and see color property. So color property, when you speak, whenever an element has unpaired electrons, automatically when you expose that particular element to photon, it gets excited to the higher state. During this process, it's going to absorb a frequency of light from the visible spectrum, right? But for showing the color property, it should have unpaired electrons. That is a concept, main concept. Color, for showing color, this one, whichever doesn't have unpaired electrons is colorless. So now we have to see whether among all these, which is not having unpaired electrons. Okay, right. I think I can use the same for this one, for this concept. Now, Ti plus 4 unpaired electrons, Ti plus 4 no unpaired electrons. Done. Next, V plus 4, how many unpaired electrons do we have? 1. Mn plus 3, how many unpaired electrons do we have? 4. Cr plus 3, how many unpaired electrons do we have? 3. So, one unpaired electron, it is colored. Mn plus 3, colored. Cr plus 3, colored. So, this doesn't have unpaired electrons, so this is colorless because there's nothing to excite to go and absorb the color or this particular frequency of color from the spectrum, isn't it? So, Ti plus 4, because of the absence of electrons, Ti plus 4 is colorless. So, I've answered all. Let us write which is more stable. I've written Cr plus 3. Which is an oxidizing agent? I said Mn plus 3. Which is colorless? I said Ti plus 4. This is how you're going to reason the answer. Right. So let us come back and do some more questions in oxidation state. So I'm trying to relate your oxidation state with electronic configuration. Let us see if we can further proceed and apply the first given information on oxidation state. Right. Let us see one more question. Why is scandium 2 virtually unknown? That means scandium oxidation 2 is not known. Why? So when I have to take scandium, the configuration 3D1 4s2. Correct. Now this is scandium 2. So when I have to show second oxidation state, I have to remove electron from here because this is the outermost shell. So I'm going to remove this as scandium 2. Then this becomes 0. Correct. Now the leftover electron in D, you have only one. Highly unstable, isn't it? So this is unstable. So when this is highly unstable, scandium doesn't show this type of oxidation state. So +2 is not shown. It can only start from 3. So this is because of this instability. Sc2 is unknown. But it is going to show +3. So when it is +3, how does it look? Scandium 3, if I have to write +3. So I said 3D1 4s2. So 3 means this becomes 0 and this also becomes 0. The leftover configuration is stable inert gas configuration. So this is your scandium. Now next important thing, why is Ti4 more stable than Ti3 or Ti2? Okay, nice. So so titanium configuration after scandium is titanium. It is 3D2 4s2. Now let us write titanium 3 and titanium 2 also. Okay. If it is titanium 2, if it is titanium 3, if it is titanium 4. In titanium 2, you are going to remove 2 electrons from here. This becomes 3D2. In titanium 3, you are going to remove 2 electrons from here. 1 electron from here. This becomes 3D1 and 4s0. This is 4s0. In titanium 4, you are going to remove 2 electrons from here, 2 electrons from here. This becomes 3D0, 4s0 and the configuration, argon configuration stable. So now let us not club this question here. This is Ti2. Okay. Now see, what are you observing? This is the original configuration. Ti2. Both, this is unpaired electron, unstable. So this is unstable. When I have to check Ti3, this is also there's only presence of one half filled. So this is also unstable. But here when it comes to Ti4, after removing 4 electrons, what is it getting? It's getting stable inert configuration. That is a reason Ti4 is more stable than Ti3 and Ti2. Simple answering, isn't it? Now let us come back and see why zinc does not exhibit variable valency. Okay, zinc does not exhibit variable valency means again they're asking us to relate with electronic configuration. When I have to take zinc, it comes under 3D series, 3D10 4s2. It can exhibit only +2 oxidation state. Yes, so only +2. So when it is zinc +2, it is 3D10 only. This becomes 4s0. So what is it attaining? This is again attaining stable configuration. So it can't expand its valency beyond that because it's very difficult to remove electron from a stable configuration. So because of the stable configuration, it only shows +2 oxidation state, not beyond that. So that's why we've written +2 here. Let us come back and solve one more question for your oxidation state. So here what does the question say? Why are molybdenum 6 and tungsten 6 found to be more stable? Means how are they formed? Basically the formation is more stable compared to chromium 6. Now your chromium is here. Now why is this oxidation state very less stable compared to your molybdenum in the next series and tungsten in the next series? Why? So if one such question is given, so our concept is Cr6 is less stable, means the formation is less stable than MO6 and W6. I have to prove this. So let us write the configuration first. Now chromium, when I have to take 6 or the electronic configuration, it is 3d5, 4s1, the normal one. Okay. Now for molybdenum, yes, 6, it is 4d5, 5s1. Now for tungsten, 6 oxidation state, 5d4, 6s2. Now what is the difference between these three? Here for chromium you have 3d, for molybdenum you have 4d and 5d. Now I am going to speak in terms of radial nodes, right? Now basically whenever we are speaking about radial nodes, two important things you have to concentrate. First, how to calculate radial nodes and what is the use of something having radial nodes and not having radial nodes. Now in case of 3D, if I have to calculate radial nodes, what is the formula I apply? I'm going to apply a formula called n minus 3. This is the formula. So now substitute this 3 here. This n is equal to 3. This becomes 3 minus 3 is equal to 0. So 3D has no radial nodes. When I have to calculate for 4D, it is 4 minus 3 is equal to 1. It has one radial node. If I have to calculate for 5D, it is 5 minus 3 is equal to 2. It has 2 radial nodes. Now, what is the use of radial nodes? Suppose if an element doesn't have any radial node, the attraction towards nucleus is very strong. So where are we finding this attraction? In 3D, isn't it? In 3D, nuclear attraction is very high because there is no node or radial node present in that. So this attraction, I'm going to write that nuclear attraction is strong. Nuclear attraction. So because of this nuclear attraction, yes, nuclear attraction. Now tell me, can chromium release or form 6 oxidation state? Can it lose 6 electrons from its outer configuration? Very difficult, isn't it? So nuclear attraction is strong. And when it is strong, formation of plus 6, 6 oxidation state becomes difficult. When it is becoming difficult, what can I write? The formation or the stability of Cr6. That is, it is less stable, hence less stable. But when I compare these two, molybdenum and this, they have radial nodes and they are not so close to the nucleus. They can easily donate those 6 electrons from their outer configuration and form a plus 6 oxidation state. So let us see this question again, very important question. What do they give us? Why are lower oxidation states found in complexes like nickel tetracarbonyl and iron pentacarbonyl? Okay, basically I already did one question based on what is the nature of carbonyl compound. Let us see. Now when I have to write this answer, we have to concentrate more on this carbonyl group. What is the reason? Basically they said lower oxidation state means to what extent? Here nickel, when I speak about nickel, when I have to calculate the oxidation state, let us take this as your X. Now plus 4, this is a neutral ligand. Now basically your carbonyl is a neutral ligand. The charge on that is 0. Neutral ligand means there is no charge. So when it is a neutral ligand into 0, so X is equal to 0. So the oxidation state of nickel in such complexes is 0. Here also it's the same case. Carbonyl is a neutral ligand. When I multiply, the oxidation state of iron also comes back to 0. What is the reason they're asking? So now your neutral carbonyl compound being a neutral ligand, what is its basic property? This carbonyl compound is going to show two important things. What? It's going to show a concept called back bonding. What is this back bonding? P-pi back bonding. Apart from that, it also forms a strong sigma bond. Let us see what it is. Now suppose I have this metal. I'm going to take this as M. You have, yes, oops. This has a pair of electrons. This metal is going to form a complex with this, with carbonyl compound. This also has. Apart from that, along with this, you have oxygen. right? So now what happens, this metal and carbonyl group first tries to form a sigma bond, strong sigma bond. This is your sigma bond, right? Now after that, this is going to also show a property called back bonding. What is back bonding? Here, from the orbital of metal, the electrons will be dragged towards your carbonyl carbon, yes, forming a p pi bonding. See here, this is p orbital, pi bonding above and below. So p pi back bonding. So this is your back bonding. Now your molecular orbital of this is a bonding molecular orbital, BMO, and as we've studied bonding and anti-bonding orbitals, isn't it? When two atomic orbitals combine to form molecular orbitals. So this is bonding molecular orbital. From here, the electrons are going to shift into anti-bonding molecular orbital. Now what happens when it's trying to drag the electrons, the bond between this and this becomes very strong, and the bond between this and this becomes very weak. That means, what am I trying to explain? Metal carbonyl bond becomes strong and your carbon oxygen bond becomes weak. It becomes weak. Now during this process, what happens? One is sigma bond, strong. One next is pi bond, done with these two effects, right? Now that particularly behaving as a neutral ligand. Because of this neutral ligand, nickel and iron both are showing zero oxidation state. So you can write your answer showing this, and you can also write p pi back bonding. Yes, it's already dragging the electron density towards itself. Alright, so let us see this question again in oxidation state. The asked us, why is a Cu plus not stable in aqueous solution? Okay, right, very famous question this is. Now, when I have to compare Cu plus 2 and Cu plus 2 is more stable in aqueous solution. So, because of the present formation of ions. Now, what is the reason? So, whenever you are speaking about aqueous solution, you have to speak only in terms of hydration enthalpy. So, what is hydration enthalpy? Basically, the amount of energy or heat released when this particular ion are forming a bond with water molecule. They're trying to form a bond, or hydrogen bond means the formation of bonds with water molecule together is called hydration enthalpy, whatever energy is released. Now, when I have to see copper and Cu plus 2 and Cu plus 2 has highest negative hydration enthalpy. So because of this hydration enthalpy, higher than hydration enthalpy, more stable is a compound. So here this copper plus 2 highest hydration enthalpy compared to this. Now when I have to see the values, the hydration enthalpy of this is for Cu plus 2 is almost minus 2161 kilojoules per mole. When I have to see for copper, Cu plus, okay, I'll write this like this, so it's clear. Now for Cu plus, when I have to take, the negative hydration enthalpy is only minus 619 kilojoules per mole. So now, based on this concept, higher the hydration enthalpy or the negative hydration enthalpy, stronger or stable is the bond. So that's the reason Cu plus is less stable than this one. So this, you can easily write this answer for 1 mark, I believe. Let us come back and see. Now they said, why are Mn plus 2 compounds more stable than Fe plus 2 compounds towards plus 3 oxidation state? Okay, they said Mn plus 2. So manganese, when I have to write, the configuration is 3d5 and 4s2. And when I have to take iron it is 3d6 and 4s2. Now they said plus the Mn plus 2 towards oxidation state of plus 3, they said, right? So now when this is losing these 2 electrons, that means Mn plus 2, this becomes 4s0. But suppose if Mn plus 2 is showing plus 3 state, now what will happen to this? This is going to lose stability, isn't it? Now Mn plus 2, it's highly stable, not a problem. It is half filled and it is highly stable. Suppose if this Mn plus 2 is trying to prefer, or if it is trying to show this oxidation state, this will become 3D4, which is unstable, correct? So it will not prefer going for plus 3 oxidation state. But when I have to take Fe, now let's see, plus 3 will it go or not? Plus 3, 2 electrons from here, 0, one more electron from here, 5. Isn't it showing stable configuration? Yes. So because of this loss of 3 electrons, Fe, because of plus 3 oxidation state, Fe will attain stable configuration. But in Mn, you have to be careful, only 2. In Fe, it can go till 3 and try to form stable configuration of this. So that is how you're going to answer the question. Right. So let us do one more question in oxidation state. Let us see this. Now what do they give us? Name an oxometal anions of first series. Okay, they want us to write an oxometal of the first series in which metal exhibits oxidation number equal to its group number. Okay, what is an oxometal basically? When I have to write or first know what is an oxometal. Now oxometal is something where you have an oxygen atom linked to two metal atoms. It can also be one metal atom like M double bond O, not a problem, right? So this is an oxometal. Now they're asking us, tell us a particular oxometal which are going to show the oxidation state equal to the group number. Now let me pick up this for example, chromium and manganese. Common things, Cr2O7 minus 2. Let me take the second one, MnO4, because I have to show the oxygen linked to the metal atom, MnO4 minus. Let us calculate here. When I have to calculate oxidation state, this is 2x plus 7 into the valency of oxygen is minus 2 is equal to 2. When I have to solve this, x is equal to plus 6. Here the group number and the oxidation number both are same. It comes under that. So both group number and oxidation number are same. Let me calculate for manganese. Manganese X. This is 4 into 2 minus 2 is equal to minus 1. X is equal to, this becomes, okay, x minus 8 is equal to minus 1. So what do I get? I get x is equal to plus 7. So here this is plus 7 oxidation state. Both the group number as well as the oxidation number are same. So this is your oxo anion for the group 1 series. 2 examples, easy, yes, done. So just calculate the charge, and we already know group number is also the same as well as the oxidation number is same. Group number, oxidation number, okay, done. So now let us come back and calculate this. Calculate the number of unpaired electrons. Okay, this is one more way of asking you question in oxidation states. So they have given us plus 3 charge. Just simply write the configuration and calculate the oxidation number. Manganese, they said plus 3. So manganese configuration is 3d5 and your 4 is 2. So simple. Now I have to take out 3 electrons, 2 from here and 1 from here. So this becomes 0 and this becomes 4. So how many unpaired electrons? 4 unpaired electrons, isn't it? 4 unpaired electrons. Now let us write for chromium. So chromium is 3d5, 4 is 1, 3d5, 4 is 1. What should I do? I have to take out 3. 1 from here, 2 from here. So let us take out that 1 from here and 2 from here. So this becomes 3. So 3 unpaired electrons. Let us write for vanadium. Vanadium is 3d3, 4 is 2. 3d3, 4 is 2. Now I have to take out 3. 2 from here and 1 from here. So how many unpaired electrons? 2. Titanium. When I have to do titanium, 3d2, 4 is 2. I have to take out 3 from here, 1 from here, 1 unpaired electron. That's it. Right. So let us come back and finish off almost all the questions of your oxidation state. Let us see this question. So which metal in first series of transition metal exhibits +1 oxidation state more frequently and why? Okay, fine. So in your transition series, first series, the first series is already on the board. They're asking me which one will show +1 oxidation state more frequently. Let us see. Here this doesn't have +1 ruled out. This also doesn't have. This also can't. This okay. We have possibility between chromium Okay, this is also ruled out, these two. Okay, let us see. You have chromium +1 and copper +1. So which will show more frequently? Suppose if I have to take out S1, right? The one electron, this becomes a D5, half filled stable. But when I have to see copper if I have to remove, it's going to attain completely filled stable configuration, right? So which is more preferred compared to chromium? Copper is more preferred, right? So copper configuration is 3D10 your 4s1. So when it loses +1, it will attain D10 configuration, stable, compared to this fully filled. So copper is the element. Now let's see, what is this given? How is the variability in oxidation state of transition metals different from non-transition elements? Okay, they want us to show how is the oxidation state varying between transition and non-transition. Okay, transition, your D block element; non-transition, when you go to your extreme of P block element, your phosphorus elements, right? All this, the P block elements, right? Extreme of the periodic table, right? So now when I have to say, just observe carefully how much. Now here it is 2, 3. Well, how many units difference? 1 unit. 1 unit. Here also 1 unit. Now this is also 1 unit. So everywhere it is differing by 1 unit, isn't it? Yes, let us take one example now. 2 after 2, 3 after 3, 4. So in transition elements, if I have to take, let us pick up any example. You can take any either iron, you can take chromium, manganese, anything, but common things are iron, isn't it? You can easily remember. If I have to take iron, now these are transition metals. Now let us write non-transition metals. So in transition metals, I am going to take Fe. So Fe exists as Fe+2 and Fe+3. So what is the difference? +1. Suppose if I take non-transition metal, phosphorus. Phosphorus, it can exist as your P3 and P5. What is the difference? 2. Let us take one more example. Suppose iron, chromium also. Cr+2, Cr+3. What is the difference? +1. Tin, Sn, Sn+2, Sn+4. These are common examples, +2. So the difference is, in transition metals they are showing a difference of +1, and here they are showing a difference of +2. Why? Because here when you are trying to fill the electrons or that particular thing, you are trying to take out one electron from here, the d orbital, as I said, it's incompletely filled, isn't it? Means, okay, not for everything, but for few. If I take out this particular thing, again I'm taking out one electron and deconfiguration. Nuclear charge is more on this, isn't it? So it tries to prefer, or means the difference is always +1. After +1, then +2. Then it goes to D, right? So, but not in case of transition metals where it is showing +2. So you can write incomplete filling of D orbitals, or the charge on D is higher compared to the non-transition elements. Right. So let us do one more question in the oxidation state. This is a very interesting question, commonly asked question also. So let us read this question. What did they ask us? Manganese shows highest oxidations of +7. Okay, when we see the table, it's going to show the maximum oxidation state. Okay, done. And with oxygen, okay, they said now we are going to speak with, as I said, oxygen and fluorine are electronegative in nature, and they're going to combine and pull the electron density and try to form a bond. Now they said with oxygen, it's going to show +7 oxidation state. Okay, and but fluorine, it shows only +4 oxidation state. What is the reason, they asked me? Right, let us see. Now the compound formed with oxygen with +7 oxidation state is sorry, this Mn2O7. Done. And with fluoride with +4, see here, manganese, and the oxidation state is +7. Yes. Now with manganese with fluorine, the compound formed is Mn4, F4, because +4. Now let us see what's happening here in Mn2O7. Why is it forming? Let us write structure. So manganese is here, one more manganese is here, 1 and 2 here. Now 7 oxygens, isn't it? 1 oxygen forms, links both the manganese, and you have 6 more, 3 on this side, 3 on this side. The 1, 2, 3, 4, 5, 6 and 7. Now what are you observing here? What type of bonding is observed here? Oxygen is going to involve the p orbital. It doesn't have d, isn't it? Oxygen is going to involve p orbital and forms p pi bonding, p pi from oxygen. And manganese, as we know, it has d orbital involving, yes, so it's going to form which type of bonding with this? Involves the d orbital and forms d pi. So p pi d pi bonds are formed. First important thing. So p pi d pi, what bonds are formed? P pi d pi, multiple bonds are formed. So here so many multiple bonds existing. Yes. So because of this reason, manganese is going to show, okay, you can write that because of p pi d pi. Let us, okay, I will p pi d pi, multiple bonds. It shows +7 oxidation state with oxygen. Done. Let us come back and see Mn4. Now in manganese, when I have to draw the structure, it is like this: 4, 4, one more and one more. Again you have one more manganese here in the center, and it is like this, both clubbed together, fluorine, fluorine and fluorine. So what are you observing when I have to see fluorine? What fluorine? Atomic number 9. 1s2, 2s2, 2p is 5, 6, 7, 8, 9. So in 2p9, 5, 1, 2, 1, 2, 3, 4 and 5. This one electron is used in participate or sharing to form a bond with manganese. One more fluorine, one with manganese, one more fluorine, manganese, one more fluorine, manganese. Do you have any availability of 2p orbital here? No, isn't it? So non-availability of 2p electrons, hence cannot form or extend beyond +4 oxidation state. This is how we are going to answer. So this is how the perfect way of answering the question. Whenever there's such question, write the structures and explain here and highlight. Take your pen and try to highlight here, and non-availability of 2p electrons. That's it. So let us see one more question, oxidation state. I'm trying to do so many questions so that you can easily do. I said the same again, one more this one also. Please try to practice the questions, all the questions. I think I've covered almost all the different variations which come under oxidation state. If something else is left out, I don't think it is left out. If it is left out, I'll do again revise in the month of February. That is your vigorous revision, which so that you could score that 70 out of 70, I hope. Let's see. In your board exams. Let us see this question. They've asked us what may be the possible oxidation state of transition metals with following electronic configuration in ground state of their atom. Okay, they are asking us to show the possible oxidation state for vanadium, manganese and iron from their ground state. I have to take the ground state configuration and show them the possible values. I'll also tell them what is the stable configuration for them. Right. So this type of question I've done one more also, but okay, let us see this. Now whenever now for this they'll be giving you the atomic number. After seeing the atomic number, you can write the configuration. Now already I have the configuration here to save time. Vanadium ground state configuration, it is argon and it is 3d3 4s2. Now for manganese, again argon configuration 3d5 4s2. For iron, argon configuration, that is 18 is argon, isn't it? So 3d6 4s2. So 18 and this comes to 6. Now 26 is the atomic number, 18 plus 2 20, 20 plus 6 26. Now they are asking me to write the possible values. Now see, one important thing you can remember. So whenever you are trying to have or trying to remove the electrons, we very well know electrons first are removed from here and then starts, right? One electron will be removed using ionization enthalpy. So here in this particular vanadium, I can remove 2 electrons. Fine, because you can start from 2. Okay, right, 2. If I can write 2, 1, can I write 1? You can write 1, but that possibility of 2, removing 2 and the leftover D3 is again stable, isn't it? So that's the reason I'm starting from 2. And after that, it can show 3. it can show 4, it can show 5. Till 5 I can remove. That means all the 5 you can remove so that it attains a stable inert gas configuration, possible values. Now, after that, here again same, 2. It can remove 3, it can remove 4, it can remove 5. Because basically all the 7 it can lose, because after losing all the 7 it attains stable configuration. So I've written step by step, plus 3 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7. So the maximum is 7. Till 7 it can lose and attain inert gas configuration. Now in iron again the same story. Start from 2, then 3, then 4, then 5, because total are 7, isn't it? Yeah, 8, isn't it? 6 plus 2, 8. So 6 plus 6, right? So it can go till plus 3 plus 4 plus 5 plus 6. Yes. Yeah, what happened here? Now just see, I have written 2, gone. How many are there still? 6, isn't it? So 3, 4, 5 and 6. Done. Maximum of 6 only. Now here they're asking me to write what is the stable configuration. Now see, in my vanadium, if it loses till 5, it is going to attain stable inert gas configuration. So stable configuration is plus 5. So write down vanadium stable configuration is plus 5, or you can write like this, vanadium 5. In manganese, if it loses plus 7, it's going to attain stable inert gas configuration. So 7 plus 7 is a stable configuration. 7. In iron, just observe, iron, if it loses 2, right, it's going to attain D6 configuration. That's one possibility. So D6, okay, it is unpaired, and there is also one paired electron, that is D, because, okay, let me write that. 1, 2, 3, 5. 1, 2, 3, 4, 5, 6. Now, when it is trying to lose 2 electrons, it is having D6 configuration. Okay, fine. But this 2 electron, to some extent, possibility that this electron gets excited to the next one. So that possibility of plus 2, yes, stable configuration 2. Now, suppose if I take 3, it's going to remove this electron from here. Yes, very stable, isn't it? Plus 3. Stable because it is going to form half filled configuration by plus 3. So I can easily say plus 2, yes, unstable configuration, plus 3 also, because by plus 3 it's going to attain half filled, that is stable D5 configuration. So iron is going to show plus 2 and plus 3. By plus 3 it attains D5 configuration. So this is how we are going to do. Let us cross check. Vanadium plus 2 plus 3 plus 4 plus 5. Vanadium plus 2 plus 3 plus 4 plus 5 stable. Manganese 2, 3, 4, 5, 6, 7. 2, 3, 4, 5, 6, 7, stable 7. Iron 2, 3, 4, 5, 6. Iron 2, 3, 4, 5, 6. Stable 2, plus 2 and plus 3. I also give the reason. This is how we are going to write the answer. So we've already completed your oxidation state. I think I have done almost all the questions which are possible for your board exams. And let us come back and do the next trend of your D block elements, that is your electrode potentials. Okay, very important concept. I think in your school's electrochemistry is already done. I hope you understand this concept clearly. But as and when I do the electrochemistry, I think I'll be touching this concept again. Right. So whenever we are speaking about electrode potential trends, 2 important concepts you have to remember. Just register that in your mind. What should you remember? First thing, in your exam, whenever questions based on electrode potentials are given, the electrode potential values are given to you. Please don't try to by heart the values, not required for you. As I said, atomic number also is given, as well as electrode potential values are also given. Nothing to remember, nothing to memorize. Point number 1. Second point, what should you remember in electrode potential is, whenever you have, just observe carefully, yes, electrode potential values are basically represented by E naught, standard electrode potential values. Yes. So we are going to study this electrode potential by a series of that particular series is called electrochemical series. Correct? Yes. So in basically electrochemical series, you have all the positive values above. In between is the reference electrode hydrogen, and your negative values come here. Because of the lack of space, I have written here. Now in electrochemical series, basically it explains us about it places different metals based on their oxidizing agent, oxidizing property and reducing property. Remember that. So I'm going to use this electrochemical series to explain the concepts of questions of your electrode potential values. So whenever you're given a question of E naught in the exam, now see E naught for an particular metal, okay, with a +2 or M +2 by M. Now I'm going to call this as a couple. Now if the E naught value is maximum negative, that is your negative value is the value is maximum negative, means SRP. Okay, what is this SRP? Negative standard reduction potential. Now if the value is maximum negative, then that particular metal, I call it as a strong reducing agent. Second thing, if the E naught value for M +2 by M is positive, which positive? If I say this is maximum negative, if I say it is maximum positive, then I call it a standard oxidation potential, SOP. And that particular element which has maximum positive value, I call it it is a strong oxidizing agent. Remember this. Yes. Now let us come back to this table. Now I have a basic idea. Whenever you see maximum negative value in the question, that means they are talking about reducing agent. That is a reducing agent. If it has positive value, it is an oxidizing agent. Okay, done. Now I am going to take this concept, come back and relate to this. Now in an electrochemical series, yes, we are going to take hydrogen. We very well know hydrogen. We take it as standard SHE, standard hydrogen electrode. We take it as a reference electrode, and the electrode potential is 0, 0. Now the element or the metals which are placed above the hydrogen, just observe, all have positive values. This positive value explains that all these elements are oxidizing agents. And I said maximum positive value. What is the maximum positive value? Cobalt. It has an electrode potential of plus 1.81. So cobalt is the strongest oxidizing agent. It is an oxidizing agent, maximum, so strongest oxidizing agent. These are also oxidizing agents because they have positive values, but the tendency of oxidizing reduces. It is less compared to cobalt. Now all these are oxidizing agents. So as we go down, the oxidizing property reduces. Correct. Now after hydrogen, when I come back to all these metals, they have all negative potentials. Now I said the maximum reduction potential, whichever has maximum negative value, that is the strongest reducing agent. So the value of lithium is -3. So this is the strongest reducing agent. So what do I write? This is the strongest reducing agent. So higher the negative value, it is the strongest reducing agent. Higher the positive value, strongest oxidizing agent. That's one thing. Next important thing which you have to remember is the metals which are above hydrogen will never replace hydrogen. Okay, all the positive values will never replace hydrogen, and the ones which are below hydrogen will replace hydrogen whenever an acid is added. Okay, remember that concept because I'll be doing so many questions based on this only. So let us write what I said. Metals with positive E naught will not reduce hydrogen, or will not release. Okay, let us not write will not release hydrogen gas. Okay, with that concept, let me start with all the questions. Hope your concept of electrochemical series is clear, and I'll be doing so many questions based on this concept. Now let us see the first question, the most popular question asked. It is the same. Most of the transition metals do not displace hydrogen from dilute acids. Why? Okay, they've given me this question. In grade 10, we have done an experiment like this, isn't it? What is an experiment? Metal plus acid. You have taken acid in a test tube and added a piece of metal in that. After some time you would have seen the formation of hydrogen gas which pops out of the test tube, and the formation of salt in the particular test tube at the base. Now what am I trying to say? Metal, when I take plus acid, gives me salt plus hydrogen gas. This is what you have studied in grade 10. That is the question asked in grade 12 now. Now they said metals of transition metals do not displace do not release hydrogen gas from acids. Why, they said. So what actually happens? I said the metals which are above hydrogen will never displace or remove hydrogen. The metals which are below the series will release hydrogen gas, I said. Now that is the reason. Now see, copper, when I react with sulfuric acid, it doesn't release hydrogen gas because the electrode potential is above. When I take chromium, it doesn't release hydrogen because the electrode potential is above. Same with manganese, same with cobalt, right? So silver also, it doesn't release hydrogen gases and it doesn't react also. So that is the reason most of the transition metals, just see, copper is above, iron is above, silver, manganese, chromium, gold, or cobalt, all are having positive electrode potential values. So reads, okay, so we'll have most of transition metals have positive electrode potential values, that is above hydrogen. Hence, they do not release hydrogen gas. Now, what will happen when I have the elements reacting below the hydrogen? So, if I take out zinc, right? Now, zinc metal, if I am going to add sulfuric acid to this is going to form zinc sulfate and hydrogen gas is released. This is how simple. This is how you're going to relate. Above will not release hydrogen, below will release hydrogen because of this negative SRP values. Right, so let us come back and do one more question on your electrode potential values. So till now we have I think one or two questions where I told you whenever it is negative, it is your standard reduction potential, electrode potential is negative. If it is positive, standard oxidation potential. Done. Now let us proceed to the next level of understanding this topic. So this is basically your NCERT question only. Let's see how can we solve this question. Very simple. The question is too large enough, but it's easy to answer. Let us read the question. They've given me M plus 2 by M. Okay, fine. Now what happened here? From plus 2 state, this has gained, this metal ion has gained electron and it has got converted to metal. It has already gained. Now let us see here. From M plus 3 to M plus 2, what happened? One electron is gained by this and it is getting converted to M plus 2. So isn't it getting reduced? Yes, done. Now systems. Now E0 values for some metals are as follows. They've given us E0 value. As I said, E0 values will be given in the exam. So they said this metal got reduced and the values of these. Now let us see for chromium. Yes, it got reduced. Here also the same. Here plus 2 to plus, okay, same, here also same, here also same, here. What are they trying to ask us? They're trying to ask us stability of Fe plus 3 in acid solution as compared to that of Cr plus 3 and Mn plus 3. Okay, they're asking me to compare the stability of Fe plus 3. So where is Fe plus 3 in this? Don't get confused between this and this. This is Fe plus 3. Fe plus 3 getting converted to Fe plus 2. So they're asking me to find for Fe plus 3. And they're asking me to compare it with Cr plus 3. Where is Cr plus 3? Cr plus 3 is here. And they're asking me to compare with Mn plus 3. So Mn plus 3 is here. Now they want me to see which is highly stable. Now let's see. Now when I have to come back to Cr plus 3, let me compare. Now from Cr plus 3 to Cr plus 2. So whenever they're asking you to find about stability, directly go into the electronic configuration concept. That is easiest way to explain. So electronic configuration, when I have chromium, now this is chromium ground state, so 3 argon, 3d5, 4s1. Now see, chromium from plus 3, if I have to write plus 3, what will happen to this chromium? Chromium plus 3 means this becomes 4s0, done. Now how many will be taken out from here? It is 3. So what is this 3? Now chromium was attained by plus 3, it has attained, let us write that. From plus 3, what did it attain? It has attained a D3 T2G set, which is stable enough. Now what is the condition? They saying from plus 3 state, it is going to accept one more electron. Yes, from 3 it is going to accept one more electron, become Cr plus 2. So to this particular state, accepting one electron. So if this accepts one electron, this becomes what? 3d4. This is D3 T2G, which is stable. Now this is going to get converted to D4, which is unstable. So will it accept that electron? Reduction becomes difficult, isn't it? It's not stable enough. So Cr plus 3 getting reduced to Cr plus 2 is not possible because it becomes unstable. So first important thing, stability wise, this is not possible. Okay, so this is my concept for chromium. So remember, this is not stable, so that doesn't undergo or that doesn't prefer undergoing reduction. So let me write the order. Now first thing, Cr is here. Now let us come back to manganese. Now manganese, they said Mn3 to Mn2. Now see, Mn3, this is your ground state configuration, take out 3. This becomes 0. 2 are gone, this becomes 4 for Mn3. This is unstable, isn't it? So now what happens? Mn3, it's going to gain one electron to forming Mn plus 2. So gaining one electron is here. So this becomes 3d5. Now what happened in manganese? First, for Mn plus 3, it has 3d4. Unstable. It is now same thing, this Mn plus 4. Okay, let us write this as unstable. Now for the same Mn plus 3, if it's trying to gain one electron, D4 becomes what? D5. Now this is stable. So will it prefer? Yes, it will prefer, isn't it? It will prefer forming that Mn plus 2 state. So Mn. Let us come back and see iron. When I have to see iron Fe plus 3 this side, I have to compare with Fe plus 3. In Fe plus 3, now this is the ground state configuration. When I have to speak about Fe plus 3, which is positive value, 3 electrons means this you're going to take 0, 2 from here and 1 from here. So this becomes 3d5. Yes, now 3d5 value is again stable. So let us write what is that Fe plus 3. So for Fe plus 3, you have for first one, like after taking out, you have got 3d5. D5, which is stable. Now after that they said Fe plus 3 to Fe plus 2. It has to further lose electrons. This becomes D4. D5 to D4. This is unstable, isn't it? So now let us compare. Now I have written all the 3 reasons. Now let us compare because they have asked me to find the stability. First compare. Now I have given the reasons. Now I have to compare both. Now which is stable? First Cr plus 3 forming stable. So chromium is that stable, isn't it? Because it is forming D3 with Cr3. Now after that Mn plus 2 from D4 it is going to D5. Highly stable because it has already attained stability reaching D5. So the first preference will be given to manganese. Greater. Done. Now I have to compare between iron and chromium. When I have to see iron, from stable it is going to unstable. From stable it is going to unstable. Both the conditions are same. But where should I see? Then I have to go to the electrode potential values. When I have to see the electrode potential values, for iron it is plus 0.8. For chromium it is minus 0.48. 0.4 minus 0.4. So when I have to see the electrode potential value, though it is positive, yes, though it's positive there, compared to this, because this condition is not isn't it feasible because this is unstable. So this condition is unstable. That is the reason compared to chromium, this is more stable. Okay, yes. So what do I write if I have to answer the second question? The ease with which iron can be oxidized as compared to similar process of either Mn or Cr. So ease, I have to first have reasoned this question, then I have to write this answer. But in this answer, what do they get? The ease with which iron can be oxidized. I have to write the order. So oxidizing property. This oxidizing property, they're asking me to write the order. So when I have to write the order, most important thing, iron oxidize first, then your Mn. Why did I take Mn? I've already told the configuration. Then comes chromium. Now observe in your reducing this in stable form, this has formed first, stable D5. Next comes chromium because T2G set. Next comes iron. So this is your order. Right. So let us see one more question. Let us apply the concept of electrode potential to this question. This is again one more famous question given. Let's see. What do they give us? The E naught of M plus 2 to M. Okay, fine. Value for copper is positive. They said, what is possibly the reason for this? Why is the electrode potential value positive and it is above the hydrogen reference electrode in the electrochemical series? They want us to give the reason. Simple, just let us write. Now, whenever you're asking or speaking about electrode potential values, your first thing which should strike you is electrode potential values or E naught is always dependent on a concept called, yes, this is dependent on a concept called delta H. I already explained in one of the questions. What is delta H? That is change in enthalpy. Okay, change in enthalpy. Now this delta H here, now this concept, let us relate to further concepts and see whether we are able to explain or not. Now this delta H is again dependent, or it is a combination of three important factors for everything, for any ion or an atom. What are they? First important thing, delta H, your sublimation, plus delta H ionization, plus delta H hydration. Now, in some cases, it depends, because this is a copper ion, isn't it? Because we have taken the copper ion. Here, we don't speak about sublimation. When do we speak about sublimation? When there's a conversion of a solid to gaseous state. So, in this case, instead of sublimation, I am going to take a concept called enthalpy of atomization. The process of converting, right? For the formation of atoms from their individual elements, isn't it? So, the atomization plus enthalpy of ionization plus enthalpy of hydration. This is the combination. Now they are asking me, why is the E naught value positive? Now what happened when I have to take the values of this delta H? HA value, or the atomization value, is 339 kilojoules per mole. Now the enthalpy of ionization 1 and ionization 2 values. How much is this value? 745 plus 1960, and the hydration enthalpy is minus 2121 kilojoules per mole. Now observe, this is atomization is positive because you're supplying, and ionization enthalpy is positive because it's going to absorb. This is also ionization enthalpy, but hydration enthalpy is amount of energy released when it forms a bonds with water molecule. So that is why it is negative. Now what happens is, when you're trying to add this value and compare with this value, the positive value is higher, isn't it? The positive value will be more compared to this negative value. Yes, so the negative value is on the whole, this is low, and the positive value, when I add all these three, is high. This is the reason when I have to compare the overall delta H value, this becomes positive. When this becomes positive, there's one important thing you have to remember. Delta H value, if this is positive, the electrode potential is also positive. If the delta H value, if you are getting negative answer, then the electrode potential value is negative. This is directly related. So now what did I get delta H value as positive? That is a reason your electrode potential is also positive. Delta E naught also is positive. This is your concept. So you can simply write delta A plus delta Hi greater than delta hydration enthalpy. So one of the question I showed you how to do the sublimation, or how to do this ionization, and how is hydration enthalpy also done. So this is how you're going to explain, and put a star for this, because this is the main concept for the whole question. So let us see this question again based on the electrode potential values. So what do they give us here? Now we are trying to relate one concept to the other, to different variations of your electronic configuration. Let us see this. Now what did we do earlier? Earlier I have related electrode potential with your change in enthalpy. Done. Before that I related your electrode potential with the oxidizing and reducing property. Done. Now we are trying to relate your electrode potential or your electronic configuration with your electrode potential. Let's see how to do this question. They're asking us, you have account for the following. You have two ions. One is your chromium ion, one is your manganese ion. Both have D4 configuration, it seems. Okay. How did I get that D4? First we'll see. Let me write the answer. Chromium, write the ground state configuration 3D5, 4s1 ground state. Now manganese is 3D5, 4s2. Now they said this is going to get converted to Cr+2. When it's getting converted to Cr+2, it has to lose 2 electrons, isn't it? From Cr to Cr+2, it has to lose 2 electrons. So 1 from here, it becomes 0, and 1 from here, it becomes D4. So now what is this configuration? D4 configuration. Okay, right, correct. Now after that, Mn. Manganese has to lose 3 electrons from Mn to Mn+3. Take out 3 electrons, 2 from here, 0, and this becomes 4 because I've lost 1 electron, 2 from here, 1 from here. This also becomes D4. So now I've written this configuration series. Now they said Cr plus 2 is strongly reducing the set. When it is reducing, what is this particular thing? Reducing means it has to accept a pair of electrons. Oxidation is loss of electrons and reduction is gain of electrons. So because they want us to prove it is reducing, from D4, what does it do? It's going to gain one electron. When it is gaining one electron, what will happen to D? It will become D3. Now what is this D3 in chromium? D3 is basically, with D normally we have 5, right? So first 3 are called T2G set and second 2 are called EG set. So now these 3 will fill the first T2G set. Now isn't it becoming stable, T2G? And after safety crystal field splitting, that this will shift above and an electron excites to the higher state. So because of D4 to D3, it's attaining stable T2G configuration. So now we'll write Cr is reducing because of conversion from D4 to D3 T2G configuration, stable. Let's come back to say manganese. Now manganese from D4, they said it is oxidizing. How can I prove that? Oxidation is loss of electrons. It has to oxidizing property, right? So what should it do? It has to increase its oxidation number. So no, oxidizing, they said. Okay, increase in oxidation number. When, how can you increase oxidation number? When you are going to remove an electron from here. When you remove an electron from here, D4 becomes D5. Now what is D5? D5 is your stable half-filled configuration. 1, 2, 3, 4, 5. Stable configuration. So that is the reason D4 to D5, it attains stability. That's why it is oxidizing. It's losing electron, reaching the stable state, D5 configuration. Let us write that. For chromium, I've written like that. Now, for manganese. Manganese is oxidizing. Why? Because of conversion from D4 to D5. D4 to D5, which is half-filled and highly stable. That's it. Because of these two, because of this, we are observing, just see, it is reducing. That's why we are getting an electrode potential of minus 0.41. If this is oxidizing, I am getting an oxidation potential of plus 1.57 volts. So this is how you have to reason your answer. Right from here, this whole thing, no need of memorizing the electrode potential values. This whole concept is important for you for writing the reason. Right, so we have done with electrode potential value concept, and let us come back and do the magnetic properties of D block elements. And later we'll finish it off with the color property. Then I'll start with your lanthanides, actinides, and then I'll be ending with your potassium permanganate and potassium dichromate. That's very, very important concept of your D block elements. Let's see. So magnetic property, when basically your D block elements, right? So this concept of magnetic or the color property depends upon your unpaired electrons. If the number of unpaired electrons are more, it's going to show or that Bohr magneton value, which is measured in Bm. If it has unpaired electrons, those electrons which when exposed to light, they get excited to the higher state. And when they get excited, as I said, they're going to absorb the particular frequency color and show that particular color of that particular ion. Now we are going to learn about magnetic moment of D block elements. So what did I say? Whenever you're speaking about magnetic moment or magnetic property, we are going to speak only in terms of unpaired electrons. So unpaired electrons, I said, right. So that is your half. This is your unpaired electron. If it is unpaired, we are going to, if an element has an unpaired electron, then we call it as paramagnetic, and if it has paired, we call it as diamagnetic substance. Done. Now this unpaired electron, we said, it's going to possess a property, or it's going to possess a magnetic moment in that, inbuilt. So that magnetic moment we are going to represent by mu. On what does this magnetic moment depend? It depends upon two important things. One is your azimuthal quantum number, and
spin quantum number. Spin quantum number.
So azimuthal quantum number is also called as what? Orbital angular momentum, isn't it? Orbital or angular momentum or orbital angular quantum number. So on these two concepts, your whole thing. But as I said, your transition elements are going to form complexes, isn't it? Coordinate covalent complexes, as we have seen in nickel tetracarbonyl, pentacarbonyl ferrate complex, isn't it? It's going to form a coordinate complex. But now what is happening in nickel complexes or coordinate complexes? You have your metal atom and your ligands surrounding this metal, bonded. Now what are these? All these are electrons, isn't it? Electrons. So all are paired. When it is paired, the concept of azimuthal quantum number is ruled out. Only left is your spin quantum number. So because they formed complexes, I am going to speak only in terms of spin quantum number, and the formula for calculating the magnetic property of the magnetic momentum using is for spin quantum number. I said spin only because azimuthal is ruled out. The leftover spin quantum number, the formula is mu is equal to under root n into n plus 2. Now this n is your unpaired electron. N is unpaired electron. Okay, simple concept. Nothing big or nothing much to learn in this concept. Only thing I have to see is, from this number of unpaired electrons, I am going to calculate the magnetic moment of that particular compound. That's it. Simple, particular ion, not compound, ion. So now with this concept, with this basic data, I am going to start solving a question. Let us see how is it given in the board. Very easy question given under magnetic momentum. What does it say? The magnetic momentum of cobalt plus 3 is greater than Cu plus 2. Now they said I have to prove this using this formula. Now there's a cobalt. Okay, cobalt ground state 3d7 4s2. Copper ground state 3d10 4s1. Now when I have to take out cobalt plus 3, so cobalt plus 3, how much it becomes? I'm going to take out 2 electrons from here, so this becomes 0. I'm going to take out 1 electron from here, this becomes 3d6. Copper, what did they give me? Copper plus 2. I have to take out 1 electron from here, this becomes 0. I have to take out 1 electron from here, this becomes 3d9. Now fill in the electrons. 3d, I have to calculate the number of unpaired electrons, isn't it? 1, 2, 3, 4, 5. This is 3d. How many? 6. First half filled. 1, 2, 3, 4, 5. Then 6. What is the number of unpaired electrons here? N is equal to 4. Done. Let me calculate here. 3d9. 9, 1, 2, 3, 4, 5, 6, 7, 8, 9. Number of unpaired electrons is 1. Now apply this in the formula given and calculate the Bohr magneton. So what is this Bohr magneton? The unit for magnetic moment. B, capital M. Now let us substitute in this formula. Mu is equal to under root 4 into 4 plus 2. Here mu is equal to under root 1 into 1 plus 2. When you solve this, I think you'll get an answer around 4.9 or something. Yes, Bohr magneton, capital B, capital M. So what is Bohr magneton? BM, it is Bohr magneton, unit for calculating magnetic moment. Solve this particular thing, I get an answer of mu is equal to 1.7 Bohr magneton. Now using what did I do? I have compared two things. First, I have got an answer for cobalt plus 3 as 4.9 bm, and for copper I've got an answer of 1.7 bm. So isn't it greater? Hence CO plus 2 is greater than Cu plus 2. So CO plus 2 is greater than Cu plus 2. Hence proved. This is how you're going to use this formula and show the value is more than the earlier one. Right. So let us come back and do this. This is again an NCERT question, but the easiest question I should say in the magnetic moment. Only thing is you have to, the atomic numbers will be given for this question. You need to write the configuration using Apwork principle. Write the configuration and your work is done. So what should I do in this question? They've asked me write down the number of d electrons in each of the following ions. Okay, they've given us a list of ions. And I have to write after removing those electrons how much, what is the leftover d electrons, and how would you expect the 5 3d orbitals to be occupied for these hydrate ions octahedral. Okay, this is important. Now basically when you study your coordination chemistry, you have octahedral complexes, tetrahedral complexes, right? In that you're going to study a theory called crystal field splitting or CFT. In that crystal field splitting, you have two types of crystal field splittings. One is the d orbital being degenerate, they're going to split or follow the octahedral splitting and tetrahedral splitting. Now they're asking us, they're relating this concept to the octahedral splitting there. What is that? In octahedral, if I have to say, and in tetrahedral, just observe, if I have to take the octahedral splitting of d orbital, how does it split? D, I very well know, it has 1, 2, 3, 5. Here also. Yes. First 3 are T2G set, second 2 are EG set. Here also the same. First 3 are T2G set, the second 2 are EG set. When octahedral has to split, remember the splitting, octahedral first the lower energy would be T2G set and the higher would be EG set. So the triplet set would be lower energy. That means in octahedral, T2G would come first and then comes EG. In tetrahedral, EG would be of the lower energy and the T2G would be of the higher energy. The sequence is this. Remember the sequence. Now what should I apply? I have to apply T2G concept here. I have to apply octahedral splitting. So that is what they said. Okay, let us start. So now I know octa means T2G comes first and then EG. Now this ion is given to me. I have written the electronic configuration to save time. It's easy for me to take out and do the numerical fast. I have to take out 2 plus 2. Remove plus 2 from here. This becomes 3d24s0. The number of unpaired electrons are how many? 2. Correct? Because they've asked me to find the number of d electrons. So number of d electrons are 2. Now how does this go and fill? First it has to fill T2G, no? Right? How will you write? You're going to write T2G2. You have to write the 2 above. Let us start for this. Now V plus 2. So this becomes 3d34s0. So 3. How should I write? T2G3. Because first T2G only 3 will fill and then you have to go to EG set. Now here chromium 3. So remove this becomes 4s0. This becomes now 1. The 3 will be left. Number of unpaired electrons 3. So T2G3. Mn plus 3. 4s0. 3d4. Now it has become 4 electrons because 1 from here, 2 from here. 4. How will you write? T2G already 3 electrons are filled, isn't it? Half filled. Don't start filling it, please. So T2G is 3 electrons. 1 electron will go to the EG set now. EG1. Let us do for this. Iron. 4s2. So 4s0. This becomes 3d6. How many unpaired electrons you have? 6. Fill in. T2G will always be 3. EG will always be 3. For Fe plus 3, remove 2 electrons from here. This becomes 0 and 3d6 becomes 3d5. How will I write that thing now? 5 unpaired electrons. So start filling. T2G will be 3 and your EG, distribute those 2 here. So let us write for cobalt now. Cobalt, when I have to take cobalt, how many? 2, isn't it? This becomes 4s0, 3d7. Now, how many unpaired electrons do we have? We have 7 unpaired electrons. Now, careful. Here what happened? Now you have filled 3 here, then you have filled 2 here. Done. Now it started pairing up. Yes. Now how is this pairing up done? Yes, still here. Okay, this is 5. No, this is your 1, 2, 3, 4, 5. Till here, I just took T2G like this and EG2 like this. Now what happened? I have 7, isn't it? Now thus that electron will come and fill the T2G set, the second electron, that is the sixth one. Now 7th one like this, the second electron. Now how many do we have? We have T2G total of 5. So T2G will be 5, EG will be 2. Let us come back and do for nickel. Nickel 2. This is 4s 0. 3d 8. So 8 electrons. So how will I fill again 8 electrons? Same thing again. Now let me write here. Yes, 1, 2, 3, 4, 5, 6, 7, 8. So T2G. How many do we have? This is T2G. This is EG. T2G has 6 electrons. And EG has 2 electrons. Done. We're almost coming closer. Copper plus 2. So you have to remove 1 electron from here. This becomes 3d9. Number of unpaired electrons are 9. So how will I fill this? Now 8 are over, isn't it? The 9th one you're going to fill here. So what do I get? T2G has 6 and EG has how many? 3. So this is how you're going to write for all. Important thing is configuration, taking out and filling. Right. So let us do one more question on your magnetic moment. Now this is again your NCERT question. Let us see how to solve this question. So these are the different variations of using the magnetic momentum formula, the spin only formula. So root n into n plus 2 under root. We have used it in calculating the Bohr magneton. Then I've used that thing in calculating the ions. Ions were given. From that again I calculated Bohr magneton. Now they've given me Bohr magneton directly and they've asked me to find out or infer what. Let us see what can be inferred from the magnetic moment values of the following complex series. Okay, nice. They've clubbed coordination chemistry chapter and your D and F block element here. Let's see how to do this. Suppose if this question is given to us, they've asked me from this Bohr magneton value of this complex, what do you infer? What can you, what information can you get or gather from this? Let's see. Now let us pick up first example. Example 1. Now example 1 is K4 MnCN6 and the Bohr magneton given to me is 2.2. Okay, not a problem. I'm not you. No, for me, let's see how can I use that. Now when such particular example is given to me, now this is your metal atom, this is your ligand, and this is also this one which is outside the sphere. Now this metal atom, the 6 ligands are going to donate electrons to this metal atom. Done. As soon as such complex is given to you, first try to calculate the oxidation state. Manganese is X plus 6 into minus 1. Yes. Now your K is also there. You have to write that this one also. Okay, it's 4. Okay, done. Solve this. Is equal to 4. X is equal to plus 2. Done. Now this is your oxidation state for manganese. Now when I'm going to write this manganese with the configuration which I've got is D 2 electrons plus 2 means Mn plus 2. Pick up the configuration of manganese. It is 3d5 4s2. You're going to take out 2 electrons from here. This becomes 0. Now what do you have? You have d5 configuration 1 2 3 4 5. Now come back to the complex. This manganese has to form a bond with ligand. Now what type of ligand is this? This ligand Cn minus is a strong field ligand. What is a strong field ligand? Strong field ligand, when it has to bond with the metal atom, it's going to pair up the electrons because it is strong field. You have strong field ligands, weak field ligands and neutral ligands like ammonia and water. So it is a strong field ligand and it's going to pair up the electrons. How does it pair? This will pair up with this will shift here, this will pair up again and left over. Let me see how can I pair up. So it is a strong field ligand and will pair up. How does this pair up? Mn plus 2. So this club together paired. Okay, 2 are gone. This club together paired. And we are left with one single. So what is this now? D. Now once this is left out with the empty orbitals, your Cn is going to come and occupy. How many do we need? We need 6 Cns to come and form a bond. How many are there? 2. So this is your 3D. Next comes your 4s. Next comes your 4p. So cyano will come and occupy here. 2, 3, 4, 5, 6. 2, 3, 4, 5, 6. 6. So now what is this hybridization? This is D. I've already written. So this is D2sp3 hybridization. Okay. So now what are we inferring? With this data given, we are calculating or we are trying to find the type of hybridization. Now how many are there? 3 plus 1, 4, 5, 6 total. So 6 means what is the geometry of the complex? It is an octahedral complex. Manganese with 6 cyano on all the sides. So this data is helping me to find out the shape of the molecule or the shape of the complex. So tetrahedral. So what do we get for this complex? I have got a configuration of D2sp3 and I told it has an octahedral geometry. Let us come back and do the next one. Fe water 6 plus 2. First calculate the oxidation state X. Now here 6 into. Now what is the mode or the type of water molecule ligand? Water is a neutral ligand. As I said, ammonia and water are neutral ligands. So the charge on water is 0. So write that here plus 2. So X. So this is 0. The left is equal to plus 2. So what do I have? Fe plus 2 oxidation state. Write that configuration for iron. It is 3d6 4s2. For plus 2, this becomes 0. Now, how many D you have? 6 electrons. How many unpaired electrons? 4. Okay. Now, this has to accommodate water molecule to form bond. But we very well know water is a neutral ligand and it is not going to pair up. No change. Nothing, because if it is a strong field ligand, it is going to pair up, but this is neutral, it will not pair up. So we are going to go to the next state, 3D, 4S, 4P. Okay, how many do I need? I need 6, isn't it? So 1, 2, 3, 4, 5, 6. I need D also. D. So now fill 1, 2, 3, 4, 5, 6. What type of hybridization did I get? I have got hybridization of sp3d2. Total how many? 3 plus 2, 5 plus 1, 6. So this is also an octahedral complex. So first one, what did I get? Well, let us take out this water. First one, I got octahedral complex D2sp3. The second one also I got a shape was octahedral complex with outer complexing, that is sp3d2. So let us do the next one. Third one. Third is K2MnCl4. You have to be very careful in copying the charges. If you copy the charges wrong, your answer whole thing will be wrong. Now, manganese is given X. Okay. Plus 4 into minus 1. is equal to minus 2 x. I've got 2. Now, what is the valency or the charge? It is Mn plus 2. Write the configuration. 3d5 4s2. Take out 2 electrons from here. This becomes 3d5. How many should it accommodate? It has to accommodate 4 Cls. So 3d 4s 4p. 1 chlorine here, 1 more chlorine here, 1 more chlorine, 1 more chlorine. What is the hybridization? These two will hybridize. So hybridization is sp3. 3 plus 1 4. The shape of the molecule is tetrahedral. So what did I get now? For the last complex, I have got sp3 hybridization and the shape is tetrahedral. Done. So this is how you're going to do for the first one, second one, third one. First step, calculating oxidation number. Second one, filling the electrons. Third one, based on the charge, removing the number of electrons. Fourth one, writing the type of hybridization. No, you have to see whether it is strong field ligand, weak field, or neutral ligand. And finally, you're going to write the shape of the molecule. Right, so let us see 2 more questions based on your magnetic moment. It's the same concept, you're applying the same formula but different types of questions. So what do they give us? The paramagnetic character in 3D transition series elements increases up to manganese and then decreases Y. Okay, fine. So whenever we speak about 3D series, your 3D series starts from scandium, and it ends with zinc, isn't it? Now till manganese, which shows +7 oxidation state. Yes. Now when I speak about till manganese, manganese is the cutoff point because here maximum till +7 you get the oxidation state. Now it's going to start from 3 +7. It goes to +7. Again comes back to +2. Now what happens from scandium till manganese? You're trying to fill one electron every time till it reaches D5 configuration. Correct. So there from scandium, everyone scandium to manganese. You are filling 1 electron to this. Again one more till it reaches your D5 configuration. Now once this D5 is reached, from manganese to zinc, you start filling or you start pairing the electrons. So till D5 what happens? They are paramagnetic. Why are they paramagnetic? Because it is half filled. After D5, once D5 all is filled, now you start adding electron. But which rule do you add? You're going to add electron here by Hund's rule of maximum multiplicity. You're going to apply Hund's rule of maximum multiplicity and start pairing up this electron. Now D5 then becomes D6, D7, D8, D9 and D10. So finally when it comes to zinc, this attains D10 configuration. When it is reaching D10 configuration, what is this property? It is diamagnetic in nature. It's completely filled, diamagnetic. So what are we trying to explain? We are trying to explain that the paramagnetic character in 3D series, okay, this is a 3D series. In this 3D series, it increases up to manganese. Okay, it increases up to manganese because the configuration, okay, according to the atomic number, I'm filling the electron. First 4 is, then I'm filling 3D one after the other, and I've got till Mn half filled. After that, it decreases. Why is it decreasing? Because I started pairing up the electron. After D5, I started pairing up one after the other. So please use pairing up. Pairing up, use this word please. Pairing up occurs according to Hund's rule of maximum multiplicity. Hence, paramagnetic behavior now becomes diamagnetic behavior. Simple. That is what you have to going to write. Now let's see this question. Use Hund's rule to derive the electronic configuration of cerium ion and calculate its magnetic momentum. Simple. Atomic number is given to you, 58. I have to calculate the Bohr magneton or the magnetic moment mu. So write the configuration. Cerium, atomic number 58. So xenon, it comes under xenon. Okay, xenon configuration. This comes your 4f electron starts entering, so 4f. After 4f, then 4 come after that 5d. After 5d, 6s. Now fill the electrons configuration 4f1, 58 isn't it? 0 4f1, 5d1, 6s2. Done. Now they ask me to take cerium plus 3. So when I have to make it cerium plus 3, you're going to remove 2 electrons from here. This becomes 6s0. 1 electron from here, 5d0. So xenon is like that, and in 4f you have 1 unpaired electron. 1 unpaired. So f, how many unpaired? 7 isn't it? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7. In F you have only 1 unpaired electron. So now your N is 1. Now substitute this 1 in your spin formula, because they have asked me to use spin only formula. Spin only formula is mu is equal to root of N into N plus 2. Spin only formula. So when I have to apply this, I get 1 root of 1 into 1 plus 2, which is equal to 1.73 Bohr magneton. I get an answer of 1.73. That's simple, isn't it? I've got, what did I do? They've given me cerium. I wrote, the atomic number is given to me. I wrote the configuration. I took out 3 electrons from here. From that, I got an unpaired electron. That unpaired electron, I applied in spin only formula and calculated Bohr magneton, that is 1.73 is the answer. So my work is done, isn't it? I've used Hund's rule and I've derived from the configuration. Right, so let us come back and see the next property of your D block elements, that is alloy formation. So we've already seen the list of catalysts with the D block elements form. So now, we already studied in grade 10 what is alloy. A combination of 2 or more metals is called alloy, right? So why do D block elements form alloys? That is a concept basically. Very simple, nothing big to remember. So when I speak about D block elements, when I have seen the trend in the atomic radii. The atomic radii, we hope you would have seen that video. The 3D, 4D and 5D series, very close, isn't it? The 3D series, 1 next 2, 3, 4 like that. The atomic radii variation for 3D, okay, 4D in this way, very close. So here D block element basically, if I see the variation in atomic radii is very less. So variation one after the other, variation in atomic radii is very less done. When it is very less, what happens? That particular metal atom, you have a lattice, isn't it? So because of this, the size variation, I can introduce or inculcate some other or combine one more type of metal atom into the lattice of that particular D block element, and you can, with the combination of 2 or more alloys, as I said, suppose I take iron lattice, the lattice size or the radii, it easily fits other also, because the immediate elements, isn't it? It will go at the other metal will come and incorporate, and this will go and incorporate, that will go and incorporate. In that way, together they form an alloy combination, and which is used for different purposes. So most important thing, variation of atomic radii is very less. So what will happen? Hence, it can fit other metal atoms into their lattice sites or crystal lattices, forming alloys, which is a solid substance here, solid substance metal, right? So here I listed out a few examples of, this is not required, okay, few examples of your alloys. So why did I write this? Basically, they mostly ask you what is mish metal, right? Here I've already written mish metal is a rare combination of it is a combination of rare earth metals, that is your lanthanides, and here just see, cerium 25%, lanthanide metals 5%, iron and traces of sulfur, carbon, silicon, calcium and aluminium. So the uses of this also are given. So here this tabular column will help you. Please note it in your books. They may ask you for one metal, what is mish metal, or what is the composition of bronze metal, what are coinage, what is coinage, composition of coinage silver. They may ask you what is gunmetal, what is the composition of gunmetal. But the concept is, this is your concept, and the uses, I hope there's nothing to explain in given this, you try to note the alloy composition. If everything is clear, I have given the alloy, type of alloy and the composition in that, and use. Again, everywhere this mish metal is very, very important. Please learn it, practice it 5 or 6 times. The composition: cerium 25%, lanthanide metals 5%, iron, traces of sulfur, carbon, silicon, calcium and aluminium. And it is used for your this in bullets lining also they'll use it. So please note it carefully. So let us come back and learn the catalytic property of D block elements. Now basically we already said D block elements, why do we call D block? Because the electron enters into your N-1 D subshell as well as Ns, right? Now when the electron every time keeps adding to this D block element, it's going to show variable oxidation state, isn't it? It's going to range, when I speak about scandium, from +3, it's going to range till +7 also in 3D series. So because of this variable oxidation state, this D block elements are going to act as very good catalyst. How are we linking between catalyst and oxidation state? Let's see. Now when I have to take a D block element, right? So first, what is the role of a catalyst? Catalyst is something which is going to speed up the reaction. Correct? It has to lower that activation energy. Now this is your activation energy. Your catalyst will lower the activation energy and try to form the products. Now without catalyst, suppose if I take a catalyst, lower, and if I take a catalyst, it's going to take such long barrier and then form the products. So first most important thing is your transition metal elements have active sites on the surface of these metals. So what is the role of active site? So this active site, it allows the other metal atoms to come and fix into the active sites. When they fix into the active sites, that is indirectly the catalyst, this transition metals, once these other metal atoms come and fix, the activity of that catalyst will become so high that it tries to form a complex. After forming the complex, what does it do? Before reaching, now I said this is forming a complex. This complex, before reaching the activation energy barrier, with low EA only, it's going to cross the energy barrier and form the products. Right? Now what is this concept now? I said it's going to form an active site. Now it has many oxidation state variable. That means it can fit any number of atoms into that particular, accept that number of atoms, and finally form a active catalyst. That is what is the concept. So this particular list of catalysts given here in your exam, they will not ask you nothing. They may ask you for 1 mark question, what is Lindlar's catalyst, or they may ask you what is the catalyst used in Ostwald process, 1 mark question. But important concept is, why do they act as catalyst? Point number 1, they have variable oxidation state. Yes. Point number 2, they have active sites because of this variable oxidation state, to which they are going to lower the activation energy. And you can note all these things, catalysts, and please memorize it for the exam. So before I end that video, let us write the variable oxidation state, participation of D subshell, presence of active sites, and most important, lowers activation energy to form products. That's it. If you write this, the whole concept of catalyst is easy. Right. Let us come and start with this topic, oxides of transition metals. Now basically in oxides, or when such compounds are given, there are 2 types of questions asked. That is either calculation of oxidation state of the metal atom, or there will be one more reasoning question which I will be doing it now. So nothing to remember. They will not ask you to write what are the oxides, no. But just for your information, I have just made it in the tabular column. Let us calculate the oxidation state. So when I have to calculate the oxidation state of this particular manganese, oxygen we very well know, no, it is -2. So manganese is obviously +2. Total is 0, isn't it? Right. Now when I have to calculate for this, here oxygen is -2 as it is said. they'll ask you to calculate oxidation state of the metal atom only. Now here, when the total charge on oxygen is -8, when I have to write for such particular metal atom, just do fractional balancing. How? This whole thing is -8. This will be +8 by 3. So when it is +8 by 3, this 3 and this 3 gets cancelled. Correct? So the leftover is 8. So this -8 and +8 balances. So total is +8 by 2. Now for oxygen here it is -2. So 3 2s are -6. So this also should be +6. If I take this as +3, 3 into 2 +6, and this becomes -6. So the oxidation state would be +3 for manganese. Now here if I have to try -2, -4 here, so this will be +4. Here when I have to see, this is 14. So for one manganese it is +7, isn't it? So because +7, 7 into 14. So this is how you're going to calculate. Now let us come back to one more concept. First, in this particular oxide, manganese oxide is the highest what do you say, ionic compound in this. This is ionic in nature, this is highly covalent. So highly ionic oxide, and this is highly covalent oxide. Covalent oxide. Now when I have to see this, this is basic in nature, this is acidic in nature. 1 2 3, these 3 are amphoteric in nature. Amphoteric, this also is amphoteric. Now why am I trying to teach you all this is so amphoteric we very well know. I call an oxide as amphoteric when it reacts both with an acid and a base. Correct? Yes. Now question asked on, what is the question asked on this particular concept? Now as we go down the group, what is happening when I'm moving down or when I'm going to the higher oxides? Now the oxidation state of manganese is +7. Here the oxidation state of manganese is +2. What is happening when the oxidation number or the oxidation state of the oxide or this particular metal is increasing? Why is the acidic nature increasing? That is the question they're going to ask you. So let us write once again this particular thing. Let me erase. So I have to write this question and answer that question. That question is very important. Let's see. So how to frame that question? Why are higher oxidation state metal atoms, okay, in this case it is oxides, isn't it? In this case metal oxide are acidic in nature, or okay, highly acidic in nature. Okay, let me pick up a particular example, simple example, and explain you. Now when I felt this example is also easy for you. Now Fe, iron exists as two forms, Fe+2 and Fe+3. Now compared to these two, this is higher oxidation state, just like manganese. So in manganese, what did we get? We have got Mn+2 and Mn+7. Correct? Now they said this higher oxidation state metal atoms are acidic atoms. Why? Let us prove. When this iron is forming a complex with water, okay, it's going to form a complex with water +2, as well as it's going to form a complex with water +3, both the oxidation states. Now what happens here? This is important. Oxygen being highly electronegative, what does it do? Now this is here, this is going to link like this. Just let us see. HO, just see, water. Oxygen being highly electronegative, it's going to drag the electron density from hydrogen. It's going to drag that electron density to that extent that this whole thing, just observe, this electronegativity which is there, when it's trying to drag the electron density, there is a difference in the charge density. When there's a difference in charge density, automatically there is a cleavage of the bond. When there's a cleavage of the bond, the release of H+ ions becomes difficult. Yes. Now what is this concept here? This size. What are the two factors? Your Fe in its higher oxidation state, two important things. One is charge is high and size of the atom is small. These two are the important things. Yes. Now observe. High oxygen is trying to drag the electron density towards it. Now, iron being the higher charge and being a smaller atom, the nucleus of this iron also tries to attract the electrons towards it. Now what happens? There's a lot of electron density created here, and due to the charge difference, or the electron charge density difference, the H plus from here is released out. When something releases out H plus, isn't it highly acidic? Yes. Let us come back and write the answer. How to write this answer? So this is your concept. Now first important thing when you're writing such answers, first thing you have to write is yes. Let us pick up. In given example, Fe plus 3. So what are the two things in Fe plus 3? Charge is higher, size of atom is smaller. Done. When the size of the atom is smaller, nuclear force of attraction, or Z effective will be is greater. Done. Now the linked oxygen, whatever is there, the oxygen which is linking iron is highly electronegative. When it is highly electronegative, it tries to, what does it do? It's going to it'll try to drag electron density. It tries to drag electron density from hydrogen. So thus release of H plus becomes easier, and hence it is acidic in nature. It is highly acidic in nature. So that is the reason when I compare between the first oxide MnO and when I compare the last oxide, that is Mn2O7 is highly acidic compared to MnO. This is how you're going to reason the answer. Now let's come back and see for vanadium. When I have to speak about vanadium, nothing, just for your information, your vanadium it's going to show even V2O2 also is one of the oxide. Yeah, so highly basic. We have also seen in manganese, basic in nature, basicity decreases down, and finally again you have an amphoteric oxide. So this basic oxide, when you dissolve it in an acid, it's going to release, or acid plus base gives me salt, isn't salt plus water. So when you're dissolving this basic oxide in acid, it's going to form a salt which forms this type of cation. Done. Now the same thing here, if you are dissolving it in an acid and a base, because it is amphoteric, it's going to release or form two types of one is your cation, one is your anion. The formation of these two ions, just for your information. Why? When they ask you what is a ion formed or what is a salt formed when the less basic vanadium tetraoxide is dissolved, you can write that answer. So this is how you will be questioned, either the oxidation state or the reasoning question in oxidation state or oxides of transition metals. Right. So one more property of D block elements, that is your interstitial compounds. So in solid state we have already studied what is an interstitial space, right? Interstitial is nothing but the vacant space present. Right, vacant space. The other name given is void. Right, we have already studied there are two types of voids. One is your tetrahedral void and octahedral void. How many tetrahedral voids we have? 2, and octahedral void is 1. Now, as I've already said, in your D block elements, the atomic radii variation is very less. When I compare scandium, titanium, vanadium, chromium, like that, one after the other element, the variation atomic radii is very less. So because of this less variation, I can easily fix a smaller atoms, like, or because of the voids also present in that particular metal, smaller smaller atoms like hydrogen, carbon, nitrogen, yes, sulfur, all these can fix into the lattices, right? When they fix into the lattices, they try to form different types of compounds. Those are interstitial compounds. So let us write, what did I say? Now, interstitials are vacant spaces or voids. Now, what happens due to less variation in atomic radii, then what will happen? And that atomic radii also we already know they have voids also present because the disturbances created, dislocations created atomic radii, and due to dislocations, gaps, dislocations are gaps. If you don't remember that, you can write gaps. Smaller atoms like hydrogen, carbon, nitrogen, sulfur, they go and fix into the lattice points. They go and fix in the lattice points in between. So when they fix in the lattice points, they form different types of carbides, or depending upon if it is with carbon, carbides, or if it is with nitrogen, nitrides. So here I've given you a list of carbides. Those are interstitial carbides because the combination of transition metals with the carbides. So 1, 2, 3, 4, like different. Now here for chromium, manganese, when they combine with in the presence of sulfuric acid, they just form hydrogen hydrocarbons. So why did I give this data? Because in the exam, if they ask you by chance list out any two carbides of the transition metals or list out any two interstitial compounds of transition metals, these examples will be useful for you, which is an extra information for you all. So if they ask you why do they form this, if they ask you why do they form this reason, if they ask you for examples, this one you can give. Now what will happen, because of the formation of the smaller atoms or introduction of smaller atoms, the transition metal atom or that particular compound becomes very hard and very strong enough, right? So because of this, it attains the particular compound is hard, right? Hard, okay. If I say strong also, rigid rather, if I have to first specifically say, they're rigid in nature. So such, for example, one more compound like cast iron, right? Very strong enough, isn't it? So that is also an interstitial compound, isn't iron incorporated with your carbon atom. So this is your information. I think I've completed your D block perfectly without leaving any part of your D block chapter. I'll be coming into now compounds of D block, that is KMNO4 K2Cr2O7 potassium dichromate. But before doing that, because KMNO4 and K2Cr I have to teach you perfectly so that you will not lose those marks, I'll be starting with lanthanides and actinides and then finish off with potassium permanganate and potassium dichromate, and then we'll be completing your board papers. Then I'll be starting your new chapter. Yes, let us come back and learn the color property of D block elements. With this color property, your D block will be done, and we'll be starting with the lanthanides and actinides, that is your F block element. So whenever I speak about color property, the most important keyword which we have to remember is wherever it is, whenever you're speaking in F block also, in F, if you're speaking, you have to speak in terms of FF transition. Here you're going to speak in terms of DD transition. Yes. So most important two keywords which you have to remember in color property is, why does a particular metal ion exhibit color? If they ask you this, first keyword is due to DD transition. We'll see what is DD transition now in a few minutes. Now, after that, why is it showing DD transition? Because of the presence of unpaired electrons. This is important. And if they're paired, a concept of color only would not exist with unpaired electrons. Now, so color property basically in D block elements, as I said, the electron enters into the n-1 d subshell. Yes, every time. Now, when it is entering, now basically when I have to speak about D, now I said, okay, n-1 d subshell, and then is your ns, correct? Now, whenever your electron is trying to enter here, it's 2. Hello? Right, so your d orbitals we have, or these d orbitals, what do they have? They have a 5. It has like this, isn't it? 1 2 3 4 5. 1 2 3 4 5. Now the first 3 are called T2G set, and the next 2 are called EG set. T2G stands for triplet degenerate set. and EG stands for doublet degenerate set. Degenerate set. Now what is this degenerate? Degenerate is something which are of all equal energy. All the 5 are of equal energy. Now what happens when this particular thing is exposed to light and photon is exposed to that? This is going to break up into 2 sets. One is T2G set at the base and EG set above. Now here when I said unpaired electron, correct? This unpaired now, and the energy difference between T2G and EG is very less. Yes, so when a photon of light is exposed on this, the electron is going to excite. Suppose if it is like this, right? One electron from here goes to the excited state of EG, and during this process, as I said, the energy difference is very less. Once it gets excited, it's going to absorb a light of frequency from which spectrum? From visible spectrum. So according to that frequency, it's going to absorb light for that particular whichever metal atom, that particular frequency. Once it absorbs color or light or that particular frequency, it's going to show different colors. Now let us come back and see. When I have scandium, in scandium it doesn't have 3 electron, isn't it? 3D, because it has already lost. What is the configuration? 3D1 4s2. It has already lost all the electrons. No electron can excite, so it is colorless. Now based on the number of unpaired electron, each metal atom is going to show different colors. Just see different colors. Yeah, here 3D7, number of unpaired electrons are 3, so it's going pink in color. If I have to come to zinc, again 3D10 4s2. There are no unpaired electrons, all are paired. Because all are paired, the number of unpaired electrons is 0 and it is colorless. So most important thing is the excitation of electrons from T2G to EG set. This transition from T2G to EG is called DD transition, and based on this DD transition, it's going to show color. So simple, I have given you, whenever they ask you why is this colored, why is that not colored, simple, take the configuration, write the number of unpaired electrons and say because of the presence of number of unpaired electron, it goes from the ground state to the excited state every time. It is octahedral complexes, isn't it? They form octahedral. Octahedral, it is T2G, EG, right? So you can start this concept 1 and 2. Second concept, show them what is this T2G and EG. Done. After that, whichever example is given, take that example, take the configuration, show how many are there, see how many are going to the excited state, and write that particular color. Yes, so color also will be given. So this is your concept for color property. Please note everything. 1, 2, 3, 4, 5, 6. Very important. Yes, so let us come back and start with your F block elements. We have completely done with the D block elements. Every topic which is required for your board exam I have done with n number of questions, numericals also based on that, reasoning questions also. Please practice D and F block perfectly, because I think 99.99% I have done. If anything else is left out, if I find any other reasoning questions very interesting and required for your board exam, I'll be surely covering it on the revision session in the month of February. Yes, so whenever I have to come back to F block elements, so here F block elements are also called as inner transition elements. Inner transition elements. Okay, yes, in this inner transition elements, D block we said transition elements, F block is inner transition. Under F block you are also going to study 2 categories. First category are F block elements. The first category is lanthanoids. Yes, here actinides. So when I have to speak about the general class or category of F block or general electronic configuration of F block elements, as I said, in D block, the incoming electron enters into n-1d subshell, isn't it? Now here, when I have to write GEC, that is your general electronic configuration. Just see, simple. Start with your NS outermost. It is 2 here. Then come back to the penultimate shell, n-1d, it is D, it's 0 to 1. Only because according to the configuration, it's going to fill till 1 only. And come back to the inner shell, n-2, F, it is 1 to 14. The maximum is 14, isn't it? Yes, so this is your configuration. Now what is this? Here NS is your valence shell, right? n-1d is your penultimate shell. penultimate shell. N minus 2 F is your anti-penultimate shell. Right, where are these present? If I have to anti-penultimate, this is your nucleus, if I take, now if I draw like this, yes, now this is your, suppose if I write it as 1, 2, 3, right, now this is your NS, this is your N minus 1D penultimate. Now this is your N minus 2 F anti-penultimate shell. Done. Every time an electron keeps on adding F1, F2, F3, F4 like that till it fills, till it goes to completely fill F14. So when I have to write the lanthanide general configuration, so GEC, right? Now I said it is NF. I have written N minus 2 because I have to show the next inner level. So you can write as NF. Now this belongs to your 4F series, 4F. After 4 it will be 5, isn't it? After F it is D. After 5 it is 6. It is S. Now in actinides this 4F becomes 5F. 5D, 6D, 6S, 7S. Now fill the electrons. F, what is the thing? It is 1 to 14. 5D is 0 to 1. 6S is 2. Here also same. 5F 1 to 14. Last element lawrencium. 6D, if I have to say, it is 0 to 1 and 7S is 2. Yes. Now lanthanum is going to start from the first element would be lanthanides, which start with the first element lanthanum, because it's going to show the properties of lanthanides, hence starting with lanthanum, so we call it as lanthanide series. Now lanthanum atomic number is 57. After this would be, after including this would be 15 elements, but after this 14 elements. That means lanthanum plus 14 elements. Means in a lanthanide you have 15 elements in the series. It ends with this an element called lanthanum to lutetium. 71 is the atomic number. Yes, total of 15 elements. Now if I have to start with actinides, the first element is actinium. It's going to follow. After this there are 14 elements in the series which I'll be dealing. It's going to end with lawrencium. LR. Atomic number 89 and here it is 103. So now I'll be dealing with the complete F block element. What should you learn for the exam? For your exam, you are going to learn, first important thing, differences between lanthanides and actinides. Most important. I'll be listing out 12 to 13 differences. Please learn those. Maybe they may ask you from any corner of that particular difference. Next, you're going to learn a concept called what is lanthanide contraction. Very important. Easy also. All are important rather. Yes. Next, they may ask you what is in uses of lanthanides, what is mish metal. I've already done this in alloy. And if they ask you chemical properties of lanthanides and actinides, all these are a part of your chapter which I'll be dealing, right? So let us meet again with your differences between lanthanides and actinides. Yes, let us come back and start with the differences of your lanthanides and actinides. I said this may be asked this year. Let's see. We will try to write the examples for everything. I'll be listing out almost 13 to 14 differences. In that, how many ever you can learn. You can at least minimum 7 to be learned in. You have to go to the exam at least 7. Minimum should be 7, right? So what did I do? I have differentiated lanthanides and actinides, and I've written the properties on one side. So please try to write the properties like this, so that it's easy for the examiner to give you marks then and there, because they will know what criteria you are differentiating the lanthanides and actinides, right? So when I have to write the general configuration of lanthanides, as I said, lanthanides and actinides, the incoming electron enters into F orbital. Yes, so here the electron enters into 4F. Here it is 5F. After after 4 we get 5, which is 5D. Now here it is 6D. After 5D, 6S. Here it is 7S. Simple. Now start filling the electrons. I said F 1 to 14. General configuration I told, isn't it? Now D, I said it is between 0 to 1. And S, as I said, it's going to be fill 2 electrons. So this is the configuration, general configuration for, this is n minus 1 and this is n minus 2. Done. Now when I have to write the configuration for actinides, the same thing, 1 to 14 here, same thing, 0 to 1 here, and 7 is 2. So this is all the 15 elements which follow this sequence while filling the electrons. Now when I have to come to the shielding effect, right, I have to compare both, isn't it? Now you have to compare between 4F and 5F. Yes, compared to 5F, 4F shielding effect is like compared to 4F. Otherwise, because of the improper shielding, it's going to show lanthanide contraction. But compared to that, 4F shielding is higher than 5F. Okay, so right now 5F has poor shielding effect. I'm comparing both. I'm not specifically writing, comparing both and writing. Now when I have to write the density, so density we very well know, we measure in gram per centimeter cube. So try to write the values and mention the units also. So here they are very dense basically. So density is equal to mass by volume, isn't it? Now the density value of your lanthanide series, it's going to start, or the value is going to start from 6.7 gram per centimeter cube to 9.7 gram per centimeter cube. Yes, now so much. So that is the reason I said density, they are denser metals. Now when I have to come back to actinides, your actinides, the density ranges from 10 gram per centimeter cube to almost 12.2 gram per centimeter cube. 12 gram per centimeter cube. Right, so that's why we call it as very dense compared to that, very dense metals compared to that. Yes, when I have to come to melting point and boiling point variations, right, actinides have very high melting and boiling point. So let us write that first. They have very high MP and BP. So what are these range? What are the range? Now here your melting point and boiling point, the value ranges from 1000 Kelvin, see very high, isn't it? 1000 Kelvin to almost 1250 or 1230, it will go till 1250 1230 Kelvin. But your samarium has maximum of 1623 Kelvin. So we will write 1000 to 1230 Kelvin, but samarium has 1623 Kelvin. Please try to mention the example so that it's easy for the examiner to immediately give you marks. Now when I have to write the melting and boiling point of this particular thing, now this is 10,000, isn't it? So 1000 Kelvin, this is going to start from 1050 Kelvin and it's going to range higher than this 1623. So this is almost 1650 Kelvin. It's going to range till higher than samarium. 1650. If I have to see the boiling point, it's going to range from 996 Kelvin to 3198 Kelvin. Very high temperature. See, 3198 Kelvin is a boiling temperature of your actinides. That's the reason I said they're very high melting and boiling point. See, plus or minus, there's some variations, but the range, you can go with the range. Now when I have to come to electropositive character, now what is electropositive character? The ability to donate electrons. When will the electropositive character come into picture? Whenever your ionization enthalpy is very less. Simple, isn't it? When ionization enthalpy is very less, I can easily pull out it can easily donate an electron to an electronegative element, right? That is the reason in lanthanides the ionization enthalpy is low. That's the reason they are electropositive. Both are electropositive. So let us write electropositive in nature. Here also the same, electropositive in nature, because ionization enthalpies are low. Here also same. I'll also show you which ionization enthalpy is more or less. So again we'll meet with the next properties. I hope it is not confusing. Simple. Whichever you write, try to compare every element. Whenever you're writing some experimental value, that's more better for the examiner to give you marks. So let us come back and do the next 5 properties of your differences between lanthanides and actinides. So when I have to speak about the ionization enthalpy, we very well know ionization enthalpy depends upon the size of the atom. Done? Yes. So the IE1 value and IE2 values of lanthanides are comparable to your alkaline earth metals, right? So alkaline earth metals you will very well study in S block elements. The first is called alkali metal, the second is called alkaline earth metals. So I can easily write, I'll tell you why. Ionization are comparable to alkaline earth metals. Why? Here the range is for lanthanides, the IE1 ranges from 600 kilojoules per mole, and IE2 IE2 will be almost 1200 kilojoules per mole. Even when I observe kilojoules per mole. When I observe the alkaline earth metals, the IE1 starts from almost 700 kilojoules per mole and it reaches around 1145 kilojoules per mole. So they're trying to compare between the alkaline earth metals, means the comparative study between alkaline earth metals and lanthanides. So when I have to come to actinides, if I specifically write, if I take actinium example, actinium ionization first ionization enthalpy is almost 499 kilojoules per mole. And when I have to take IE2 value for actinium, it is almost 1170 kilojoules per mole. Yes. Now, if I have to take one more example, lawrencium, the last element. Lawrencium, the ionization enthalpy or IE1 value is 470 kilojoule per mole. So what are you observing? The ionization enthalpy values are lower than the lanthanides. That is most important, isn't it? So IE values are lower than lanthanides. Why? Not lanthanum, it is lanthanides. You have to write the complete thing. Why? Because of the outer configuration of the electrons which are held loosely. Your 4f electron, or your here it is 5f electron, your next to your 6d and this is s electron, they are very loosely held in the particular outermost shell. That is the reason I can apply less energy and remove that electron. So IE is lower than lanthanides. So when I have to come back to magnetic behavior, so when do we call something is showing magnetism? When they have unpaired electrons. So most important thing, whichever has unpaired electrons will show paramagnetism, whichever has paired electron will show diamagnetism. Now when I have to speak about F14 configuration, F14 is completely filled, isn't it? So whichever has F14 are called as diamagnetic substances. Right. Now if I take some more specific examples like lanthanum plus 3, if you write the configuration, it is paramagnetic in nature. Cerium plus 4, they are paramagnetic in nature. So I have given you 2 examples. So wherever you're finding completely filled, diamagnetic, whichever has unpaired electron, paramagnetic. So this is enough for this particular. Now when I have to write for actinides, actinides also show magnetic behavior, but not much as compared to your lanthanides. Yes, so the magnetic moment that is mu is less compared to your actinides. So I'm why are they showing? Because of 5f transitions, or 5 from the excitation, isn't it? The electrons 5 of wave function, they are going to show magnetic property, right? Yes, they are going to show magnetic moment, moment. Yes. Now I'm writing one example, I'm explaining. Otherwise I'm writing general one, I'm writing explaining, so that it's not confusing for you all. So let us learn the color property. So whenever we speak about color property, most important thing is they should be either DD transition for D block elements, or it should be FF transition for F block elements. But important thing is it should have an unpaired electron. Only in the presence of unpaired electron, that will go to the excited state and absorb that particular color from the spectrum and then show that particular color in the compound. So now when I have to speak about the color property in lanthanides, as I said, FF transition is important. Now the element with no unpaired electrons are colorless. So which will be no unpaired? Basically your F0 and F14 will be unpaired. Correct. Now F0 is your lanthanum plus 3. F14 is lutetium plus 3. Both are uncolored. They're colorless, means because of unpaired electrons. Now when I have to specifically write some examples, so samarium plus 3. it is your the color of samarium is yellow. When I have to write one more specific color, or this one example, Nd plus 3, this is pink in color. Yes, because of unpaired electrons. Now, if I have to write for actinides, now your uranium, what is the color of uranium? It is purple in color. Yes, now thorium, if I take thorium, because of unpaired electrons, it is dark blue in color. Dark blue in color. Yes, so all these, this is basically your, because of excitation of unpaired electron transfer, that is FF transfer. Now when I have to come to radioactivity here, in actinides are more radioactive compared to your lanthanides. So we can write they are more radioactive than lanthanides. That is the reason the elements after uranium are called transuranic elements. Means they are going to show radioactivity that is starting from actinium 89 to your the last element actinium 103. All are radioactive elements. Everything is radioactive. So let us write from all actinides are radioactive in nature. Yes, now here elements like basically your samarium plus 3 and promethium plus 3, or some, we will not write ions because reactivity we are speaking, isn't it? Samarium and promethium both are non-radioactive and remaining are radioactive in nature. So remaining are radioactive in nature. Right? Done. Now let us come back to the last one, oxocation. So what is actually an oxocation? Let's see. First important, lanthanides do not form oxocation. Yes. Now these are going to form oxocation. Now what is oxocation means? If the oxygen atom is carrying the positive charge, then we call it as oxocation. Like for example, just see your uranium, okay, plus look here, oxygen is carrying an positive charge, so oxocation. So NpO2, right, this is also carrying a cation, so oxocation, right? So basic thing is, if the oxygen, the electronegative atom is normally it carries a negative charge, but here if the positive charge is carried by the oxygen atom, we call it as oxocation, which lanthanides are going to form. So these do not form oxocation, so they form oxocation. Yes. Let us again meet with the next differences. Let's come back and learn the differences based on the oxidation state. So what does the oxidation state depend? Oxidation state basically depends upon the electronic configuration. It either loses electrons or it's going to gain electrons till it reaches that stable configuration, isn't it? So in case of lanthanides, your cerium is going to, based on the configuration, it's going to show +4 oxidation state. If I have to speak about samarium, it's going to show both +2 and +3 oxidation state also. Yes. Now let us come back and see based on the configuration whether I can tell them whether it is reductant or oxidant. Now when I have to take europium, configuration is 4F7 5S2, right? Fine. Now when I have to speak about one more, terbium, right, it is 4F9 5S2. When I have to speak about ytterbium, YB, it is 4F14 and 5S2. Let's see. Now here, europium, it can lose 2 electrons, isn't it? Yes, so it can show which oxidation, which state, it can show EU +2. One more ionization enthalpy I'm going to lose, and it can also lose one more electron. Yeah, that is your one from here, Nef subshell, and it can also show EU +3. Now let's come back to this TB. TB configuration, it can lose 2 electrons, it can become TB +2. It can also lose 1 electron from here, it can be TB +3. It can further extend its configuration because now this loses 1 electron, this becomes 4, this one isn't it, 8. Okay, from 9 it has become 8. Again, if it is losing, now 2 electrons, these two have lost. If I take out one more electron, it becomes 8. One more electron, if I take it, it's become 4f7. 4f7 is half filled and highly stable, isn't it? Yes, so it will also prefer forming Tb plus 4. That's the main thing. Now, when I take out ytterbium, this is completely filled configuration, so that's going to show Y, the stable configuration, YB plus, because this is already completely filled and will prefer showing +2 oxidation state, stable form. Yes, it also shows +3 with more amount of ionization enthalpy, correct? So these are your oxidation states of this one. So based on this oxidation state, I can say, yeah, it's losing, so I can say this is a reductant. This acts as a reductant. Now when I see this configuration, this is an oxidant, isn't it? Oxidant, it can act as an oxidant. Now again, this is a reductant. Yes, yes. So now when I have to come to actinides, the general configuration or the common configuration is +3. Yes, it can go and extend its configuration, like for neptunium and plutonium, it can extend its oxidation state till +7, right? So common is 3 +3 and it can go till +7. Now what actually is happening here, I'm trying to explain the concept of their reducing property also in this. So if they ask you the reducing property differences, you can write that and write this is reductant or oxidant. Complex formation. So now what actually depends on complex formation? Lanthanides do not form complexes, and these form complexes. What is the reason they form complexes? So the reason is here, when I have to speak about the configuration, it is 4D, right? Now this is 6s. I'm sorry, this is 6s, isn't it? 4f, 5d and 6s, correct? So I'm sorry, here this is 6s. No, it's wrong. Yes, it is 4f, 5d and 6s. Now here what happens is your 4f electron, yes, and your 5d and 6s. Here what is in this case? It is 5f, 6d, 7s, isn't it? Yes. Now what happens when I'm trying to take one electron out from 4f? The nuclear attraction is very high and the shielding effect also is very less. So this is, compared to 5f, this is more inner. It is incorporated, it is inside the atom, and the nuclear attraction is more on this compared to this, isn't it? So pulling out the f electron is very difficult to form complexes. That's the reason it doesn't form complexes. So what should I write? The 4f electron or the 4f electron is, or experiences more nuclear charge compared to 5f. So now 5f can easily donate electron and form complexes. So 5f participates in complex formation. Yes, complex formation, that's it. So compared to this, the distance, and I'm comparing the distance between 4f and 5f, and I'm explaining the possibility. So you can write this. So these are your differences. Almost 12 differences are given. Please learn at least 7 out of that. If they give you 4, on the safer side, try to learn 10 and keep it with you. So whichever property is asked, you can easily write that. Right, so let us come back and learn the chemical properties of your lanthanides and actinides. So we've already studied the differences between lanthanides and actinides. So let's come back and see this topic. So basically your lanthanides, or this particular lanthanum, we're going to learn the reactions of lanthanum and what is the configuration of lanthanum, right? Lanthanum, when I speak 4f0, 5d1, 6s2, isn't it? Yes. So it can only show a maximum of +3 oxidation state. It can lose these 2 electrons and this one. And since f is 0, it doesn't extend its valency. It doesn't extend its oxidation state beyond +3. So lanthanum will show +3 oxidation state. Yes. Now with this concept, I'm going to show how is it going to react with different elements. Very easy to just see. Now we very well know it is a rare earth metal. Yes, when you're dropping a metal in an acid, we very well know it's going to form salt plus hydrogen gas. We've learned in grade 10, metal plus acid gives me salt plus hydrogen gas, which pops out, isn't it? So same thing, metal plus acid, it's going to release out hydrogen gas. That's it, simple. Now suppose if I have to take halogen. Now halogen suppose X, right? Now let me take Cl. Now what is the valency of chloride? It is -1. What is the valency of this in lanthanum? No, it is LaCl suppose. This valency is 1. Lanthanum is 3. So it is LaCl3. So 1 not required. That means it is Lx3. Simple. Now let us come back to water. So basically water I can write it as HOH, isn't it? Yeah. Let us combine. No, not it is lanthanum. No. Yes. Should I? Metal X3. Okay, done. Lanthanum chloride. Now I have to react lanthanum with your water. So just combine. This is your positive. This is your positive. This is negative. Combine with your negative anion. It becomes LnOH. Now valency, just see. OH valency is -1. Lanthanum is 3. So lanthanum hydroxide. Simple. Now let us come back with carbon. Basically carbon, specifically if this temperature is given to you in the paper, yeah, only this temperature is given, just simply write it forms LnC2. But otherwise if I have to see the different combinations of carbides, it's going to form a carbide with this valency Ln2C3. Further, it can also form a carbide of this type. It can also form a carbide of this type. This I have written already. Yes, so this is your type of carbides which is going to form. Now if I take nitrogen, now combine L and N. Now L and N. Nitrogen valency is -3. Lanthanoid valency is +3. So both when you cross, the formula is lanthanum nitride. Simple, isn't it? This is -3 got cancelled, +3 got cancelled, so Ln is the formula. Now sulfur. Now again write down Lns. The lanthanum valency is 3, sulfur valency is 2. So lanthanum sulfide, Ln2S3. Simple. Now let us write with oxygen. Same thing again, combine Ln and oxygen. Oxygen valency is -2. Lanthanum valency is 3. So Ln2O3. So that is your lanthanum formation. Again, acids we very well know, when we drop, hydrogen gas is going to release with the formation of salt. Done. I have not written any acids, so specifically I have written a general formula. Here halogen, as I said, it is Ln, lanthanum, and chlorine valency is -1, lanthanum valency is +3 because I've shown you here Ln X3. Done. Water, same thing, H plus and OH minus. OH valency is -1, lanthanum is 3. Done. Carbides, as I said, it is going to form different combinations. Lanthanum 2 carbide, this particular thing I have crossed it, so it's going to form different type of carbides at different temperatures, but specifically if they are giving you, right, LnC2. Now here nitrogen valency is -3, lanthanum is +3, got cancelled. Here sulfur valency is +2, lanthanum valency is +3, so Ln2S3. Now oxygen valency is -2, lanthanum is +2, Ln2O3. So these are the simple chemical reactions of lanthanum only, which is prescribed for your syllabus, right? Now when I have to go to actinium also the common oxidation state is +3. So same thing again, H and OH. And this is minus, this is plus, this is plus. Now take down ACOH. So I said OH is -1, not required to write. Actinium is 3, so ACOH take 3. Now oxygen, again the same thing, ACO, right? Oxygen valency is 2, this one is 3. Now further, if you want to prepare any halogen from actinium trioxide, what do? They're going to add aluminium bromide to this. When you add aluminium bromide, just observe, yes, it's going to form, just see, this is going to form actinium bromide, I'm not balancing, and Al2O3. That's it. These are your reactions of your actinium and actinides and lanthanides. The first element actinium and the first element lanthanum. That's it. So simple, isn't it? Just note it carefully and practice it properly. Maybe if that is given, this will be useful for you all. Right. So let us come back and do the next topic of your lanthanide elements. Very important question, that is, what is lanthanide contraction, right? So most famous question asked in lanthanides. We've been seeing the same since years. Okay, fine. Let's see what should we do and how should we write in the exam. Now this question can be asked in a different way also. How will they ask you? If it is not a direct question like this, then you will be questioned like in this form. Why does the ionic radii decrease from cerium +3 to lutetium +3? Don't get confused. Simple it is. Let us write that question also. Why does the ionic radii decrease from cerium +3 to lutetium +3? Okay, right. Basically what happens when you see direct lanthanide contraction, everybody tends to write the answer, but problem is if you tend to forget this particular element, right, that particular lanthanide element, then there's a problem. So to confuse you all, they may give you in this way, because cerium, lanthanum, cerium, all these are lanthanide elements. They may give you to confuse you, but don't get confused. Simple thing, cerium to lutetium. When you see lutetium, okay, just remember lanthanum to lutetium, they're asking you about lanthanide contraction. Done. So basically in your board paper, in the marking scheme, 3 important things should be given as subheadings when this answer is given. What are those? First would be definition. Next would be explanation. Next would be consequences. These 3 would be there in the board paper, right? So you should be able to write those 3 subheadings, then try to explain the answer. Then you'll be allotted full marks for that particular thing. So before I go to the consequences, first I'll explain this, then I'll go with the consequence. Let us write. So whenever we speak about lanthanide contraction, so we have already studied lanthanides. The general configuration for lanthanides is what? When I have to write lanthanum, so we're going to start with 4F, right? 1 to 14, yes, 5D, 0 and 1, and 6S, 2. This is what is your configuration, isn't it? Now, I already said this is the valence shell, this is the penultimate shell, this is the anti-penultimate shell. Now, what is happening here? Lanthanide contraction, basically, you're going to write 3 important keywords. What? First, definition-wise, the decrease. Your answer, start your answer with the decrease. So automatically your answer, you will have that flow in that answer. The decrease in ionic radii. Yes, of what? What is decreasing? Of which ionic radii? Ionic radii or from lanthanum. Okay, right? So ionic I said, so write the ions. Lanthanum ion to lutetium ion, because this is a stable state of stable oxidation state, isn't it? Lanthanum ion to lutetium ion. Why is it decreasing? Due to imperfect shielding of, what did I say? Every time the electron enters into the F subshell, yes or no? So imperfect shielding of 4F. Most of the students, I don't know why, they write some other 5D, 6s. Please don't do that. Imperfect shielding of 4F electron from the nuclear charge. So from where is it? This is from nuclear charge. Okay, this is your basic thing. After writing the definition, try to just leave some space. Okay, explanation I'll write here. Try to write one important thing here. So I said decrease in ionic radii, isn't it? Now observe, cerium, the ionic radii is 103 picometer. Gradually due to lanthanide contraction, it has come down to lutetium 85 picometer. So just start your answer so that the examiner will have, okay, fine, this particular student has an idea of lanthanide contraction. So here you can write cerium +3, as you have written, from 103 picometer reduces to lutetium +3, which is here 85 picometer. You have to remember the values in Go, so that you know you will get that extra mark in the exam, right? Yes. Now, when I have to explain this particular concept, simple, just start writing. So, we very well know, according to the configuration, your 4F. Now, this is your nucleus, isn't it? Right. You have proton, you have neutron also. You have the shell, again, the one more shell and one more. Now, we are speaking. Suppose if I speak about the outermost shell, this is your valence shell. Now, 6s. Next comes your penultimate shell, that is your 5D. Next comes your anti-penultimate shell, 4F. Now what happened? This is 2. This is 5D, 0 to 1. Now this is 1 to 14. Every time the electron tries to add to this 4F subshell, isn't it? Yeah, automatically when the electron is added, even the proton is also added. Now what happens? The Z effective, the nuclear charge of the Z effective, it tries to drag this 4F which is closer to this. So what will happen? Already 4F has a double dumbbell shape, and the shape is diffuse, isn't it? It can't shield the outer electrons. So this 4F, suppose if I write 4F here, okay, let me write 5D here, let me write 6S here, okay. So it's clear for you all. Yes. Now what happens? Your 4F, because of its diffuse shape, first important thing when you're explaining, right, 4F has diffused shape. So what is diffuse shape? Diffuse shape is nothing but the electrons are spread all over. So because 4F has diffuse shape, this starts, or this particular thing, when the nucleus is trying to drag this electron here. Now I said Z effective is very high. It will not, because of its diffuse shape, it will not protect the electrons which are there at the 5D shell, subshell and 6S. So now what happens? Your nuclear charge is directly attacking on this. It's directly attacking on this, and the protons which are getting added, they try to drag the S electron and the 5D electron very closer, making the atomic size of the ionic radii very less. So once again, 4F electron has diffuse shape. Because of what will happen? It has imperfect shielding. Now because of this imperfect shielding, what is happening? Always the Z effective, or the nuclear charge, is acting more on the 5D and 6S. Yes. So Z effective tries to drag the electrons, hence reducing ionic radii. Simple, isn't it? So already the protons are also getting added, electrons also getting added, but this for 4F, since it is not trying to screen or protect this electron and this electron, the whole ionic radii keeps on decreasing as I go down. Just see 1 or 3, again decreasing, it has reached 85 picometer. So I try to explain this concept. Now I have to explain the consequences of this. What is happening because of this? Now done. I am already clear with the concept, and I have to come to the consequences. So whenever you are writing the consequences of these things, important, you are going to explain the consequences under 4 subheadings. Okay. Now consequences means what happened because of this atomic radii, Lanthanoid contraction. So you like that, consequences, right? First important thing, because of this Lanthanoid contraction, now when I see, we've already studied 3D series, D block elements, isn't it? 3D, 4D, 5D and 6D. Correct. Now first important thing, just observe, this is your 3D scandium, this is yttrium, now 5D lanthanum. Now adjacent to that you have elements which are arranged according to the atomic number. Just see your elements which are just adjacent to lanthanum. Now because you're at a lanthanide contraction started from here, lanthanum, cerium and everything. So lanthanum, this particular thing, immediately the element adjacent to that, hafnium. The element adjacent to yttrium, that is zirconium. The element adjacent to the niobium. After hafnium, tantalum, right? After niobium, molybdenum. All these, this whole lanthanide contraction effect was observed in all these elements. Yes. So that particular element, what happened? Your first important thing. So because of lanthanide contraction, start like answer here, because of LC means lanthanide contraction, the properties of what properties of, let us write the table. So where it started? It started with zirconium. Below zirconium you have hafnium. After zirconium you have niobium. Below that you have tantalum. After niobium you have molybdenum. All these properties are affected by lanthanide contraction, because that's the same lanthanum following, isn't it? What properties are affected? If I have to write, let's see here. Now when I see zirconium, the bond, the radii of zirconium was 159. Okay, let us see. Zirconium is 159 picometer. Okay, when I have to speak about hafnium radii is 1656 picometer. Are you not finding the difference? Because down the group it has to increase, isn't it? The atomic radii has also decreased. If I have to see the ionic radii, suppose if I take zirconium plus 4, hafnium plus 4, how many is it? Listen, the zirconium ionic radii is 79 picometer, hafnium it has become 78 picometer. Are you not observing the decrease in ionic radii? Yes, done. Yes, the same thing. Now what happened? Even the molecular mass, now zirconium 91.22, later on when I see hafnium it has gone to 178.4. so the mass and the atomic radii, what will happen to the density? We very well know mass and volume, right? Density is equal to mass by volume. So the atomic radii and your mass together also changes the density of these particular elements. So important, because of these properties, the what properties I said? Yes, atomic radii is varying, density is varying. Yes, because I already told you atomic in listen. Ionic, okay, atomic radii, okay, you can write ionic radii also, not a problem. Ionic radii, okay. Ionic radii similar? Yes, ionic radii is varying. Along with that, density, properties like melting point, boiling point, all these factors are varying. So what is making this vary? The Lanthanoid contraction. Now when such properties all are similar, right? So can I separate the elements? It's very difficult for me to isolate all these elements, isn't it? So that would be your second point. First point, because of this, the properties of all these elements have become or this almost similar. Done. Now second point, when I have to write, you're going to write separation of these metals becomes difficult. Why? Because when there is a variation of very less variation, I can't isolate the metals separately, isn't it? So separation becomes of these metals become difficult. And now when you're writing, write subheading like this: because of these elements, properties have become similar, underline. Now separation of these metals becomes difficult, underline. So let us come back to third important thing. Right, and when I have to write the third consequence, you have to first go back to your grade 11th Fajon's rule. What does it say? Third important concept is, it's going to speak about basicity concept. Basicity concept, what is it? Or solution. Now, what does it say? I said basicity concept, when I have to speak, I'm going to speak only when your cations are combining with water to form, because the oxidation state of this is +3, isn't it? Stable. Now HOH, I can write it as like this, correct? Now this is positive, this is positive, this is negative. It's going to form a bond with this, and lanthanum hydroxide plus hydrogen gas. Remember, you most important thing is you will speak only in terms of hydroxides when you are speaking about basicity. Yes. Now you are going to write the basicity concept based on Fajon's rule. You can write here also like this, Fajon's rule in the exam. What does it say? Yes, whenever the charge of the cation, now this is your cation. Which cation is this? Ln +3. After your lanthanum, isn't it? Okay, right. So lanthanum, okay, lanthanum, your La +3. So this La +3 cation, yes, when I have to see what are the characteristics of this. First important thing, the cation charge is larger, correct? Now higher, which charge is higher? Positive charge. Higher the positive charge. Okay, done. What else are you finding? The size, when the charge is higher, according to this one, automatically the size of the cation is already smaller, isn't it? Smaller would be cation. Okay, smaller the cation. When the cation is smaller, as I said, this cation is going to drag or polarize this anion. It's going to drag that anion, isn't it? So what will happen? This cation and the anion is going to drag, and the polarizability will be very high. Yes or no? So when it is trying to drag or polarizability is very high, what will happen to the character? It's going to form a covalent bond because it's dragging that whole density towards it. So covalent nature increases. When the covalent nature increases, just simple, easy thing, isn't it? Now when it's trying to drag, will it release this OH minus ion easily? Right? So I'm going down, size is decreasing. It will be highly polarizability. Lutetium will have high polarizability. It's going to pull the electrons because of its size. Now when it's trying to pull the electrons, will the basicity decrease or increase down the group? Automatically basicity decreases. Yes or no? Let us come back and experiments again. What did we say? Lanthanum to lutetium. So which is higher charge? Lanthanum is higher charge. Next comes cerium. Like that till last is the smallest one is lutetium. Larger cation, smaller cation. Okay, and let's come back. Now see, when the size of the cation or the higher the positive charge is higher, +3. Because this is the maximum charge. The size of the cation will be smaller. Yes, according to Fajan's rule. When the cation is smaller, it's going to drag the anion, which is OH minus, yes, towards it. When it is trying to drag, it's going to form a tight covalent bond. When it is forming a tight covalent bond, will it release the OH minus ion? It doesn't release, isn't it? Basicity decreases down the group. So that's why when I have to see this, okay, you're going to write all this important thing and come back to the conclusion. Conclusion is lanthanum hydroxide is more basic than lutetium hydroxide. So this is based on basicity, because it is not going to release that OH minus ion because the size is very small. So your basic concept is, speaking in terms of Fajan's rule, finally concluding your basicity. Basicity decreases down the group. Yes, so this is done with your third, this one. So what did I say? There is variation in atomic radii. First thing, separation becomes very difficult for me. Second thing, I said basicity decreases down the group. That is what I said. Yeah, let us come back and do the next one. So what would be the fourth concept? When I have to speak about fourth concept, yes, simple thing. I'll just I finish off this consequence with speaking in terms of electronegativity. Just now I said when I go down from lanthanum +3 to lutetium +3, which is a smaller ion, this is the smaller cation. When the cation is smaller, what will happen to the M+3 electronegativity? Yes, this is going to drag the electrons from the OH minus ion. Yes, because it's positive charge. So what will happen? Down the group, electronegativity of M+3 increases. Simple. Yes, so this is your lanthanide contraction. Please remember definition, yes, explanation, yes, second, third would be consequences. 4 consequences should be written, everything underlined. Yes, if you don't remember the graph, not a problem, but please try to remember 103 picometer and 85 picometer, that would be better. So this is your lanthanide contraction. So let us come back and start with the chemical properties of your potassium permanganate. So as I said, potassium permanganate and potassium dichromate are oxidizing agents, good oxidizing agents. So we are going to learn these oxidizing properties by showing or taking different examples. Basically you have 5 or 6 examples. I think you have 5 examples for your acidic medium and 3 examples for your neutral medium. So what I'll do is, whenever I'm trying to convert or show you the oxidation, I'll be picking up each and every reaction and show you how to balance these reactions. Basically not writing the reactions, we'll see how to balance. So the method which I'm going to use is your half cell reaction method. So let's start. So as I said, permanganate or permanganate, this particular thing as an oxidizing agent is going to oxidize. Now these are the list of reactions which we'll be doing one after the other. So it's going to oxidize iodides to iodine. Done. When I say oxidizing agent, that means it's going to gain electrons. Yes, done. And that the other one is going to just decrease in the oxidation number. Simple, isn't it? Whichever has higher oxidation state or higher oxidation number acts as an oxidizing agent. The one with the lower oxidation number acts as a reducing agent. Right, let us come back. So what is the concept? Manganate oxidizes iodides to iodine, ferrous to ferric, nitrite to nitrate, oxalates or oxalic acid to carbon dioxide, hydrogen sulfide to sulfur, sulfide to sulfate. Okay, these are just the reactions. I'll start with one after the other. So let us come back and start with the first balancing or conversion or oxidizing properties of KMnO4 using 1-1 reaction. So let's start with your oxidizing properties of permanganate. So as I said, I've given you a list of oxidizing properties at different reactions which is prescribed for your syllabus. So I've picked up one important reaction. Let us do all the 5 in acidic medium and neutral medium. So first, doing such reaction, basically how is this given in the exam? This particular question is given in this way: MnO4 minus plus C2O4 minus 2. This, they'll give you this and they'll ask you to complete it. You have to complete it. For that, we are going to follow a method called half cell reaction method, which you have studied in your grade 11. Now, once this question is given to you in the paper, now what did I write here? Here I've written the complete reaction which I'm supposed to get, because first initially you're learning. I think you've forgotten your this in grade 11th only. So first I've written what should be obtained. This is the final answer. We'll do here and compare it with you. Now, whenever you have to do, let us do it stepwise. Step 1. First, pick up that basic reaction which is given to you in the question paper. MnO4 minus C2O4 minus 2. Right. How should I remember which product? Basically, I said oxalates or oxalic acid to carbon dioxide. I said that. Iodines or iodide to iodine. Sulfides to sulfur. So, that basic thing you have to remember and go, and then it will be easy. So, now this one, Mn plus 2, and oxalate is going to form carbon dioxide. This thing at least you can remember, I think. Yes. So first important thing is calculating oxidation numbers. Calculating oxidation numbers. Right. Now start with the first one. Now this is a metal atom, X plus 4 into valency is minus 2 minus 1. X minus 8 plus 7. So manganese oxidation state is plus 7. Done. So let me erase this. Now let us come back to oxalate. Now calculate oxidation number here. This is 2x, isn't it? This is x, and this already we know, 2x minus this is plus, isn't it? Initially, okay. So 4 to the then it becomes minus 8 minus 2. 2x is equal to plus 3. I have got oxidation state of carbon as plus 3. So let us write as plus 3. Done. Let me come back here. This is already Mn plus 2. Now for carbon dioxide, this is minus 2. Yes. So when this is minus 2, this is minus 4, isn't it? This should be plus 4. Because minus and plus should get cancelled and becomes finally 0. Now let us erase this also. Now first step is done. Now in step 2, you are going to see which is the oxidation or which is undergoing oxidation, which is undergoing reduction. It's the same procedure for all. Now when I have to see in this particular thing, okay, if you want to write the reaction again, not a problem. MnO4 minus C2O4 minus 2, you can write here also. I am again writing plus 2 plus CO2 plus 4 plus 2. Now I've got this is plus 7. Now from here, you will see what is happening to this Mn, and from here see what is happening to this carbon dioxide. Now here manganese from plus 7, it has gone to plus 2. So what happened? it started gaining electrons, isn't it? 7, earlier it was plus 7, it has lost 7 electrons. Now it has gained and come back to plus 2. Don't get confused. Higher oxidation to lower oxidation state means they have gained the electrons and underwent the reduction process. Gaining electrons is reduction. So from plus 2 to plus 7, how much? 7, it's 5, isn't it? So how much has it gained? It has gained 5 electrons. When it has gained 5 electrons, what process does it undergo? What process has it undergone? It has gone under reduction process. Gain of electrons is reduction. Now here from plus 3, it has gone to plus 4. What happened? Now from higher to lower is reduction, from lower to higher is oxidation. How many electrons has it lost? It has lost 1 electron. When it has lost 1 electron, what process do I call it as? Oxidation process. Simple. Now your step 2 is done. Now come back to step 3. Now write half cell reactions. Half cell reactions means anodic reaction, cathodic reaction. Now here one has undergone reduction, one has gone oxidation, so divide. Take that oxidation reaction here. This oxidation reaction always happens at anode. Take that reduction reaction here. This reduction reaction occurs at cathode. Done. Now write the oxidation reaction half cell. Divide into 2 equal halves. So your oxidation reaction is this, isn't it? Write that C2O4. Copy with the charges, not a problem. It is giving me carbon dioxide minus 2 plus 4. This is your plus 3. Now come back and write the reduction reaction. What is the reduction reaction? MnO4 minus is forming, or it's Mn plus 2, and the oxidation state is plus 7. Yes, done. I have written the half cell reactions. Now important, once you write the half cell reactions, just try to balance the atoms here. Now here carbon is 2. So let us write half cell reaction and balance. Balance atoms. Now here carbon is 2. Here it is only 1. So try to make it 2. Done. Let's come back and see. Manganese is 1. Manganese is 1. Oxygen, I'll balance at later stages. Done. This is also done. After that, let us come back to step 4. Here you said oxidation, here you said reduction. You have to see how many electrons got lost and how many electrons have gained. Here in reduction process, it has what should you say, reduction is gain of electrons, isn't it? Which has gained electrons? MnO4 has gained 5 electrons. That's why the reduction process you will write as gaining. The oxidation you will write as loss. Okay, it has gained 5 electrons. And here what happened? Oxalate, how much it has lost? It has lost 1 electron. Correct? Hope you understood this. This has lost 1 electron outer side. This has gained 1 electron inner side. Done. Both are. Now in step 4, you are going to take these 2 half cell reactions and try to balance with oxygen. You have to balance oxygen. Let us write this reaction first. I'm going to, okay, let me draw a line. Take this oxalate, right? Minus 2. Now 2 CO2 plus 1 electron. Oxidation cell reaction I've written. Then copy this reduction reaction here. MnO4 plus 5 electrons gives me Mn plus 2. Now I have to balance your oxygen. How will you balance oxygen? Just observe acidic medium I said, isn't it? When I say acidic medium, you have to be very careful. You have to balance oxygens on whichever side is less. Again, whichever side oxygens are less, that side you will add water. Yes, hope you understood this. Just see in the final reaction, where did I get water? I got water on the right hand side. So let us come back and see. Now on this particular thing, how many do we have? You have oxygens, 4 plus 4, 8 oxygens. On this side, how many do we have? You have only, now just see, your 2 twos are 4 only, isn't it? You have only this one 4 oxygens. So how many are excess on this side? You have 8 here, you have 4 here. So you're going to multiply with 4 water molecules on this side. 4 water molecules. Simple. 4 plus 4, 8 oxygens. 2 twos are 4 oxygens. So to compensate that, I have multiplied with 4. Done. Now again, to compensate this hydrogen, you are going to add on this left hand side. Right hand side water, left hand side protons. So how many hydrogens do we have? Now oxygen is balanced. 4, done. Now hydrogens are 4 2s are 8. Try to add 8H plus on this side. Done. Yes, we are almost coming close to the reaction. Now, one important thing, this part is done. In the next step, in step 5, now you have to be careful. What are we doing? We are going to cancel, okay, let us write, in step 5, we are going to cancel electrons. How are we going to cancel electrons? First important thing, you have to see, here when I have written carbon dioxide 1 electron, for 2 carbon dioxide, so for 1 carbon, 1 electron. For 2 carbons, how many electrons? It should be 2 electrons, isn't it? Simple. Yes, so here also 1 carbon was 1 electron, 2 carbons was 2 electrons. It should be 2 electrons. Done. Now you're going to cancel electrons. What should you do? Here, to cancel the electrons on LHS and RHS, simple. Here what do you have? You have 5 electrons here. Here you have 2 electrons. So now cross multiply. This 2 electron, try to multiply with this. This 5 electron, try to multiply with this. Then what happens? We have cross multiply with this number. Again, 5 electrons to cancel these 5 electrons, I have multiplied here. To cancel these 2 electrons, I have multiplied here. Just simple, isn't it? Now 5 into 2 electrons will get cancelled on the RHS. 2 into 5 electrons will get cancelled on your LHS. Done. Once this is done, let us write the overall reaction. You have to be very careful here. First important thing, this 5 is common to all. This 2 is common to all. Just to cancel the electrons, I wrote it, isn't it? Now start. When you're writing this reactant, 5 oxalates. So 5 C2O4 minus 2 plus. All right on the reactant side, below oxalate, what do you have? MnO4. Just below, how many are there? 2 plus 2 MnO4 minus plus. Electrons got cancelled. There's nothing here. After electrons, you have 8. 8H plus, when you multiply with this becomes 8 to the 16H plus. Done. Let's come back to the product side. When I have to write the product side, now again start. 5 is common to whole. 5 into 2 is 10 carbon dioxide. Plus electrons got cancelled. Below carbon dioxide, what do you have? You have Mn plus 2. How many do you have? 2 Mn plus 2. Done. Plus water molecule, 4 into 2, 8 more water molecules. Let us come back and compare with the main reaction. This is your main reaction. 5 oxalates, correct. 2 MnO4, correct. 16H plus, correct. 10 carbon dioxides, also done. 2 Mn plus 2 done. 8 water molecule done. This is how you're going to balance the half cell reaction method. Let us meet again with the next oxidizing property of KMnO4. So let us come back and do the next oxidizing property of your potassium permanganate. So now what did we learn first? We have learned the oxidation of your this in the earlier reaction complete, we will learn a clear picture of step by step conversion of your oxalate or oxalic acid into carbon dioxide. Now here we are going to learn oxidation of ferrous to ferric. Your ferrous is +2 oxidation state, ferric is +3. Let's see the stepwise balancing. So this is the reaction which you have to get. Now again it is an acidic medium only. Let us write the step. When you have to do the first step, step 1 is calculating oxidation numbers. Oxidation numbers. Okay, please observe carefully. If there's any confusion, you can just send me a message so that I'll respond. So oxidation number calculating, take that skeletal reaction MnO4 minus plus your Fe. Just don't take anything else. Just a skeletal reaction, the question which is given in the exam paper. Now what did I say? Fe plus 2 will get converted to Fe plus 3 and MnO4 will get converted to Mn plus 2. This is what is the reaction. Let's start. First, when you're calculating the oxidation number, this manganese X, same thing like earlier video, plus 4 into minus 2 minus 1. Minus 8 minus 1, X is equal to plus 7. So manganese oxidation status plus 7. Done. Now let us write that plus 7. After this, Fe plus 2 is already there, nothing to do with that. Fe plus 3 is already there. Mn plus 2 is already there. Simple. Now in step 2, what should I do? I have to see which is undergoing oxidation and which is undergoing reduction. Yes. Now important thing, how should you remember? Fine. Whenever there is higher oxidation state, okay, let us write higher oxidation state. If it is coming down to lower oxidation state, then it is reduction. Just remember like this, reduction. Okay, indirectly I am talking about gain of electrons. Done. If it is in lower oxidation state and if the oxidation state is becoming higher, then it is oxidation, loss of electrons. Done with this concept. Now see, manganese from plus 7 to plus 3. Now what happened? Higher to lower. So what is happening? Higher to lower, from plus 7 it has gone to plus 2. That means it has gained electrons. That means it is undergoing a reduction process. Done. So let me erase the first one. Now I have to see the second one. The second one is your Fe plus 2, from here it's going to Fe plus 3. Lower oxidation state to higher oxidation state is called oxidation and it is loss of electrons. So from plus 2 to plus 3 it is going, and this process is oxidation. It has lost how many electrons? The difference is plus 1 electron. Done. Step 2 is done. Sorry, step 1 is done. Now in that step 2 also is incorporated because I have shown you what is oxidation, reduction. Now writing half cell reactions. Divide your page into 2. Try to write your oxidation half cell or oxidation half cell reaction and reduction half cell reaction. Done. Now write that reaction here. Which one underwent? This one is oxidation, this is reduction, isn't it? So write that Fe plus 2 forming Fe plus 3 plus 1 electron. Write with electrons. That's important because half cell reaction method, we are balancing based on electrons only. Yes, now write the reduction method. Reduction, this is MnO4 minus getting converted to Mn plus 2 plus 7. This is. Now after writing this, you here electrons have written, isn't it? Now here also have to write electrons. How many electrons has it this in? What is the difference between this and this? From plus 5 to plus 2, plus 7 to plus 2, how many? 5 electrons it has gained. So just write how many. This has gained 5 electrons, isn't it? From here till here, so 5 electrons. Done. Electrons are balanced. Now after this, let us come back to your step 3. In step 3, you're going to balance oxygens by adding water molecule whichever side oxygen is less. Let's write the heading balancing oxygen atom. How do you balance oxygen atom? By adding water. Let's take this reaction first. Fe plus 2, there's no oxygen, so not a problem. Fe plus 2, Fe plus 3 plus 1 electron. Write the second reaction here. MnO4 minus plus 5 electrons giving me Mn plus 2. Now if I have to see oxygens, this doesn't have any, this is an oxygen atom, not a problem. Here, how many oxygens do we have? You have 4 oxygens. Yes, this side there are 4 oxygens, this side there are no oxygens. Now I said it is acidic medium. See in the final reaction, acidic medium. Wherever there is oxygen excess, the opposite side you have to add water. Simple. Now how many are there? 4 oxygens. So you will balance it by writing 4 water molecules. Now again, to balance hydrogen, oxygen atom is balanced and also we'll balance hydrogen atom also. Now oxygen 4. Hydrogen has become excess now. 4 2s are 8. So try to add 8 protons on this side. Now just see, the oxygen is balanced. Electrons are not balanced until now. Proton is balanced. Oxygen is balanced. Done. Now in step 5 or step 4, you're going to balance electrons or cancel electrons. Better I write cancel electrons. Cancel electrons. Yes, done. Here, as I said, put a bracket like this on both the sides. Now how many are there? In the first one, there's only one electron. Here there are 5 electrons. To cancel this electron in LHS and RHS, just see, multiply this reaction with 1 here and multiply this reaction with 5 here. Okay, when I multiply, what will happen? Let us write the overall reaction with electrons cancelled. This 5 electrons will get cancelled on the RHS. This 5 electron will get cancelled on the LHS. Done. Now start writing the product. 5 Fe plus 2. Okay, done. Come down because we don't have any other reactant here. Come down. What is there here? MnO4 minus. MnO4 minus plus. Do we have anything in the reactant side? Not there. So you will just write an arrow. Now come back to this. 5 Fe plus 3. 5 Fe plus 3. Plus electron got cancelled, then come down to the product side. 1 Mn plus 2, so not required to write 1, so Mn plus 2. 4 1 there's nothing. 4 water molecules. Now compare. 5 Fe correct, MnO4 correct. Now 8 we forgot 8. Okay, water molecules protons we forgot. 8 H plus. Please be careful because acidic medium. 8 H plus. Done. 5 Fe plus 3 done. Mn plus 2 done. Water molecules done. So this is how you're going to do your balancing. So we'll meet again with the next type of oxidizing property of KMnO4. Let us come back and do one more oxidizing property of your KMnO4, where it's going to oxidize sulfide to sulfate. So what is the sulfide? Sulfide is basically your SO3 minus 2 and sulfate is SO4 minus 2. So now we're going to balance this reaction. I've already done 2 videos on this. So let's start using half cell reaction method. So in half cell reaction method, when I have to take the step 1. As I said, in your question paper, what will be given in the question paper? Your question paper, this part and this part will be given. You need to show the complete step-by-step balancing and get that balanced reaction. So in your paper, let us write the question given in your paper first. Minus and your SO3 minus 2. Done. I already said manganate always gets reduced to Mn plus 2. The same thing everywhere, it's the same. Mn plus 2. And sulfide gets oxidized to SO4 minus 2. So in your step 1, first you have to calculate oxidation numbers. Start calculating. This is X. 4 into oxygen valency minus 2 and minus 1. So if I have to solve this, I'm going to get X is equal to plus 7. Done. So take this plus 7 and write it here. Done. So let us take this out. So now what do you have? You have plus 7 here, and let's start with sulfur. Now sulfur, when I have to calculate, X plus 3 minus 2 minus 2. When I have solved this, plus 4 I get, isn't it? Now write sulfur valency as 4. Done. Let us come back. Here manganese is already plus 2. Now I have to calculate for this sulfur. Now X plus 4 into minus 2. Here I've got valency of sulfur as plus 6. Done. In step 2, what should I do? I have to, first important thing, see which is undergoing oxidation, which is undergoing reduction. Now I'm going to write the same reaction here with oxidation states which I calculated. Manganese from plus 7, its oxidation state has come down, or it has gone to plus 2, means come down means the oxidation value, number value. But in the process, what is happening? From higher value to lower value when it is going, that means it has gained 5 electrons, and it means from 5, 7, 6, 4, 5, 4, 3, 2. 5 electrons it has gained, and from plus 7 to plus 2, it has gained 5 electrons. So those 5 electrons I call it as reduction gaining. Now this one from 4 plus 4, it is going to plus 6. It has lost 2 electrons. First it was 4, then 5, then 6. So from plus 4 to plus 6, it has lost 2 electrons and it is oxidation. Loss of electrons is oxidation. Done. Now you're going to write half step 3, half cell reaction method. You're going to divide into oxidation or anodic cell reaction, oxidation cell reaction, and reduction cell reaction. Done. Now oxidation, this part, manganese, sulfate is oxidation, manganese is reduction. Write that sulfate reaction, SO3 minus 2 to SO4 minus 2. How many electrons has it lost? It has lost 2 electrons, so 2 electrons. Now come back and write the reduction part. So reduction part is your manganese, because manganese has gained 5 electrons. So manganese MnO4 minus plus, it has gained 5 electrons to form Mn plus 2. After this, now you're going to balance oxygen atoms. In step 4, you're going to balance oxygen atoms. So write both the reactions together. SO4, so 3 minus 2 giving me SO4 minus 2 plus 2 electrons, and copy this reaction down. MnO4, careful with the electrons, 5 electrons giving me Mn plus 2. Now see which side oxygen is less, and then after oxygen we are going to balance hydrogen. Here you have 7 oxygen atoms, 4 here, 3 here. Here how many oxygen atoms? You have 4. So it is less by 3 oxygen atoms. Now count 4 plus 3, 7. 3 plus 4, 7. Now I have to balance hydrogen atoms. Now hydrogen, how many? You have 3 into 2, 6 protons. Just see 6 protons are already ready with 6 protons. But now you have to be very careful. This 3 water molecule, how many? I said 6. Now if I have to multiply the 6, careful here. This particular reaction here, you have, if I have to break this, 3 protons only, isn't it? Now if I have to see like this, H plus plus OH minus. Yes, how many protons are there? If I see, it is only 3 protons. So write that 3 protons here. Now you are going to cancel the electrons. Now to cancel the electrons, what are we going to do? Here there are 5 electrons because I have to get the final reaction. Multiply this reaction with 5. Multiply this reaction with 2. Finally cancel all the electrons on the LHS and RHS. Now here this 2 electrons gets cancelled. This and these electrons get cancelled. Now let us write the final reaction. Now the first one on the reactant side, 5 SO3 minus 2. Okay, this is done. Plus on the reactant side you don't have anything else. Come back to the below reaction. Now manganese is 2 MnO4 minus. Come down. 3 into 2, 6 protons here. Yes, let us see whether we have got 6 protons. Yes. Now on the RHS side, this 5 into sulfate, 5 SO4 minus 2. Electrons got cancelled. Come down to this reaction. 2 Mn plus 2. So I have to write Mn plus 2 here also 2, isn't it? Yes, 2 Mn plus 2. Yes. So 2 Mn plus 2. Done. Now important, here how many protons do we have? You have only 6 protons on this side. So this should again be 3H2O only, because 3 into 2, 6 protons here. So don't try to multiply here, because already 6 protons, we have already made it half for 3 this one, and taken as 3 into 2, 6 protons here, 6 hydrogens here. So this is your reaction, converting sulfite to sulfate. Now we are going to learn one more oxidizing property, that is your oxidation of hydrogen sulfide to sulfur. Okay, this is a little bit simple it is. Now here in the exam, how do they give this? Now in the exam, when I have to see this particular question, you have to balance it by half cell reaction method. That is what we have studied in all these videos. Now exam, it will be given as write or show. Okay, show oxidizing property of KMnO4, where it has to convert hydrogen sulfide to sulfur. This is what is given. Don't get confused. Nothing is there in this. So simple. You have to first take hydrogen sulfide. Hydrogen sulfide will first dissociate into 2H plus plus S minus 2. Now this is your S minus 2 sulfide, which is going to combine with MnO4 and finally precipitate sulfur out. Let's see. Now in your step 1, write the skeletal reaction. So what is the skeletal reaction? S minus 2 plus MnO4 minus. I very well know, okay, let me, right, okay. Yeah, I very well know sulfide to sulfur. So write what? Elemental sulfur. The manganate to Mn plus 2. That's understood common. Every time it is Mn plus 2 only. So Mn plus 2. Find step 2. Calculate oxidation numbers. I already did x plus 4 into 2 minus 1. X is equal to plus 7. So I've got manganese is plus 7. So erase this. Now first, plus 7 to plus 2. Minus 2 to 0. Elemental sulfur, isn't it? Yeah. Now from plus 7 to plus 2, how many? It has gained 5 electrons because oxidation number is increased. It has taken 5 electrons and then it has come down to plus 2. Next, from minus 2 to 0. How many electrons has it lost? It has lost 2 electrons. Done. After this, let us write step 3 now. In step 3, try to make oxidation reaction and reduction reaction. Oxidation is sulfur is giving me S plus 2 electrons. Reduction, copy this MnO4 minus. It's forming Mn plus 2. And how many electrons? It has gained 5 electrons. Now, this is almost, we are almost coming closer to this reaction. Now, what should we do? In step 4, try to club both the reactions. MnO4 minus plus 5 electrons giving me Mn plus 2. Now, in step 5, 4 and 5, you will balance the oxygen atoms. Now again it is acidic medium, I said. You have to say the proton should be there on the LHS and water should be there on the RHS. Now observe here, how many oxygens do we have? 4 oxygens. So try to balance with 4 water molecules here. Now immediately as soon as you balance water molecule or oxygen, you have to balance hydrogen, that is proton. Now oxygens are 4, protons are 8. 8 protons. Done. In step 5, now step 6, you will cancel electrons. How do you cancel electrons? Put a bracket for both. Now here to cancel this electron, multiply with 2. To cancel this electron, multiply with 5. So this electron, this 10 electrons here and these 10 electrons get cancelled. Now try to write the overall reaction. Now pick up the overall reaction. So what do you have? You have 5 sulfur, correct? Now come down to the product. 2 MnO4 minus, 2 MnO4 minus. There's nothing here. Come down. You have protons. 8 to the 16. 16 protons giving me 5 sulfur. 5 sulfur. Okay, let us write that as last. Okay. After that, manganese is 2 Mn plus 2. 2 Mn plus 2. Water is 4 to the 8. 8 water molecule. That's it. This is your complete reaction for converting or oxidizing sulfides to sulfur. This is the most important. Most of the students get confused here. They pick up hydrogen sulfide and start doing. Don't do that. First write, dissociate into sulfide, then add it to your right. So let's come back and do one more oxidizing property, that is your conversion of iodides to iodine. So here we are going to convert in your reaction I minus using MnO4. This is your question basically. This will be your question in the exam. I minus MnO4. Now I said iodide to iodine. plus manganate to Mn plus 2. This is your reaction. Now exam what is given, these two are given. You should remember the products. Iodides will get oxidized to iodine and MnO4 minus gets reduced to Mn plus 2. So in your step 1 you have to calculate oxidation numbers. Same. Here it is -1. Already it is my 1 given. Now we've already calculated the oxidation number in the previous video, isn't it? How much did I get? Manganese plus 7. Now come back. Already manganese is plus 2 here. Here iodine 0. Understood, isn't it? Done. Now start in step 2. Try to see which is getting oxidized and which is getting reduced. Now always Mn plus 7 to plus 2. It is undergoing the reduction process by 5 units. It has gained 5 electrons. 5 electrons. Now from -1 to 0. Right? So -1 to 0. Done. 1 electron, isn't it? It has lost 1 electron, but for 2 iodines, 2 electrons. Okay, we'll see that. It has lost 1 electron. Done. Now in step 3, you are going to write oxidation half cell reaction method. Oxidation half cell or oxidation reaction and reduction reaction. Now I said manganese always undergoes reduction. Why? Higher to lower oxidation state. Now write that MnO4 minus to Mn plus 2. How many electrons has it gained? 5 electrons. Come back to this part. Take this iodine, I minus. It has lost 1 electron, isn't it? But first, after writing this electron, try to balance iodine 2. Now for 1 iodine, it was 1 electron. For 2 iodines, it will be 2 electrons. Now I'm done with step 3. Let me come back to step 4. In step 4, you have to now balance your oxygen atoms. Then try to balance your electrons. Done. Now minus I2 plus 2 electrons. MnO4 minus plus 5 electrons gives me Mn plus 2. Here there are no oxygens. Here there are 4 oxygens and there's nothing on the RHS. Yes or no? So 4 oxygens. So you're going to write 4 water molecules. Now how many do we have here? 4 2s are 8 protons. Here, careful. 8 protons. Done. Now in step 5, you're going to balance the electrons. Into balance electrons or balance and then cancel the electrons. Now put a bracket for this both. Here there are 5 electrons, here there are 2. Cross multiply 2 here, cross multiply 5 here. So that these electrons on the RHS and these electrons on the LHS gets cancelled. Now write step 6, write the overall reaction. Careful now, it will be very, most of the students do mistake here only while writing the overall reaction. First, this is 5 into 2, 10. 10 I minus plus. There's nothing on the reactant side, come down to products. 2 MnO4. 2 MnO4 minus. Electrons got cancelled, you have protons multiplied. So 8 to the 16, 16 H plus. Let's come back to this side. Here you have 2 manganese, just see. And okay, iodine is also there, isn't it? Now first iodine I, 5 I2 plus 2 Mn plus 2 plus water molecule 4 2s are 8 water molecules. Now let's come back and check whether we have written it correctly or not. 10 correct, manganate yes, 16 correct, 2 manganate correct, iodine 5 correct, and water molecule correct. So this is how you're going to, this is how permanganate is going to convert iodides to iodine by half cell reaction method. Right, so now one last oxidizing property of your KMnO4, that is an acidic medium. Now here you're going to oxidize nitrite to nitrate. So nitrite is NO2 minus and your nitrate is NO3 minus. Simple. So NO2 minus 2 getting oxidized to NO3 minus. I have to show that. Now, as I said in your paper, what will be given? Your skeletal, let us write with the step 1 reaction. Your skeletal reaction, MnO4 minus plus NO2 minus will be given. Or they may ask you, show the how is oxidation of nitrite to nitrate carried in the presence of KMnO4. That also they may ask you. So remember this formula. Now, I already said manganate gets reduced to Mn plus 2. It's the same for all. And your nitrite to nitrate formula is NO3 minus. Now let us start with the step 1. So in step 1, you're going to calculate oxidation number. So we've already calculated oxidation number for manganese in the earlier video. This has got plus 7. Now let's write for this. Take nitrogen's X plus 2 into, correct, plus 3. Let us come back to this. This is already there. Now here, three into valency of oxygen so I'm going to write plus 3 here. I'm going to write plus 5 here. Erase this. Now come back in step 2. I have to see which is getting oxidized and which is getting reduced. I always said manganese will undergo reduction. This will undergo oxidation. So plus 3 to plus 5, it has lost 2 electrons. Plus 7 to plus 5, it has plus 2. Plus 7 to plus 2, it has gained 5 electrons. So write everything. Now in step 3, I'm going to write half cell reaction. In step 3, write down oxidation half cell reaction and reduction half cell reaction. When I have to write both, pick up the oxidation reaction. Where is oxidation reaction? This one, your nitrite. So NO2 minus giving me NO3 minus. Now here on the reduction side, minus giving me manganese. Now how many electrons has it gained? It has gained 5 electrons here. Now here how many electrons has it lost? 2 electrons. Yes. Now club both the reactions. You have to club because I have to balance oxygen after this step immediately, isn't it? Now club both the reactions here. Minus 3 plus 2 electrons and write that MnO4 minus plus 5 electrons giving us Mn plus 2. We are almost coming closer to the reaction. Just see a nitrate, I have to cancel the electrons and I'll get that. Now here how many do we have? We have 4 plus 2. 6 oxygens. So on this side I have to write, so 3, let me see whether I've written it correctly. MnO4, 4, 5, 6. Okay, 6 here and here already 3 are there. This is 6 and this is 3. So I have to only write 3 water molecules. Correct. After this, I have to balance the protons. Protons 3 to 6. So LHS, protons are less. So I write 6. Now in step 5, you're going to cancel the electrons. Now this is 5, this is 2. Multiply with 5 here, multiply with 2 here. First, this electron and this electron gets cancelled. And this electron, this one gets cancelled. Now start writing the final reaction. 5 NO2 minus plus 2 MnO4 minus. Now I have to balance the protons. You be very careful now here. Now observe, suppose if I've written 6 here, 6 2s are 12 protons will become. But here how many do we have? You have only 3 2s are 6 protons. So that is the reason you have to be careful here. This will not be 6 protons. This will be 3 protons only. Once again, here I have taken 6 oxygens. Done. That because so 3 oxygens, 3 plus 3 6 and how many? Yeah. So I have to balance this 6 here and I have to balance this 6 here. Done. But I have to be careful with the protons also because protons are only 6 on this side. If I multiply 6 here, it will become 12. So try to multiply with 3. So copy that 3 into 2, 6 protons, giving me 5NO3 minus 5NO3 minus 5NO3 minus plus 2Mn plus 2Mn plus 2 plus. Now observe 2, 3 2s are 6. Okay, now again same thing. If I have to multiply here, I did, but the same thing if I try to multiply 3 2s are 6, the balancing will be not proper, isn't it? So 3H2. This is what we did. The same thing. Now let's see. 6 protons, 6 protons. Nitrogen 5, nitrogen 5. Oxygen 5 is a 10. 8 done. 8 and 11. Yes, done. So have we got the earlier reaction? Yes, we did. Yes, so students, welcome back to one more session of your KMNO4 topic. We've already studied the chemical properties, that is oxidizing nature of KMNO4. I've shown you in acidic medium as well as in neutral medium. Yes, so now let us come back and learn the preparations as well as structures of your permanganate and manganate ion also. So when I have to learn about the preparation of KMNO4, most important thing is you are going to learn all the 4 preparations perfectly, because in your NCERT only one is given. Let's see all the 4. So different combinations, anytime anything would be given to you. So let us start and write the subheadings of the preparation. So when I have to prepare KMNO4, it can be prepared both by commercial method and it can also be prepared in the lab. So lab method. So in between you have 2 more methods, that's also in the lab. But let us see, whenever I speak about commercial method, the method or this particular thing, I'm going to obtain KMNO4 from the mineral called pyrolusite. So the mineral of KMNO4 which I'm going to take, that mineral is called pyrolusite. And the formula for pyrolusite is MnO2. I'm going to use that to prepare KMNO4. Done. After that, I'm going to show you a lab method. This is also a lab method, but particularly that process is called electrolytic oxidation. Oxidation method. Yes. After that, I'll be showing you something called chemical oxidation method. Done. Last but not the least, in the lab method, we are going to prepare KMNO4 from peroxodisulfate. So remember, lab method is from peroxodisulfate. Yes. So this is important. Yeah, I'll be doing one after the other, each and everything. Try to reason also wherever it is required. And most important thing, please learn it as and when I upload the reactions on daily basis. Then only your syllabus will be done. Yes, let's meet again with your first method, that is commercial method for preparation of KMNO4. Right, let us start with the first preparation, that is a commercial method of preparation for KMNO4. So most important thing in the exam, remember this question may be asked directly, or they'll ask you just write the commercial method of preparation of KMNO4, or they may give you in the form of a paragraph and ask you to write that formula. Done. So whenever you're writing commercial method, suppose if you don't remember the reaction, at least try to write it in words. So let us write in words first, then come back to the reaction. So commercial method, in commercial method, I'm going to use so in this particular thing, I'm going to use a mineral of potassium permanganate. That mineral is called pyrolusite, right? So as I already said, pyrolusite is a mineral and the formula for this is MnO2. I'm going to take that pyrolusite. Let us write in words now. So how will you write in the exam? When pyrolusite is treated, okay, when pyrolusite, right, is treated with potassium hydroxide, a strong base, or potassium nitrate, or potassium chlorate in the presence of oxygen, it yields, means it gives or it forms, it yields a green colored solution green colored solution, that is potassium manganate, which on further electrolytic oxidation is going to yield will produce three important products. One, potassium permanganate, comma, your potassium hydroxide back, and hydrogen gas. Okay, I've written such a big paragraph. Why did I write this? For some students, if you can't practice the reaction, suppose if you can write the theoretical part, at least you'll get 30% of the marks. Remember that. Next important thing, second reason for me writing this is, if they're giving you in the form of a paragraph based question, if such question is given to you, you are supposed to see that question, write the answer. That is the reason I've written this whole thing. Let's see. Right, okay, pyrolusite is MnO2. I'm going to add, is treated with a base. Okay, pick up any one base. Potassium hydroxide is strong base. Now I'm going to roast it in the presence of oxygen. So when you're roasting in the presence of oxygen, suppose if I take this as 2 moles. Yeah, then what happens? This potassium permanganate is going to react with this and forms a salt, that is K2MnO4. Higher oxidation state. Observe, this is a green colored solution which is formed, and this is called potassium manganate. Along with that, you're going to also get water out. Let us now balance and see whether it is correct or not. So first, when balancing, now I've taken 2. Then, okay, let me take this as 4. When I'm taking this as 4, this will be 2. Right. Now I have to balance hydrogens here. Manganese is 2, done. Potassium is 4, done. Now let us balance hydrogen. Hydrogen is 4. So if I put 2, okay, let us see oxygens are balanced or not. Now here it is 4 oxygens, 8 oxygens, 9, 10 oxygens on this side. Here 4 to the 8 oxygens, 2, 10 oxygens on the other side. Done. This is a perfect reaction. So I'm going to still not prepare KMnO4. Now what am I going to do? I'm going to take that 2 KMnO4 and perform a reaction called electrolytic oxidation. This is important. In electrolytic oxidation, we are going to take the green solution and to this in the presence of water. Yes, you are electrolyzing it in the presence of an aqueous solution. So when you are electrolyzing it, it's going to break up. Now this is going to break up into the respective ions. First most important thing, your KMnO4 comes out. After that, one has come out with the same KMnO4. Now water is HOH, isn't it? So there is one more K here. That K will come out as KOH. This is done. Okay, KMnO4 is done. There is one more K and that K. Okay, let us not write first only 2. Okay, one K has come out as KMnO4. One K has come as KOH. Now what else is left? You are left with hydrogen gas. Hydrogen gas. Done. So this is your potassium permanganate. Potassium permanganate. Now let's see if I have balanced. Now potassium is 2 here. Okay, now here potassium is 2. Done. Manganese is 1 here. Manganese is 1 here. Done. Oxygen is 4 plus 1, 5 here. Oxygen is 4 plus 1, 5 here. Done. Now hydrogen, how many are there? If I have to take hydrogen is 2 here. Hydrogen is 2 here. Oh, I think the reaction is almost balanced, I believe. Yes, 4 plus 1, 5. 4 plus 1, 5. Yes, it is balanced. Yes, this is your first preparation of your KMnO4. Right, let us come back and learn the next preparation methods of your potassium permanganate. Simple. So in chemical oxidation method, I'll just write a simple equation. If it is, I think, please memorize it. It's very easy actually. In chemical oxidation, I'm going to again take the same K2MnO4, that is your potassium manganate. And what am I going to do? I'm going to introduce chlorine gas to this. When I introduce this chlorine gas, immediately what happens? Chlorine comes out or precipitates out as potassium chloride salt. Done. Along with this, now what it does is I'm going to take 2 moles of this. So total of 4, isn't it? Now this particular thing, potassium with KCl2 comes out as potassium chloride, and the leftover, now we still have 2, isn't it? Total 4, 2 have already come out. We have 2 potassiums that comes out, precipitates out as 2KMnO4. Now this is your purple colored solution. Now this is further evaporated, right? And, and when you try to evaporate this, it's going to form crystals of KMnO4. Purple crystals of KMnO4. This is how we are going to prepare from chloric gas. Now, next important thing here, electrolytic oxidation. Electrolytic oxidation, whenever we speak about electrolysis process, we just speak about dissociation into anion, cation going to a cathode and anion going to the anode, and finally writing the total reaction. Yes or no? Let's see. So in electrolytic oxidation method, important thing, you're going to pick up your potassium manganate. This one I'm going to take the whole thing in an alkaline medium. When I take it in an alkaline medium, this is going to dissociate into 2K plus plus MnO4 minus 2. Correct? Yes. Now this is your manganate ion. Now I said alkaline medium, the solution part. So water also dissociates into 2H plus plus OH minus. Right, now basically it is like this, isn't it? H2O. If you like, we should write like this, H plus plus OH minus, not a problem. But okay, write like this. I'll tell you what to do later. Right, better. Now what's going to happen? Now this is your anion and this is your cation. Now try to make 2 cell reactions. Anodic reaction first, where always oxidation process occurs. Cathodic reaction, where always reduction process occurs. Oxidation is loss of electrons, or reduction is gain of electrons, isn't it? This is loss of electrons. Reduction is gain of electrons. This is what you've studied, isn't it? Oil rig. What is this? Oxidation is loss, reduction is gain. Common thing which you have studied in your schools. Done. Now here, anodic reaction, what will come here? Anion is going to come, and cathodic reaction, cation. Now what is anion, this reaction? MnO4 minus. So MnO4 minus 2. What is this ion? This is your manganate ion. So manganate ion, what is the color of manganate ion? It is green color. Further, it's going to get converted because it is going to lose electrons. How many electrons is it going to lose? This is going to lose MnO4, isn't it? It's going to lose, just see. First, it's going to get converted to MnO4 minus 1. 1 electron has already gone. It has to lose 1 electron, so 1 electron here. Now observe, this is manganate ion. MnO4 minus 2 is manganate. Now MnO4 minus 1 is permanganate ion. This is MnO4 minus is permanganate ion. The color of manganate, manganate is green color, and the color of permanganate is purple, which you are seeing. Done. Now, how many electrons are here? 1 electron. Now, from anodic compartment, this electron travels to the cathodic compartment. What cation do we have? We have H plus. This H plus is going to pick up this electron here, and it's going to become H, hydrogen. Now, when I have to take 1 more hydrogen, this combines with 1 more hydrogen. Okay, let us write 2 hydrogens. Yes, because if I take 2 here, it will become 2H, isn't it? So, 2 hydrogens will form hydrogen gas. This hydrogen gas evolves out of the cathode. Now, still we are not done. We still have not prepared the potassium permanganate. Now, this potassium permanganate, this permanganate and this potassium together combines. It is there in the reaction cell, isn't it? So, these are taken and finally they are concentrated. Means they are going to concentrate it to that certain time till that all the moisture, whatever is there, everything evaporates out, and that during this concentration, the process of evaporation takes place. Yes, this evaporation, once it is evaporated, you are left out in the test tube. What is left out? Or in the beaker, the left out is the crystalline form of KMnO4. So your KMnO4, this MnO4, this K, the crystalline form, you get as a purple color crystal. purple colored crystals. That's it. So hydrogen gas already escapes out, or between it is in the cathodic compartment which escapes out. I'm left with potassium permanganate, purple color crystals in the electrolytic cell, which can be, because already they've taken and evaporated, and we have finally got that compound which we are trying to prepare. So now this is one preparation for chemical oxidation method. This is one preparation electrolytic method. Now let us meet again with the lab method for preparation of KMnO4. Right, let us come back and learn the lab preparation. Here you have a specific reaction where I'll be showing you the ionic reaction also. Please note it. I've already done the ionic reactions under oxidizing properties of KMnO4. The procedure is the same. So once I write the reaction, I'll also be showing you that reaction. First, watch that video. Please come back to this video. Now in lab method, we are going to perform the oxidation process using peroxo disulfate. So what is this peroxo disulfate? Let's see. So peroxo disulfate, when I have to write the structure, first let us write the formula. Formula is S2O8. How does this look? Now this is your sulfur. 2 atoms are here. Now you have to distribute this oxygen atoms between both sulfurs. First double bond O, double bond O. One more double bond O, double bond O. 4 are done. We still have 4, isn't it? Now 1 oxygen here. 1 more oxygen here. So 1, 2, 3 here, 1, 2, 3 here, 6 are done. We have left with 2. So this is going to form a bond. This is your peroxo disulfate. Peroxo, because you have a peroxide linkage here, peroxo disulfate. Now, first important thing, you're going to just cleave the bond here. When you cleave the bond, what do you get? S. Now this is one SO 1, 2, 3, 4. Correct? Right? So 2 becomes S2O8. Just see. SO4 becomes S2O8. Done. Now you're going to add, or we are going to pick up that Mn+2 ion. Here Mn+2 is getting oxidized to its state, to the next state. So what will happen? This whole process occurs in the presence of an acidic medium. So this reaction is an acidic medium reaction. The acidic medium reaction means you should compulsory have the presence of H+ ions in the reaction, as I've shown you in the oxidizing property. First I'm writing the products like this, then I'll show you the reaction, the whole ionic reaction. Now S2O8 done. Now along with this the aqueous medium. Now this whole thing, when I have to write the final reaction, just simple as of now, remember, this Mn+2 is getting oxidized to a higher oxidation state, MnO4 minus. Now here it is +2. Now here when I have to calculate, this is x plus 4 into -2 is equal to -1. X minus 8 is equal to -1. X is equal to +7. So here the oxidation state is +7. Higher oxidation state. Done. So now after this manganese, this one, peroxo disulfate gets getting converted to sulfate ion. I have not still balanced it. The leftover, suppose if you're not writing it specifically, you can also write like this, HSO4 minus. This is also fine, not a problem. This product also is correct. Right? In your textbook, they've given us H plus and SO4 minus 2. So together, I've written as bisulfate ion. Simple. This Mn+2 to higher oxidation state Mn+7 from S2O8, this is combining and forming bisulfate. Now we'll see how should I, now this is acidic medium, isn't it? Bisulfate ion. Now I'll show you the mechanism. How are we going to balance this reaction? So as of now, remember, peroxo disulfate, it is also called oxyanion. Why is it called oxyanion? You have oxygen linkage, yes, and anion, it's linking with oxygen, which is oxygen is anionic form. So oxyanion. Now next important thing, here Mn+2 to +2 to +7. It's going higher oxidation state. Yes, hence oxidized. Yes, done. The S2O2, it's going to form SO2. Now let us write the mechanism and see how are we balancing this. Right, so I've done the balancing of the reaction as I already explained in the oxidizing property of KMnO4 in acidic medium. So based on that, I've already done it and kept it for you all. So it's the same step which I've done, one after the other, finally cancelling electrons. So please note it carefully. It's again I'm specifying same procedure. Don't get confused. So once I've done, I've got the final equation as this. This is your final balanced equation. So go through each and every step. Any doubts, please let me know in the comment section. So I didn't want to repeat it again. Done. So this is your final reaction. So I try to, this is the first reaction which you have written. This is your final reaction which you have written. Now ma'am, should we practice it for the exam? Like, if you really want to practice it and know the final product correctly, if you have time, you can do it. But otherwise, if you still have the capability of calculating very quick, so this is your final reaction when peroxide disulfate reacts with Mn+2 in your acidic medium. So please note it. Right. Let us come back and learn the structures. Till now we have learned the preparations or commercial method, lab method of KMnO4. We also done the chemical properties, that is oxidizing properties of KMnO4. Done. Let us come back and end the topic with structure of manganate and permanganate. Very important in your DNF block, in the P block, structures are very important. Please do practice it. So whenever I say manganate ion and permanganate ion, simple, important thing. Manganate is MnO4 minus 2. Charge, because we have got it from potassium manganate, isn't it? K2MnO4, where we have broken into 2K plus and MnO4 minus 2. So MnO4. Permanganate is MnO4 minus. Remember this. This is minus 2 and this is minus permanganate. And when I have to draw the structure, simple. Both are similar, only light difference. Mn here, again manganese in the center. Then you have 4 oxygen atoms. Observe. First oxygen atom, suppose, okay, let us start from here. Let us start from here. First, one oxygen atom, double bond. One more oxygen atom, double bond. You're left with 2 oxygen atoms, isn't it? Now, one oxygen atom here, one oxygen atom here, minus and minus. 2, 4 done. So, minus 2 is a charge. Now, when I have to come back to permanganate ion, the same thing. Now, 4, there's only one oxygen atom with minus. Observe carefully. So, one oxygen double bond, one more oxygen double bond, one more oxygen double bond, and the 4th oxygen atom is 1. Just observe. Oxygen minus 1. What are you observing? Both are, they have a shape of tetrahedral, isn't it? Isn't it tetrahedral arrangement? So, they are tetrahedral. The shape is tetrahedral. Here also the shape is tetrahedral. Yes. Now let us come back and see. We've already studied the color of manganate ion is green, isn't it? This is the green colored ion. Green. The color of permanganate is purple. Simple. Next important. When I see the structure, okay, this is going to show resonance, isn't it? So when I see the structure of this, how many unpaired electrons does it have? It has 1 unpaired electron. Yes or no? Because this is going to shift here, this is going to shift here. So there's only 1 unpaired electron. So, okay, it has 1 unpaired electron. Now, when you observe here, how many do you have any unpaired electron? No, isn't it? Because this is going to shift here, this is going to shift here. So, important, no unpaired electron. Come back. In this particular thing, when you have 1 unpaired electron, what is the magnetic property of this? Magnetic property. When there's unpaired electron, we call them as paramagnetic in nature. When I have to see this magnetic property, it is diamagnetic in nature because it doesn't have diamagnetic in nature. Simple, isn't it? Nothing. Just remember, please try to draw and learn this ion. Try to draw the structure, both, and try to write the parameters which are important. 1, 2, 3 parameter, 1, 2, 3 parameter, more than enough for your structure. So let us come back and do the preparation of KMnO4. Basically, when you do your preparation of KMnO4, such questions will be given to you in the form of a paragraph. What do they want us to do? These are called as identification type questions. They want you to read the question and write in the form of equations or the reactions and identify A, B, C and D, whatever is the requirement. So you have to be very careful while doing such questions. Important thing is you have to read line by line and keep noting what is given to us. So I'm going to prepare prepare today KMNO4 with your from your ore called chromite or ferrochrome. Okay, important. First, let me divide the page into 3 because I need place. Done. So when I'm going to divide the page into 3, first important thing I have to remember, what is iron ferrochrome or chromite ore? Your chromite ore or your ferrochrome both are same. Formula is FeCr2O4. This is ferrochrome. I'm going to use this and prepare our orange crystals of potassium this in dichromate. Let's start. In your step 1, let us read what is given to us. When a chromite ore is fused with sodium carbonate, so this is what is I require FeCr2O4. What is it fused with? Fused with sodium carbonate, Na2CO3 in free excess of air, in excess of oxygen, and the product is dissolved in water. So they want us to write the product first. So when I have to write the product, just see, this sodium is going to replace this iron, and now what did I say? What is this? This is called chromite, ITE, or ferrochrome. Now when sodium is reacting with this sodium is going to replace the iron metal, right? And immediately, because this is highly reactive than iron, so this is going to replace this iron and it's going to form a complex. This is going to undergo higher oxidation state, that becomes Na2Cr2O4. Okay, yes. Now, what is this compound, right? This is, no, I should write CrO4 only, no? Oxidized, yes. So, chromite ore, and this is called now sodium chromate. Chromite to chromate. Observe, chromite is this one, chromate is this one. Now, after that, along with that, your iron is going to combine with oxygen to form Fe2O3. Now observe, the difference between this and this is water soluble compound and this is water insoluble. Okay, done. Now what did they say? And the product is dissolved in water. Okay, now they want me to take this product and dissolve in water. So there are 2 products. So I said this is water soluble. So whichever is soluble, you're going to take this soluble product, that is your Na2Cr4, and dissolved in water, right? It's going to be dissolved in water and compound B is obtained, it seems. Fine. So Na2Cr4, when you are trying to dissolve in water, compound B is obtained after treatment of this yellow colored solution with sulfuric acid. Okay, they said this is water soluble. Don't get confused. They dissolved in water means this is already water soluble, and they already gave me, it is an yellow colored solution. Yellow solution they've given. Okay, let us write according to their norms. Yellow solution. Done. Now this yellow solution, water soluble one, after treatment of this yellow colored solution with sulfuric acid. Okay, now I have to take this yellow colored solution and I have to treat it or acidify with sulfuric acid, H2SO4. Till here. Done. Now compound C. Okay, now let me first write the products. When you're taking this, important, you're acidifying it, isn't it? When you're acidifying it, this is going to the higher oxidation state. What is that higher oxidation state? Na2Cr2O7. Yes. Now plus the leftover sodium is forming Na2SO4. Done. Now let me name this sodium dichromate. Now what is the difference? Earlier it was chromite, then it was chromate, now it has become dichromate. The compound C can be, now this compound C can be crystallized from the solution. Now when compound C is treated with KCl, now if you're getting confused, what you do, first you've got compound A, try to name this as compound A. Done. You've got a yellow colored solution, this is yellow colored solution, compound B. You're going to take the same compound B and treat it with sulfuric acid, you get compound C, isn't it? Yes, compound C. Now take that compound C, because I'm here. Compound C can be crystallized from the solution. Okay, this can be crystallized, it seems. When compound C is treated with KCl. Now take this compound C, Na2Cr2O7, compound C is treated with KCl. Now what is this KCl doing? KCl is going to replace this sodium now and forms K2Cr2O7 and your NaCl is out. Your NaCl is there. Now here important thing, you have also water also extracting, isn't it? Yes, water also is important. Now your case. Now they said compound C is treated with KCl, orange crystals of compound D are formed. This is your compound D, which is an orange crystal. Identify A, D and also explain. Yes, this is your whole concept. Now let us summarize and write. What is compound A? After writing everything, you are going to please write it like this. Compound A is Na2CrO4. Okay, no. Compound A is ferrochrome. No, I'm sorry. FeCr2O4. What is compound B? Compound B is Na2CrO4. What is compound C? Na2Cr2O7. What is compound D? Compound D is K2Cr2O7. That's it. This is how you are going to solve the whole equation. Let us come back and learn the structure of chromate and dichromate ion. Right. So, as we have studied in potassium permanganate, manganate and your permanganate ions, here you are going to study about chromate and dichromate. So, whenever I speak about chromate ion, the formula for this is just see Cr O4 minus 2. The overall charge is minus 2. Here when I have to speak about dichromate, just see this is chromate. Now 2 chromates, isn't it? 2 chromates linked together, it is Cr2O7 minus 2. So this is your charge and this is your whole formula. Let us write the structure. So when they have asked me to write the structure, just see, as you have seen, there are 4 oxygen atoms surrounding chromium. So chromium is a central metal atom. Done. Okay, let me not write this like this. Let us write in this way. Done. Now you have 4 oxygen atoms distributed. Right, 1 above and 1 below. 1 more oxygen atom here and this 1 more oxygen atom here. Done. The whole charge, as I said, minus 2. Done. So when I have to join these, how is it looking? It's just looking like a tetrahedral structure, isn't it? Yes. Okay. Right. So this is basically looking, so the shape of the molecule is tetrahedral. Tetrahedral. Now when I have to come to dichromate, 2 chromate ions are going to combine together to form a dichromate ion, right? Both interconvertible. So chromate on further forming just like a dimer. So the same chromate, draw the structure, right? Now just see Cr, okay, 1 more Cr. Your double bond is still existing here. Your double bond is still existing here. Your 1 more double bond is again existing. Here also 1 more double bond existing. This oxygen atom is still existing there. This oxygen atom is still existing here. Now how many are over? 3 plus 3, 6. I have to make 7. The 7th oxygen atom is going to form a link between these 2. Yes, so this is your dichromate ion. Just see, now just join like this. You can, okay, if you wish to join like this, and just like I have shown it, if you wish to join, you can join the ring, not a problem. Tetrahedral here also. Okay, so this is your dichromate ion. Now when I have to see, this is also tetrahedral but arranged in like in the form of a dimer. When I have to write this structure without no bonds, it's simple representation. You can also write like this, make Cr, right? So 1 oxygen, 2, 3, 4. Yes, minus 2. Then when I have to write this structure, how does this look like? It looks like Cr linked with oxygen, 1 more Cr, 1, 2, 1, 2, 3, 3, minus 2. So this is the electron. So most important. Here what's happening? Here chromium and oxygen bonds. When I have to see, all chromium and oxygen bonds are equivalent, isn't it? All are equal. So Cr all, okay. All Cr bonds are equivalent, means equal. But when I have to see dichromate structure, just see. Now, as I said, this is equal, this is equal, this is equal. But this particular bond, what am I trying to speak? This bond, yeah, from the CR-OCR bond. When I have to see the bond length, observe the bond length here, or the bonds are longer. Why are they longer? Let's see. If I have to come back and write, now your CR is like this. Now this is your CR, this is your CR, isn't it? Now from here till here, the bond length was observed to be 179 picometer. Okay, here and here, same. But when I compare this chromium and this chromium, this oxygen, I'm talking about this. This is only 163 picometer already. You see? So all are 163, 163, 163 picometer, but the center carbon where chromium where it's forming oxygen bond is 179 picometer. That means I'm trying to explain one important concept. In dichromate, you have two types of bonds. One is a longer bond, that is CR-O bonds are longer, and the other which is forming is 163 picometer shorter bonds. That is important. So here all are equivalent, but CR-O-CR bonds are longer and CR-O bonds are shorter. That's it. Important thing to remember. Now, when I have to come back to the structure, as I've said, okay, -2 charge, there also -2 charge. That's more than enough for you to explain the whole structure of chromate and dichromate. So now let us start with the chemical properties of potassium dichromate. So most important thing you have to remember is three things. First, what is the formula for chromite? What is the formula for chromate? What is the formula for dichromate? Okay, let us see once again. If you are speaking about chromite, ITE, okay, let it be the combination with aluminium or as I said, sodium or iron. But if I speak of iron, chromite, Fe, okay, FeCr2O4. This is your chromite. Please remember. When you are writing or about chromate, chromate formula is CrO4 -2. If you are writing the formula for dichromate, the formula is Cr2O7 -2. Most of the students, they get confused here. Please don't get confused. Simple it is. Right. So when I have to see the properties, chemical properties of potassium dichromate, it's same like potassium permanganate. This is also an oxidizing agent. Then we are going to see a list of oxidizing properties of potassium dichromate, and let's start with the first one. Now here I have written one important reaction, decomposition reaction of potassium dichromate. What is going to happen when you are trying to decompose potassium dichromate? Let's see. So whenever you are taking potassium dichromate, it's going to decompose on heating. It's going to decompose into three important products. One is your potassium chromate, okay, plus chromium 3 oxide plus oxygen. Three important products are going to form. Let's see, what are they? Potassium dichromate formula K2Cr2O7. You're heating it. It's going to decompose into three products. I said potassium chromate. Okay, K. What is chromate formula? I've already given K. Okay, K2Cr4 plus chromium 3 oxide. Chromium, yes, 3 oxide. Okay, see, this is oxygen. The valency of oxygen is 2. The valency of chromium is 3. This is chromium 3 oxide plus oxygen. Simple, isn't it? Yes. Let's come back and see the oxidizing property. When I have to see the oxidizing property, your potassium dichromate K2Cr2O7 is going to oxidize, a list of oxidizing reactions we have. First important, dichromate, because of the release of the nascent oxygen, this dichromate is going to liberate your iodine from Ki. Okay, yes, Hi also. Okay, not a problem. We can write Hi also. It's going to liberate that iodine from Hi. Next important, this is going to convert or oxidize Fe+2 to Fe+3, higher oxidation state. Loss of electrons, isn't it? Oxidation done. It's going to also convert Sn+2, stannous to Sn+4, higher oxidation state. And next important reaction which we are going to study, it's going to convert hydrogen sulfide to sulfur. So these are the list of reactions which I'll be doing one after the other. It's going to take time, but please and try to understand carefully. We are doing one time preparation. Let us not be in a hurry to complete the chapter and finish off. Let us understand so that you will get full marks in the board exams. Let us learn the last oxidizing property of your potassium dichromate. So again, when I take hydrogen sulfide, now it's going to oxidize it to sulfur atom. Now here what happened? 2H plus plus S minus 2. Now the valency of this is 0, isn't it? Sulfur atom. So oxidizing property, let's see. Now whenever I take potassium dichromate, done, you're going to add, as I said, sulfuric acid, which is acting as an oxidizing agent. And you're adding H2S to this. When you're adding H2S to this, it's going to again form the same products, but only difference is this part you have to be careful. K2SO4, it's the same as I said in the earlier video. Cr2SO4 taken, this is 3. Sulfate valency 2, chromium valency 3. Apart from that, water and hydrogen sulfide here, it is 1 into 2, this is minus 2. This is going to get oxidized to sulfur atom. So this is your important thing. Simple, done. Now let us come back and see with stannous, Sn plus 2. This is stannous, this is stannic. So if I take stannous chloride, SnCl2, stannic chloride, SnCl4. Now let me write the ionic reaction of this so that you will understand why I am writing all these. So when I take potassium dichromate, when I break this potassium dichromate, K2Cr2O7, it breaks up into 2K++ Cr2O7 minus 2. Correct? Now I'm going to take this ion Cr2O7 minus 2. I'm going to add, or acid in the presence of acidic medium, I'll take H+. I'm not writing the whole thing, I'm writing the ionic reaction. Plus, I'm going to take the stannous chloride Sn plus 2. Now, I said this is an oxidizing agent. Now, let's see this also. We are going to get what products. Important. First, I said stannous gets oxidized to stannic. So, Sn plus 2 becomes Sn plus 4. Done. What is the valency here? Chromium is 2x minus 7 into minus 2. Minus 2. So 2x 14 minus 2. 2x is equal to minus 2 plus 14. 2x is equal to, I got 12. X is equal to 6. Let's see once again. This is 2x, 7. This is plus actually. 7 to the 14, 12. This is 14, 12. 2, 16, 6, 12, 6. Here what did I get? I got a valency of plus 6. Done. Now what happened when this is undergoing oxidation reaction? Cr plus 6 is getting converted to Cr plus 3. What happened now? It has gained electron. Yes or no? So this is from plus 6 to plus 3. It has gained 3 electrons. Now your Sn plus 2 has lost 2 electron. Yes, that is what you have to do now. This is undergoing which reaction? This is undergoing oxidation reaction. And this chromium is undergoing reduction reaction. Just see, reduction, it is a gain of electrons. Oxidation, loss of electrons. And your H plus, to balance H plus, we are going to add water. Ionic reaction, yes. So now we are left out with your balancing. Let us balance the reaction. So let us come back and do one more oxidizing property. What did we learn? We said whenever it's going to react with sulfuric acid that is concentrated, it's going to form important things. One is potassium sulfate, chromium sulfate, and water as well as oxygen is liberated. That is what you're going to learn, right? So now whenever in the exam, if they give you oxidizing property, remember important compounds. First, the basic things are same, but only thing you have to remember what to oxidize to what. Now suppose if I'm going to take K2Cr2O7. We very well know sulfuric acid is compulsory because it is acting as an oxidizing agent. Now important, I have to convert, or this potassium dichromate has to oxidize potassium iodide to iodine. Now they are going to give you like this. or they may just take out this potassium and write like this, not a problem. So now I'm taking potassium iodide. Done. Okay, let me write that also so that it's not confusing. Let me write this one. Here I'm again going to take K2Cr2O7. I'm going to take sulfuric acid concentrated, that is understood, plus. Here what is my task? My task is to convert, what is this, Fe plus 2? Yes, ferrous. What is Fe plus 3? Ferric, right? Fe plus 2 is ferrous. Fe plus 3 is ferric. Now I have to convert ferrous salt to ferric salt, oxidize, right? Now ferrous salt, FeSO4, ferrous sulfate, or in the exam it may be given as Fe plus 2. Done, not a problem. Let us see. Both the products are same, only difference lies here and here. Where? This one. So let us write for common thing. First common thing. First you will get potassium sulfate, okay, K2SO4. Here also you will get K2SO4. Next you will get Cr, okay, chromium sulfate, again same thing, sulfate valency 2, chromium valency 3. Here also same story, CrSO4, chromium sulfate valency 2, chromium valency 3. Same products, isn't it? Yeah. Now next important thing, here you are going to get, now this is over, a part is over. Third important thing, water. Here also we have shown already in the earlier reaction, water. Here lies the difference. Here I said potassium iodide is getting oxidized to iodine. How? Here it is -1 charge, here it is becoming 0. Done? Yes. Here FeSO4 plus 2. So it's going to get converted or oxidized to higher oxidation state, that is ferric. Now this is ferrous sulfate, right? So ferrous sulfate. Now ferrous sulfate will become ferric sulfate. How to write ferric sulfate? Now ferric sulfate, right? Now ferric valency, the charge is plus 3. Now write sulfate, Fe and SO4. Write like this. Put brackets. Sulfate valency is 2. Iron. Now iron is which state? This is ferric state. Ferric, no? 3. So ferric means 3. Ferrous means 2. So ferric sulfate, ferrous sulfate. Because my plus 2 minus 2. Here sulfate is 2, iron is 3. So ferric sulfate. So this is your reaction. Only thing left is balancing the reactions. So after balancing your complete oxidation property, concentrate on this: iodide to iodine, ferrous to ferric. So let us come back and start with the chemical properties of your potassium dichromate. So potassium dichromate, as we said, it is an oxidizing agent, but it is a milder oxidizing agent than KMnO4. That is important. You have to remember that. So whenever I have to take potassium dichromate, I'm treating with these two acids. Okay. Before going to the topic, let me give you some information. So what are oxidizing acids? Let us see this word. Oxidizing acids. Now basically oxidizing acids are those which help in the process of oxidation, isn't it? Yeah, let's see. Now whenever I see oxidizing acids, examples are HNO3. Nitric acid is an oxidizing acid. Then perchloric acid. What is perchloric acid? Perchloric acid. Perchloric acid formula is HClO4. Then chloric acid. Chloric acid. Chloric acid formula is HClO3. This is also an oxidizing acid. Sulfuric acid, H2SO4, is an oxidizing acid. Okay. Because sulfuric acid is an oxidizing acid, we are going to take that along with your potassium dichromate. Here I am going to show you two reactions. Those reactions are with cold sulfuric acid and concentrated sulfuric acid. Yes, let's see. So whenever I am adding your sulfuric acid cold to potassium dichromate, first important thing, what is the color of potassium dichromate? It is an orange crystal, isn't it? Yes. This orange crystal, whenever you're treating with your sulfuric acid which is cold, right, this potassium dichromate is going to get converted into a red colored crystal from orange to a red crystal. That red crystal is called, okay, I'm writing that red crystal, I'll write the remaining products. It's going to convert into a red crystal from Cr to O7. It's going to form a red crystal called chromium anhydride. Okay, this is called chromium anhydride. Apart from this is also going to combine with the sulfuric acid, form KHSO4, potassium bisulfate. Chromium anhydride has come out, potassium bisulfate has come out. There's still one hydrogen, isn't it? That hydrogen comes out as water molecule. Simple. Let's see. Now, when I have to treat with concentrated sulfuric acid, K2Cr2O7, I'm going to take this sulfuric acid, now concentrated conditions. Most important, whenever you see concentrated sulfuric acid in the paper, if you don't remember the whole reaction, just simply write at least, no, this is only for your half mark, it liberates oxygen. This is important. If you write this, at least little half mark consideration would be there in the exam. Now, whenever you're adding sulfuric acid, it's going to again form 4 types of products. See, 1, 2, 3 and 4. Now I say concentrated liberates oxygen. Apart from that, just see, it's going to form 2 types of salts. One is potassium sulfate, chromium sulfate, water and oxygen. Let's write potassium sulfate, K2SO4. Chromium sulfate. What is chromium sulfate? No, let us write like this. So sulfate valency is 2, chromium valency is 3. And it's also going to form water and oxygen. Simple. So oxygen gas, important. So this is your reaction of potassium dichromate with sulfuric acid. With this, I'm going to start with the oxidizing properties. Yes. So oxidizing agents also, please note it. Very important thing for you all. If they ask you any reasoning question, what is the role of this? You can write, they act as powerful oxidizing agents. So let us see this question. This is a bit different question where I felt it is important. I just got it. So please try to practice this question. Maybe they may give you in the form of a paragraph. Here, what are we going to do? Earlier, all the reactions which you have studied was oxidizing property. We have taken different hydrogen sulfide to sulfur, your Fe+2 plus 3. Now this is a different reaction. Let's see. Now they've asked me what happens when potassium dichromate reacts with hydrogen peroxide. What is the speciality of hydrogen peroxide? We'll see. So basically, hydrogen peroxide is an oxidizer. Okay, this is one important thing you have to remember. Now, because of this peroxide linkage, it's going to form a different type of product. Yes, where the oxidation state is +6, but that different type of product, they're asking us what is that different type of product when it reacts, and we're going to show that structure. So they said a blue colored compound B is obtained when hydrogen peroxide is added to dichromate. Okay, so they have said when potassium dichromate, right, in the presence of sulfuric acid, when it is reacting with hydrogen peroxide, it's going to form a blue colored compound, it seems. Okay, what is that blue colored compound? First, let us take out this first important thing, K2SO4. As we know, we are going to get K2SO4. We've done in the earlier reactions also, and water also done, H2O. Important thing, this is your blue colored compound. Here, this Cr2O7 in the presence of peroxide is going to form a new compound, or a compound formula is CrO5. What is the CrO5? Chromium peroxide. Okay, how can I write the CrO5? It can be written like this also. See here, 5, isn't it? Cr. Now, 5 for oxygen distributing O2. Okay, 2. So 2 2s are 4. I'm left with 1 oxygen. 2 2s are 4 plus 1. Now this is your peroxide linkage. Yes, so this peroxide linkage, chromium. Now the blue colored solution is because of the formation of chromium peroxide. So this is your blue colored solution. So chromium peroxide. Done. Now this blue colored solution further immediately, like after 2 or 3 it's going to fade away. Why is it fading away? Because this chromium peroxide further reacts with your sulfuric acid, which is still there, and it's going to form first 2 and 3. Let's see what are they. First, it's going to form chromium sulfate, SO4. Sulfate valency is 2, chromium valency is this. Because now the color has faded, the blue color has faded away, it is become dull. So chromium sulfate is formed because of chromium sulfate. What are left out? Water is left out, oxygen also is left out. That's it. Simple, isn't it? So these are the important things. So the blue colored compound, you can write it as an answer. A blue color compound is CrO5 or CrO2 taken twice O. Right? Now let us come back and draw the structure of this. Now let us learn the structure of your CrO5. So that is your chromium anhydride. So one more important thing you have to remember in the continuation of the earlier identification question. So chromium, if you say chromium pentoxide or chromium peroxide, right? So this particular structure when you're writing, first important thing, the word which is given to the structure of this particular compound is butterfly structure. Butterfly structure. So if they give you write the structure, butterfly structure, whatever it is, you directly just correlate with your CrO5 structure and write it. So in CrO5 structure, most important thing, your chromium is in the center. Okay, you have 5 oxygens, isn't it? Now first forms a double bond. Done. We are left with 4 more. Now, 1 oxygen here, 1 oxygen here, O and O. The other oxygen here, another oxygen. Isn't it looking like the butterfly, the center one, and 2 wings, right? So that's why we call it as butterfly structure. So these 2 are linked and these 2 are linked. Yes. Now when I have to calculate the oxidation state of chromium here, remember most of the students what mistake they do. Now suppose if I take CrO5, what do we do? Okay, oxygen is minus 2 ma'am, 2 into 5 is minus 10 here. So this should be plus 10. No, this is wrong. No, not plus 10 here. How do we calculate? Basically, oxygen is electronegative here, isn't it? No, it is electronegative. So what happens? This oxygen is going to drag the electron density and it's going to hold 4 electrons with it. It's double bond. And after that, this particular thing, it's bonded. We consider this as one entity. Now this is going to drag 1 electron and this is going to drag 1 more electron, total of 2 electrons by single bonds. So 1 here, total of 2 electrons. So 4 here and 1 here, total of 2. So 6 electrons. So oxygens have 6 electrons, minus 6 here, and chromium obviously will have plus 6. So the oxidation state of here, this chromium is plus 6 and for oxygen it is minus 6. Remember that. So in CrO5, the valence or the oxidation state is 6, 5. This is important. This is your oxidation state. So butterfly structure. Now basically this is the butterfly structure of CrO5 is unstable, highly unstable. So how does it attain stability? So this is going to form a bond with, when it comes in contact with ether molecule, it's going to form a coordinate covalent bond and then become stable structure. So this, if you wish to learn, please remember this is unstable compound. To attain stability, it's going to combine with the ethereal solution and that finally forms a bond, making it more stable. So let us start with this chromite chloride test. Basically, what is this test? In your lab, you would have done your anion and anionic cation analysis, isn't it? That is your salt analysis. There, after finding out the presence of chloride ion, you would have gone to a test called confirmatory test for chloride anion. That confirmatory test is this chromite chloride test. So let us write. Chromite chloride test is a quantitative test. Quantitative test for detection of chloride anion. Chloride anion is Cl minus. Now you're going to test this. So basically, in the exam, if suppose this question is asked, right, you're blank with the reaction, you were not able to write or recollect the reaction. At least try to learn the paragraph which I'm going to write now, and just write that paragraph in words. you'll be at least allotted 30% of the marks. Yes. So for chromyl chloride test, what are the basic requirements? First important, when, okay, potassium dichromate is, okay, is like fused, or when potassium dichromate is treated with, okay, you can go with concentrated HCl also, not a problem, with concentrated HCl or KCl, anything, because chloride is present, isn't it? I have to test for chloride, that is your salt, suppose. Concentrated HCl or KCl in the presence of sulfuric acid. So what actually forms sulfuric acid? It forms or releases, what does it release? Reddish brown vapors. What are these reddish brown vapors? The reddish brown vapors are chromyl chloride vapors. Yes, so reddish brown vapors will just release out of the test tube. This particular test, or the release of reddish brown vapors, confirms the presence of chloride anion in the salt. Reddish brown vapors, that is chromyl chloride. Okay, this confirms the presence of chloride anion. Done. Let us write the reaction. Now potassium dichromate, KCl, sulfuric acid. Done? Yes. Now let us write the products. So first important thing what you should remember, just see this potassium and your sulfuric acid. Suppose if it is like this, HHSO4 minus, H plus plus HSO4 minus. Now this potassium K plus will combine with this, forming KHSO4, potassium bisulfate. Now next important, yes, your chromyl Cr, this compound, along with this oxygen and with this chlorine, 1, 2 and 3, are going to form a compound called CrO2Cl2. This is your chromyl chloride, which comes out in the in the form of reddish brown vapors. This reddish brown vapors will indicate, you can show to the examiners, ma'am or sir, these are the reddish brown vapors because of the presence of chloride. That chloride has formed a complex with the chromium ion and comes out as chromyl chloride. Yes, along with this water is released out. Now let us balance the reaction. How to balance? Suppose here your chromium is 2, isn't it? Now let me write 2. Okay, after chromium, let us balance chlorine. 2 2s are 4. Now how many chlorines here? Only 1, so write 4. Now done. Let us balance potassium. Potassium is 4. So potassium is 4. Let us write this. Now and chromium. Okay, let us see what is left. Chromium is balanced. 2, done. Potassium is okay. Potassium is balanced or no? 4, 5, 6, isn't it? 4, 5, 6. So I have to write 6 here. That is wrong, isn't it? 6. Now potassium is balanced. Done. Chlorine, 4 chlorines, 2 to the 4 chlorines. What is not balanced? Oxygen is not balanced. Okay. Hydrogen is 2 here. Hydrogen is 2 there. Sulfate is 6. Okay. Here. Now sulfate is 6. Suppose if I write sulfate as 6 here. Now how many hydrogens have come to? It has come to 6 to the 12 hydrogens. Sulfate is 6. Not a problem. But hydrogen is 6 to the 12. So here you can write 6 to the 12, isn't it? Okay. Suppose if I write 6. Okay, let us see. Yeah. Now, careful. Here it is 6 to the 12. Here already I have 6, isn't it? So now I'll write 3. Simple. Now observe. Here hydrogen is 6. Here 6 to. Right. So now this is your balanced reaction. We've completely balanced everything. So whenever chromyl chloride is asked to you, try to write it in words, and also try to balance the reaction.